Notice, this book is produced in Daisy Digital Talking Book, Daisy Text only, and in print format for people with bona fide print disability by V4U. This book is created for special distribution for the print disabled in accordance with Section 52 Clause 1 Subclause ZB of the Copyright Act of India as amended in 2012. The Daisy Digital Talking Book, Daisy Text only, Braille book is permitted to be used only by persons with print disabilities. Any further reproduction, distribution to any person without a print disability or any commercial use of this book is strictly prohibited and will be subject to a legal action.
Fundamentals of Physical Geography, textbook for class 11th. Contents: Unit 1, Geography as a Discipline. Chapter 1, Geography as a Discipline. Unit 2, The Earth. Chapter 2, The Origin and Evolution of the Earth. Chapter 3, Interior of the Earth. Chapter 4, Distribution of Oceans and Continents. Unit 3, Landforms. Chapter 5, Minerals and Rocks. Chapter 6, Geomorphic Processes. Chapter 7, Landforms and their Evolution. Unit 4, Climate. Chapter 8, Composition and Structure of Atmosphere. Chapter 9, Solar Radiation, Heat Balance and Temperature. Chapter 10, Atmospheric Circulation and Weather Systems. Chapter 11, Water in the Atmosphere. Chapter 12, World Climate and Climate Change. Unit 5, Water, Oceans. 13, Water, Oceans. Chapter 14, Movements of Ocean Water. Unit 6, Life on Earth. Chapter 15, Life on Earth. Chapter 16, Biodiversity and Conservation. The next page has an article from the Constitution of India. Constitution of India, Part 3, Articles 12 to 35. Subject to certain conditions, some exceptions are reasonable restrictions. Guarantees these fundamental rights. 1. Right to equality. Bit 1. Before law and equal protection of laws. Bit 2. Irrespective of religion, race, caste, sex, or place of birth. Bit 3. Of opportunity in public employment. Bit 4. By abolition of untouchability and titles. 2. Right to freedom. Bit 1. Of expression, assembly, association, movement, residence, and profession. Bit 2. Of certain protections in respect of conviction for offences. Bit 3. Of protection of life and personal liberty. Bit 4. Of free and compulsory education for children between the age of 6 and 14 years. 5. Bit 5. Of protection against arrest and detention in certain cases. 3. Right against exploitation. Bit 1. For prohibition of traffic in human beings and forced labor. Bit 2. For prohibition of employment of children in hazardous jobs. 4. Right to freedom of religion. Bit 1. Freedom of conscience and free profession, practice, and propagation of religion. Bit 2. Freedom to manage religious affairs. Bit 3. Freedom as to payment of taxes for promotion of any particular religion. Bit 4. Freedom as to attendance at religious instruction or religious worship in educational institution wholly maintained by the state. 5. Cultural and educational rights. Bit 1. For protection of interests of minorities to conserve their language, script and culture. Bit 2. For minorities to establish and administer educational institutions of their choice. 6. Right to constitutional remedies. Bit 1. By issuance of directions or orders or writs by the Supreme Court and High Courts for enforcement of these fundamental rights.
Chapter 1: Geography as a Discipline. You have studied geography as one of the components of your social science course up to the secondary stage. You were already aware of some of the phenomena of geographical nature in the world and its different parts. Now, you will study geography as an independent subject and learn about the physical environment of the Earth, human activities, and their interactive relationships. Therefore, a pertinent question you can ask at this stage is, why should we study geography? We live on the surface of the Earth. Our lives are affected by our surroundings in many ways. We depend on the resources to sustain ourselves in the surrounding areas. Primitive societies subsisted on natural means of subsistence, i.e., edible plants and animals. With the passage of time, we developed technologies and started producing our food using natural resources, such as land and water. We adjusted our food habits and clothing according to the prevailing weather conditions. There are variations in the natural resource base, technological development, adaptation with, and modification of physical environment, social organizations, and cultural development. As a student of geography, you should be curious to know about all the phenomena which vary over space. You'll learn about the diverse lands and people. You should also be interested in understanding the changes which have taken place over time. Geography equips you to appreciate the diversity and investigate into the causes responsible for creating such variations over time and space. You will develop skills to understand the globe converted into maps and have a visual sense of the Earth's surface. The understanding and the skills obtained in modern scientific techniques, such as GIS and computer cartography, equip you to meaningfully contribute to the national endeavor for development. Now, the next question which you may like to ask is, what is geography? You know that Earth is our home. It is also the home of many other creatures, big and small, which live on the Earth and sustain. The Earth's surface is not uniform. It has variations in its physical features. There are mountains, hills, valleys, plains, plateaus, oceans, lakes, deserts, and wilderness. There are variations in its social and cultural features too. There are villages, cities, roads, railways, ports, markets, and many other elements created by human beings across the entire period of their cultural development. This variation provides a clue to the understanding of the relationship between the physical environment and social/cultural features. The physical environment has provided the stage on which human societies enacted the drama of their creative skills with the tools and techniques which they invented and evolved in the process of their cultural development. Now, you should be able to attempt the answer of the question posed earlier as to, what is geography? In very simple words, it can be said that geography is the description of the Earth. The term geography was first coined by Eratosthenes, a Greek scholar, 276 to 194 BC. The word has been derived from two roots from Greek language, geo, earth, and graphos, description. Put together, they mean description of the earth. The earth has always been seen as the abode of human beings, and thus scholars define geography as the description of the earth as the abode of human beings. You are aware of the fact that reality is always multifaceted, and the earth is also multidimensional. That is why many disciplines from natural sciences such as geology, pedology, oceanography, botany, zoology, and meteorology, and a number of sister disciplines in social sciences such as economics, history, sociology, political science, anthropology, etc., study different aspects of the Earth's surface. Geography is different from other sciences in its subject matter and methodology, but at the same time, it is closely related to other disciplines. Geography derives its database from all the natural and social sciences and attempts their synthesis. We have noted that there exist variations over the surface of the Earth in its physical as well as cultural environment. A number of phenomena are similar, and many are dissimilar. It was, therefore, logical to perceive geography as a study of areal differentiation. Thus, geography was perceived to study all those phenomena which vary over space. Geographers do not study only the variations in the phenomena over the Earth's surface, space, but also study the associations with the other factors which cause these variations. For example, cropping patterns differ from region to region, but this variation in cropping pattern, as a phenomenon, is related to variations in soil, climates, demand in the market, capacity of the farmer to invest, and technological inputs available to her/him. Thus, the concern of geography is to find out the causal relationship between any two phenomena or between more than one phenomenon. A geographer explains the phenomena in a frame of cause and effect relationship, as it does not only help in interpretation, but also foresees the phenomena in future. The geographical phenomena, both the physical and human, are not static, but highly dynamic. They change over time as a result of the interactive process between ever-changing Earth and untiring and ever-active human beings. Primitive human societies were directly dependent on their immediate environment. Geography, thus, is concerned with the study of nature and human interactions as an integrated whole. Human is an integral part of nature, and nature has the imprints of human. Nature is influenced by different aspects of human life. Its imprints can be noticed on food, clothing, shelter, and occupation. Human beings have come to terms with nature through adaptation and modification. As you already know, the present society has passed the stage of primitive societies, which were directly dependent on their immediate physical environment for sustenance. Present societies have modified their natural environment by inventing and using technology, and thus have expanded the horizon of their operation by appropriating and utilizing the resources provided by nature. With the gradual development of technology, human beings were able to loosen the shackles of their physical environment. Technology helped in reducing the harshness of labor, increased labor efficiency, and provided leisure to human beings to attend to the higher needs of life. It also created the scale of production and the mobility of labor. The interaction between the physical environment and human beings has been very succinctly described by a poet in the following dialogue between human and nature, God. You created the soil, I created the cup. You created night, I created the lamp. You created wilderness, hilly terrains, and deserts. I created flower beds and gardens. Human beings have claimed their contribution using natural resources. With the help of technology, human beings moved from the stage of necessity to a stage of freedom. They've put their imprints everywhere and created new possibilities in collaboration with nature. Thus, we now find humanized nature and naturalized human beings, and geography studies this interactive relationship. The space got organized with the help of the means of transportation and communication network. The links, routes, and nodes, settlements of all types and hierarchies, integrated the space, and gradually it got organized. As a social science discipline, geography studies the spatial organization and spatial integration. Geography as a discipline is concerned with three sets of questions. Number 1. Some questions are related to the identification of the patterns of natural and cultural features as found over the surface of the earth. These questions are about what? Some questions are related to the distribution of natural and human cultural features over the surface of the earth. These questions are about where. Taken together, both these questions take care of distributional and locational aspects of the natural and cultural features. These questions provided inventorized information of what features and where located. It was a very popular approach during the colonial period. These two questions did not make geography a scientific discipline till the third question was added. Number 3. The third question is related to the explanation or causal relationships between features and the processes and phenomena. This aspect of geography is related to the question, why? Geography as a discipline is related to space and takes notes of spatial characteristics and attributes. It studies the patterns of distribution, location, and concentration of phenomena over space and interprets them, providing explanations for these patterns. It takes note of the associations and interrelationships between the phenomena over space and interprets them, providing explanations for these patterns. It also takes note of the associations and interrelationships between the phenomena resulting from the dynamic interaction between human beings and their physical environment. Geography as an integrating discipline. Geography is a discipline of synthesis. It attempts spatial synthesis, and history attempts temporal synthesis. Its approach is holistic in nature. It recognizes the fact that the world is a system of interdependencies. The present world is being perceived as a global village. The distances have been reduced by better means of transportation, increasing accessibility. The audiovisual media and information technology have enriched the database. Technology has provided better chances of monitoring natural phenomena as well as the economic and social parameters. Geography as an integrating discipline has interfaced with numerous natural and social sciences. All the sciences, whether natural or social, have one basic objective of understanding the reality. Geography attempts to comprehend the associations of phenomena as related in sections of reality. Figure 1.1 shows the relationship of geography with other sciences. Every discipline concerned with scientific knowledge is linked with geography as many of their elements vary over space. Geography helps in understanding the reality in totality in its spatial perspective. Geography thus not only takes note of the differences in the phenomena from place to place, but integrates them holistically, which may be different at other places. A geographer is required to have a broad understanding of all the related fields to be able to logically integrate them. This integration can be understood with some examples. Geography influences historical events. Spatial distance itself has been a very potent factor to alter the course of history of the world. Spatial depth provided defense to many countries, particularly in the last century. In traditional warfare, countries with large size and area gain time at the cost of space. The defense provided by oceanic expanse around the countries of the New World has protected them from wars being imposed on their soil. If we look at the historical events world over, each one of them can be interpreted geographically. In India, Himalayas have acted as great barriers and provided protection, but the passes provided routes to the migrants and invaders from Central Asia. The seacoast has encouraged contact with people from East and Southeast Asia, Europe, and Africa. Navigation technology helped European countries to colonize a number of countries of Asia and Africa, including India, as they got accessibility through oceans. The geographical factors have modified the course of history in different parts of the world. Every geographical phenomenon undergoes change through time and can be explained temporally. The changes in landforms, climate, vegetation, economic activities, and cultural developments have followed a definite historical course. Many geographical features result from the decision-making process by different institutions at a particular point of time. It is possible to convert time in terms of space and space in terms of time. For example, it can be said that place A is 1,500 kilometers from place B, or alternately, it can also be said that place A is 2 hours away if one travels by plane, or 17 hours away if one travels by a fast-moving train. It is for this reason time is an integral part of geographical studies as the fourth dimension. Please mention other three dimensions. Figure 1.1 amply depicts the linkages of geography with different natural and social sciences. This linkage can be put under two segments: physical geography and natural sciences. All the branches of physical geography, as shown in Figure 1.1, have interface with natural sciences. The traditional physical geography is linked with geology, meteorology, hydrology, and pedology, and thus geomorphology, climatology, oceanography, and soil geography respectively have very close link with the natural sciences, as these derive their data from these sciences. Biogeography is closely related to botany, zoology, as well as ecology, as human beings are located in different locational niche. A geographer should have some proficiency in mathematics and art, particularly in drawing maps. Geography is very much linked with the study of astronomical locations and deals with latitudes and longitudes. The shape of the Earth is geoid, but the basic tool of a geographer is a map, which is two-dimensional representation of the Earth. The problem of converting geoids into two dimensions can be tackled by projections constructed graphically or mathematically. The cartographic and quantitative techniques require sufficient proficiency in mathematics, statistics, and econometrics. Maps are prepared through artistic imagination. Making sketches, mental maps, and cartographic work require proficiency in arts. Geography and social sciences. Each social science sketched in Figure 1.1 has interface with one branch of geography. The relationship between geography and history have already been outlined in detail. Every discipline has a philosophy, which is the raison d'etre for that discipline. Philosophy provides roots to a discipline, and in the process of its evolution, it also experiences distinct historical processes. Thus, the history of geographical thought as mother branch of geography is included universally in its curricula. All the social science disciplines, viz. Sociology, political science, economics, and demography, study different aspects of social reality. The branches of geography, viz. Social, political, economic, and population and settlements, are closely linked with these disciplines, as each of them has spatial attributes. The core concern of political science is territory, people, and sovereignty, while political geography is also interested in the study of the state as a spatial unit, as well as people and their political behavior. Economics deals with basic attributes of the economy, such as production, distribution, exchange, and consumption. Each of these attributes also has spatial aspects, and here comes the role of economic geography to study the spatial aspects of production, distribution, exchange, and consumption. Likewise, population geography is closely linked with the discipline of demography. The above discussion shows that geography has strong interface with natural and social sciences. It follows its own methodology of study, which makes it distinct from others. It has osmotic relationship with other disciplines. While all the disciplines have their own individual scope, This individuality does not obstruct the flow of information, as in case of all cells in the body that have individual identity separated by membranes, but the flow of blood is not obstructed. Geographers use data obtained from sister disciplines and attempt synthesis over space. Maps are very effective tools of geographers in which the tabular data is converted into visual form to bring out the spatial pattern. Branches of geography. Please study Figure 1.1 for recapitulation. It is very clearly brought out that geography is an interdisciplinary subject of study. The study of every subject is done according to some approach. The major approaches to study geography have been 1. Systematic, and 2. Regional. The systematic geography approach is the same as that of general geography. This approach was introduced by Alexander von Humboldt, a German geographer, 1769 to 1859, while regional geography approach was developed by another German geographer and a contemporary of Humboldt, Karl Ritter, 1779 to 1859. In systematic approach, Figure 1.2, a phenomenon is studied world over as a whole, and then the identification of typologies or spatial patterns is done. For example, if one is interested in studying natural vegetation, the study will be done at the world level as a first step. The typologies such as equatorial rainforests or softwood conical forests or monsoon forests, etc., will be identified, discussed, and delimited. In the regional approach, the world is divided into regions at different hierarchical levels, and then all the geographical phenomena in a particular region are studied. These regions may be natural, political, or designated region. The phenomena in a region are studied in a holistic manner, searching for unity in diversity. Dualism is one of the main characteristics of geography, which got introduced from the very beginning. This dualism depended on the aspect emphasized in the study. Earlier scholars laid emphasis on physical geography, but humans are an integral part of the Earth's surface. They are part and parcel of nature. They also have contributed through their cultural development, thus developed human geography with emphasis on human activities. Branches of geography based on systematic approach. Number 1. Physical geography. 1. Geomorphology is devoted to the study of landforms, their evolution, and related processes. 2. Climatology encompasses the study of structure, of atmosphere, and elements of weather and climates, and climatic types and regions. 3. Hydrology studies the realm of water over the surface of the earth, including oceans, lakes, rivers, and other water bodies, and its effect on different life forms, including human life and their activities. 4. Soil geography is devoted to study the processes of soil formation, soil types, and their fertility status, distribution, and use. This recording.
Okay. That's good.
No.
Then,
Wait, you're not supposed to speak.
you
It'll.
can't delete it?
Number 2. Human geography. 1. Social/cultural geography encompasses the study of society and its spatial dynamics, as well as the cultural elements contributed by the society. 2. Population and settlement geography, rural and urban. It studies population growth, distribution, density, sex ratio, migration, and occupational structure, etc. Settlement geography studies the characteristics of rural and urban settlements. 3. Economic geography studies economic activities of the people, including agriculture, industry, tourism, trade, and transport, infrastructure, and services, etc. 4. Historical geography studies the historical processes through which the space gets organized. Every region has undergone some historical experiences before attaining the present-day status. The geographical features also experience temporal changes and these form the concerns of historical geography. 5. Political geography looks at the space from the angle of political events and studies boundaries, space relations between neighboring political units, delimitation of constituencies, election scenario, and develops theoretical framework to understand the political behavior of the population. Number 3. Biogeography. The interface between physical geography and human geography has led to the development of biogeography, which includes 1. Plant geography, which studies the spatial pattern of natural vegetation in their habitats. 2. Zoogeography, which studies the spatial patterns and geographic characteristics of animals and their habitats. 3. Ecology/ecosystem deals with the scientific study of the habitats characteristics of species. 4. Environmental geography concerns world over leading to the realization of environmental problems such as land gradation, pollution, and concerns for conservation has resulted in the introduction of this new branch in geography. Branches of geography based on regional approach. Figure 1.3. Number 1. Regional studies/area studies, comprising macro, meso, and micro-regional studies. Number 2. Regional planning, comprising country/rural and town/urban planning. Number 3. Regional development. Number 4. Regional analysis. There are two aspects which are common to every discipline. These are 1. Philosophy. A. Geographical thought. B. Land and human interaction/human ecology. 2. Methods and techniques. A. Cartography including computer cartography. B. Quantitative techniques/statistical techniques. C. Field survey methods. D. Geoinformatics comprising techniques such as remote sensing, GIS, GPS, etc. The above classification gives a comprehensive format of the branches of geography. Generally, geography curricula is taught and learned in this format, but this format is not static. Any discipline is bound to grow with new ideas, problems, methods, and techniques. For example, what was once manual cartography has now been transformed into computer cartography. Technology has enabled scholars to handle large quantum of data. The Internet provides extensive information. Thus, the capacity to attempt analysis has increased tremendously. GIS has further opened vistas of knowledge. GPS has become a handy tool to find out exact locations. Technologies have enhanced the capacity of attempting synthesis with sound theoretical understanding. You will learn some preliminary aspects of these techniques in your book, Practical Work in Geography, Part 1, NCERT 2006. You will continue to improve upon your skills and learn about their application. Physical geography and its importance. This chapter appears in the book entitled Fundamentals of Physical Geography. The contents of the book clearly reflect its scope. It is, therefore, appropriate to know the importance of this branch of geography. Physical geography includes the study of lithosphere, landforms, drainage, relief, and physiography. Atmosphere, its composition, structure, elements, and controls of weather and climate. Temperature, pressure, winds, precipitation, climatic types, etc. Hydrosphere, oceans, seas, lakes, and associated features with water realm. And biosphere, life forms including human being and macroorganism and their sustaining mechanism, viz. Food chain, ecological parameters, and ecological balance. Soils are formed through the process of pedogenesis and depend on the parent rocks, climate, biological activity, and time. Time provides maturity to soils and helps in the development of soil profiles. Each element is important for human beings. Landforms provide the base on which human activities are located. The plains are utilized for agriculture. Plateaus provide forests and minerals. Mountains provide pastures, forests, tourist spots, and are sources of rivers providing water to towlands. Climate influences our house types, clothing, and food habitats. The climate has a profound effect on vegetation, cropping pattern, livestock farming, and some industries, etc. Human beings have developed technologies which modify climatic elements in a restricted space, such as air conditioners and coolers. Temperature and precipitation ensure the density of forests and quality of grassland. In India, monsoonal rainfall sets the agricultural rhythm in motion. Precipitation recharges the groundwater aquifers, which later provides water for agriculture and domestic use. We study oceans, which are the storehouses of resources. Besides fish and other seafood, oceans are rich in mineral resources. India has developed the technology for collecting manganese nodules from oceanic bed. Soils are renewable resources, which influence a number of economic activities, such as agriculture. The fertility of the soil is both naturally determined and culturally induced. Soils also provide the basis for the biosphere, accommodating plants, animals, and microorganisms. What is geography? Geography is concerned with the description and explanation of the areal differentiation of the Earth's surface. Richard Hartshorne. Geography studies the differences of phenomena usually related in different parts of the Earth's surface. Hettner. The study of physical geography is emerging as a discipline of evaluating and managing natural resources. In order to achieve this objective, it is essential to understand the intricate relationship between physical environment and human beings. Physical environment provides resources, and human beings utilize these resources and ensure their economic and cultural development. Accelerated pace of resource utilization with the help of modern technology has created ecological imbalance in the world. Hence, a better understanding of physical environment is absolutely essential for sustainable development. Exercises. Number 1. Multiple choice questions. 1. Which of the following scholars coined the term geography? A. Herodotus, B. Eratosthenes, C. Galileo, D. Aristotle. 2. Which one of the following features can be termed as physical feature? A. Port, B. Road, C. Plain, D. Water park. 3. Make correct pairs from the following two columns and mark the correct option. 1. Meteorology. 2. Demography. 3. Sociology. 4. Pedology. A. Population geography. B. Soil geography. C. Climatology. D. Social geography. A. 1B, 2C, 3A, 4D. B. 1A, 2D, 3B, 4C. C. 1D, 2B, 3C, 4A. D. 1C, 2A, 3D, 4B. 4. Which one of the following questions is related to cause-effect relationship? A. Why. B. Where. C. What. D. When. 5. Which one of the following disciplines attempts temporal synthesis? A. Sociology. B. Geography. C. Anthropology. D. History. Number 2. Answer the following questions in about 30 words. 1. What important cultural features do you observe while going to school? Are they similar or dissimilar? Should they be included in the study of geography or not? If yes, why? Two, you have seen a tennis ball, a cricket ball, an orange, and a pumpkin. Which one amongst these resembles the shape of the earth? Why have you chosen this particular item to describe the shape of the earth? Three, do you celebrate Van Manhotsava in your school? Why do we plant so many trees? How do the trees maintain ecological balance? Four, you have seen elephants, deer, earthworms, trees, and grasses. Where do they live or grow? What is the name given to this sphere? Can you describe some of the important features of this sphere? Five, how much time do you take to reach your school from your house? Had the school been located across the road from your house, how much time would you have taken to reach school? What is the effect of the distance between your residence and the school on the time taken in commuting? Can you convert time into space and vice versa? Number 3. Answer the following questions in about 150 words. 1. You observe every day in your surroundings that there is variation in natural as well as cultural phenomena. All the trees are not of the same variety. All the birds and animals you see are different. All these different elements are found on Earth. Can you now argue that geography is the study of areal differentiation? Two, you have already studied geography, history, civics, and economics as parts of social studies. Attempt an integration of these disciplines, highlighting their interface. Project work. Select forest as a natural resource. 1. Prepare a map of India showing the distribution of different types of forests. 2. Write about the economic importance of forests for the country. 3. Prepare a historical account of conservation of forests in India with focus on Chipko movements in Rajasthan and Uttaranchal. Chapter 2. The Origin and Evolution of the Earth. Do you remember the nursery rhyme, Twinkle, Twinkle, Little Star? Starry nights have always attracted us since the childhood. You may also have thought of these stars and had numerous questions in your mind. Questions such as, how many stars are there in the sky? How did they come into existence? Can one reach the end of the sky? Maybe many more such questions are still there in your mind. In this chapter, you will learn how these twinkling little stars were formed. With that, you will eventually also read the story of origin and evolution of the Earth. Early theories. Origin of the Earth. A large number of hypotheses were put forth by different philosophers and scientists regarding the origin of the Earth. One of the earlier and popular arguments was by German philosopher Immanuel Kant. Mathematician Laplace revised it in 1796. It is known as nebular hypothesis. The hypothesis considered that planets were formed out of a cloud of material associated with a youthful sun which was slowly rotating. Later in 1900, Chamberlain and Moulton considered that a wandering star approached the Sun. As a result, a cigar-shaped extension of material was separated from the solar surface. As the passing star moved away, the material separated from the solar surface continued to revolve around the Sun, and it slowly condensed into planets. Sir James Johns and later Sir Harold Jeffrey supported this argument of a companion to the Sun to have been coexisting. These arguments are called binary theories. In 1950, Otto Schmidt in Russia and Carl Weizsäcker in Germany somewhat revised the nebular hypothesis through differing in details. They considered that the Sun was surrounded by solar nebula containing mostly the hydrogen and helium, along with what may be termed as dust. The friction and collision of particles led to formation of a disc-shaped cloud, and the planets were formed through the process of accretion. However, scientists in later period took up the problems of origin of universe rather than that of just the Earth or the planets. Modern theories. Origin of the universe. The most popular argument regarding the origin of the universe is the Big Bang theory. It is also called expanding universe hypothesis. Edwin Hubble, in 1920, provided evidence that the universe is expanding. As time passes, galaxies move further and further apart. You can experiment and find what does the expanding universe mean. Take a balloon and mark some points on it to represent the galaxies. Now, if you start inflating the balloon, the points marked on the balloon will appear to be moving away from each other as the balloon expands. Similarly, the distance between the galaxies is also found to be increasing, and thereby, the universe is considered to be expanding. However, you will find that besides the increase in the distance between the points on the balloon, the points themselves are expanding. This is not in accordance with the fact. Scientists believe that though the space between the galaxies is increasing, observations do not support the expansion of galaxies, so the balloon example is only partially correct. The Big Bang theory considers the following stages in the development of the universe. 1. In the beginning, all matter forming the universe existed in one place in the form of a tiny ball, singular atom, with an unimaginably small volume, infinite temperature, and infinite density. 2. At the Big Bang, the tiny ball exploded violently. This led to a huge expansion. It is now generally accepted that the event of Big Bang took place 13.7 billion years before the present. The expansion continues even to the present day. As it grew, some energy was converted into matter. There was particularly rapid expansion within fractions of a second after the bang. Thereafter, the expansion has slowed down. Within first 3 minutes from the Big Bang event, the first atom began to form. 3. Within 300,000 years from the Big Bang, temperature dropped to 4,500 Kelvin and gave rise to atomic matter. The universe became transparent. The expansion of universe means increase in space between the galaxies. An alternative to this was Hoyle's concept of steady state. It considered the universe to be roughly the same at any point of time. However, with greater evidence becoming available about the expanding universe, scientific community at present favors argument of expanding universe. The star formation. The distribution of matter and energy was not even in the early universe. These initial density differences gave rise to differences in gravitational forces, and it caused the matter to get drawn together. These formed the basis for development of galaxies. A galaxy contains a number of stars. Galaxies spread over vast distances that are measured in thousands of light years. The diameters of individual galaxies range from 80,000 to 150,000 light years. A galaxy starts to form by accumulation of hydrogen gas in the form of a very large cloud called nebula. Eventually, growing nebula develops localized clumps of gas. These clumps continue to grow into even denser gaseous bodies, giving rise to formation of stars. The formation of stars is believed to have taken place some 5 to 6 billion years ago. A light year is a measure of distance and not of time. Light travels at a speed of 300,000 kilometers per second. Considering this, the distances the light will travel in 1 year is taken to be 1 light year. This equals to 9.461 times 10 to the power of 12 kilometers. The mean distance between the Sun and the Earth is 149,598,000 kilometers. In terms of light years, it is 8.311 minutes. Formation of planets. The following are considered to be stages in the development of planets. 1. The stars are localized lumps of gas within a nebula. The gravitational force within the lumps leads to the formation of a core to the gas cloud and a huge rotating disk of gas, and dust develops around the gas core. 2. In the next stage, the gas cloud starts getting condensed, and the matter around the core develops into small rounded objects. These small rounded objects, by the process of cohesion, develop into what is called planetesimals. Larger bodies start forming by collision, and gravitational attraction causes the material to stick together. Planetesimals are a large number of smaller bodies. 3. In the final stage, these large number of small planetesimals accrete to form a fewer large bodies in the form of planets. Our solar system. Our solar system consists of 8 planets. The nebula from which our solar system is supposed to have been formed started its collapse and core formation sometime 5 to 5.6 billion years ago, and the planets were formed about 4.6 billion years ago. Our solar system consists of the Sun, the star, 8 planets, 63 moons, millions of smaller bodies like asteroids and comets, and huge quantity of dust grains and gases. Out of the 8 planets, Mercury, Venus, Earth, and Mars are called as inner planets, as they lie between the Sun and the belt of asteroids. The 4 other planets are called the outer planets. Alternatively, the first 4 are called terrestrial, meaning Earth-like, as they are made up of rocks and metals, and have relatively high densities. The rest 4 are called Jovian, or gas giant planets. Jovian means Jupiter-like. Most of them are much larger than the terrestrial planets and have thick atmosphere, mostly of helium and hydrogen. All the planets were formed in the same period, sometime about 4.6 billion years ago. Till recently, August 2006, Pluto was also considered a planet. However, in a meeting of the International Astronomical Union for Celestial Objects 2003 UB, discovered in recent past may be called dwarf planet. Some data regarding our solar system are given in the box below. Why are the inner planets rocky while others are mostly gaseous in form? The difference between terrestrial and Jovian planets can be attributed to the following conditions. 1. The terrestrial planets were formed in the close vicinity of the parent star, where it was too warm for gases to condense to solid particles. Jovian planets were formed at quite a distant location. 2. The solar wind was most intense nearer the Sun, so it blew off lots of gas and dust from the terrestrial planets. The solar winds were not all that intense to cause similar removal of gases from the Jovian planets. 3. The terrestrial planets are smaller, and their lower gravity could not hold the escaping gases. The Moon. The Moon is the only natural satellite of the Earth. Like the origin of the Earth, there have been attempts to explain how the Moon was formed. In 1838, Sir George Darwin suggested that initially the Earth and the Moon formed a single rapidly rotating body. The whole mass became a dumbbell-shaped body, and eventually it broke. It was also suggested that the material forming the Moon was separated from what we have at present, the depression occupied by the Pacific Ocean. However, the present scientists do not accept either of the explanations. It is now generally believed that the formation of Moon as a satellite of the Earth is an outcome of giant impact, or what is described as the Big Splat. A body of the size of 1 to 3 times that of Mars collided into the Earth sometime shortly after the Earth was formed. it blasted a large part of the Earth into space. This portion of blasted material then continued to orbit the Earth and eventually formed into the present Moon about 4.44 billion years ago. Earth. Do you know that the planet Earth initially was a barren, rocky, and hot object with a thin atmosphere of hydrogen and helium? This is far from the present-day picture of the Earth. Hence, there must have been some events, processes which may have caused this change from rocky, barren, and hot Earth to a beautiful planet with ample amount of water and conducive atmosphere favoring the existence of life. In the following section, you will find out how the period between the 4,600 million years and the present led to the evolution of life on the surface of the planet. The Earth has a layered structure. From the outermost end of the atmosphere to the center of the Earth, the material that exists is not uniform. The atmospheric matter has the least density. From the surface to deeper depths, the Earth's interior has different zones, and each of these contain materials with different characteristics. How was the layered structure of the Earth developed? Evolution of lithosphere. The Earth was mostly in a volatile state during its primordial stage. Due to gradual increase in density, the temperature inside has increased. As a result, the material inside started getting separated depending on their densities. This allowed heavier materials, like iron, to sink towards the center of the Earth, and the lighter ones to move towards the surface. With passage of time, it cooled further and solidified and condensed into a smaller size. This later led to the development of the outer surface in the form of a crust. During the formation of the Moon, due to the giant impact, the Earth was further heated up. It is through the process of differentiation that the Earth-forming material got separated into different layers. Starting from the surface to the central parts, we have layers like crust, mantle, outer core, and inner core. From the crust to the core, the density of the material increases. We shall discuss in detail the properties of each of this layer in the next chapter. Evolution of atmosphere and hydrosphere. The present composition of Earth's atmosphere is chiefly contributed by nitrogen and oxygen. You will be dealing with the composition and structure of the Earth's atmosphere in Chapter 8. There are 3 stages in the evolution of the present atmosphere. The first stage is marked by the loss of primordial atmosphere. In the second stage, the hot interior of the Earth contributed to the evolution of the atmosphere. Finally, the composition of the atmosphere was modified by the living world through the process of photosynthesis. The early atmosphere, with hydrogen and helium, is supposed to have been stripped off as a result of the solar winds. This happened not only in case of the Earth, but also in all the terrestrial planets, which were supposed to have lost their primordial atmosphere through the impact of solar winds. During the cooling of the Earth, gases and water vapor were released from the interior solid Earth. This started the evolution of the present atmosphere. The early atmosphere largely contained water vapor, nitrogen, carbon dioxide, methane, ammonia, and very little of free oxygen. The process through which the gases were outpoured from the interior is called degassing. Continuous volcanic eruptions contributed water vapor and gases to the atmosphere. As the Earth cooled, the water vapor released started getting condensed. The carbon dioxide in the atmosphere got dissolved in rainwater, and the temperature further decreased, causing more condensation and more rains. The rainwater falling onto the surface got collected in the depressions to give rise to oceans. The Earth's oceans were formed within 500 million years from the formation of the Earth. This tells us that the oceans are as old as 4,000 million years. Sometime around 3,800 million years ago, life began to evolve. However, around 2,500 to 3,000 million years before the present, the process of photosynthesis got evolved. Life was confined to the oceans for a long time. Oceans began to have the contribution of oxygen through the process of photosynthesis. Eventually, oceans were saturated with oxygen, and 2,000 million years ago, oxygen began to flood the atmosphere. Origin of life. The last phase in the evolution of the Earth relates to the origin and evolution of life. It is undoubtedly clear that initially the Earth, or even the atmosphere of the Earth, was not conducive for the development of life. Modern scientists refer to the origin of life as a kind of chemical reaction which first generated complex organic molecules and assembled them. This assemblage was such that they could duplicate themselves, converting inanimate matter into living substance. The record of life that existed on this planet in different periods is found in rocks in the form of fossils. The microscopic structures closely related to the present form of blue algae have been found in geological formations much older than some 3,000 million years. It can be assumed that life began to evolve sometime 3,800 million years ago. The summary of evolution of life from unicellular bacteria to the modern man is given in the geological time scale. Exercises. Number 1. Multiple choice questions. 1. Which one of the following figures represents the age of the Earth? A. 4.6 million years. B. 13.7 billion years. C. 4.6 billion years. D. 13.7 trillion years. Two. Which one of the following has the longest duration? A. Eons. B. Period. C. Era. D. Epoch. 3. Which one of the following is not related to the formation or modification of the present atmosphere? A. Solar winds. B. Differentiation. C. Degassing. D. Photosynthesis. Four. Which one of the following represents the inner planets? A. Planets between the Sun and the Earth. B. Planets between the Sun and the belt of asteroids. C. Planets in gaseous state. D. Planets without satellites. Five. Life on the Earth appeared around how many years before the present? A. 13.7 billion. B. 3.8 million. C. 4.6 billion. D. 3.8 billion. Number 2. Answer the following questions in about 30 words. 1. Why are the terrestrial planets rocky? 2. What is the basic difference in the arguments related to the origin of the Earth given by A. Kant and Laplace, B. Chamberlain and Moulton? Three. What is meant by the process of differentiation? 4. What was the nature of the Earth's surface initially? 5. What were the gases which initially formed the Earth's atmosphere? Number 3. Answer the following questions in about 150 words. 1. Write an explanatory note on the Big Bang Theory. 2. List the stages in the evolution of the Earth and explain each stage in brief. Project work. Collect information about the Project Stardust website www.sci.edu/public.html and www.nasm.edu along the following lines. 1. Which is the agency that has launched this project? 2. Why are scientists interested in collecting stardust? 3. Where from the stardust is being collected? Chapter 3. Interior of the Earth. What do you imagine about the nature of the Earth? Do you imagine it to be a solid ball like cricket ball, or a hollow ball with a thick cover of rocks, i.e. lithosphere? Have you ever seen photographs or images of a volcanic eruption on the television screen? Can you recollect the emergence of hot molten lava, dust, smoke, fire, and magma flowing out of the volcanic crater? The interior of the Earth can be understood only by indirect evidences, as neither anyone has, nor anyone can, reach the interior of the Earth. The configuration of the surface of the Earth is largely a product of the processes operating in the interior of the Earth. Exogenic as well as endogenic processes are constantly shaping the landscape. A proper understanding of the physiographic character of a region remains incomplete if the effects of endogenic processes are ignored. Human life is largely influenced by the physiography of the region. Therefore, it is necessary that one gets acquainted with the forces that influence landscape development. To understand why the Earth shakes, or how a tsunami wave is generated, it is necessary that we know certain details of the interior of the Earth. In the previous chapter, you have noted that the Earth-forming materials have been distributed in the form of layers, from the crust to the core. It is interesting to know how scientists have gathered information about these layers and what are the characteristics of each of these layers. This is exactly what this chapter deals with. Sources of information about the interior. The Earth's radius is 6,370 kilometers. No one can reach the center of the Earth and make observations or collect samples of the material. Under such conditions, you may wonder how scientists tell us about the Earth's interior and the type of materials that exist at such depths. Most of our knowledge about the interior of the Earth is largely based on estimates and inferences. Yet, a part of the information is obtained through direct observations and analysis of materials. Direct sources. The most easily available solid Earth material is surface rock, or the rocks we get from mining areas. Gold mines in South Africa are as deep as 3 to 4 kilometers. Going beyond this depth is not possible, as it is very hot at this depth. Besides mining, scientists have taken up a number of projects to penetrate deeper depths to explore the conditions in the crustal portions. Scientists world over are working on two major projects, such as Deep Ocean Drilling Project and Integrated Ocean Drilling Project. The deepest drill at Kola in Arctic Ocean has so far reached a depth of 12 kilometers. This and many deep drilling projects have provided large volume of information through the analysis of materials collected at different depths. Volcanic eruption forms another source of obtaining direct information. As and when the molten material, magma, is thrown onto the surface of the Earth during volcanic eruption, it becomes available for laboratory analysis. However, it is difficult to ascertain the depth of the source of such magma. Indirect sources. Analysis of properties of matter indirectly provides information about the interior. We know through the mining activity that temperature and pressure increase with the increasing distance from the surface towards the interior in deeper depths. Moreover, it is also known that the density of material also increases with depth. It is possible to find the rate of change of these characteristics. Knowing the total thickness of the Earth, scientists have estimated the values of temperature, pressure, and the density of materials at different depths. The details of these characteristics with reference to each layer of the interior are discussed in this chapter. Another source of information are the meteors that at times reach the Earth. However, it may be noted that the material that becomes available for analysis from meteors is not from the interior of the Earth. The material and the structure observed in the meteors are similar to that of the Earth. They are solid bodies developed out of materials same as, or similar to, our planet. Hence, this becomes yet another source of information about the interior of the Earth. The other indirect sources include gravitation, magnetic field, and seismic activity. The gravitation force, G, is not the same at different latitudes on the surface. It is greater near the poles and less at the equator. This is because of the distance from the center at the equator being greater than at the poles. The gravity values also differ according to the mass of material. The uneven distribution of mass of material within the Earth influences this value. The reading of the gravity at different places is influenced by many other factors. These readings differ from the expected values. Such a difference is called gravity anomaly. Gravity anomalies give us information about the distribution of mass of the material in the crust of the Earth. Magnetic surveys also provide information about the distribution of magnetic material in the crustal portion, and thus provide information about the distribution of materials in this part. Seismic activity is one of the most important sources of information about the interior of the Earth. Hence, we shall discuss it in some detail. Earthquake. The study of seismic waves provides a complete picture of the layered interior. An earthquake, in simple words, is shaking of the earth. It is a natural event. It is caused due to the release of energy, which generates waves that travel in all directions. Why does the earth shake? The release of energy occurs along a fault. A fault is a sharp break in the crustal rocks. Rocks along a fault tend to move in opposite directions. As the overlying rock strata press them, the friction locks them together. However, their tendency to move apart at some point of time overcomes the friction. As a result, the blocks get deformed and eventually they slide past one another abruptly. This causes a release of energy, and the energy waves travel in all directions. The point where the energy is released is called the focus of an earthquake. Alternatively, it is called the hypocenter. The energy waves traveling in different directions reach the surface. The point on the surface nearest to the focus is called epicenter. It is the first one to experience the waves. It is the point directly above the focus. Earthquake waves. All natural earthquakes take place in the lithosphere. You will learn about different layers of the Earth later in this chapter. It is sufficient to note here that the lithosphere refers to the portion of depth up to 200 kilometers from the surface of the Earth. An instrument called seismograph records the waves reaching the surface. A curve of earthquake waves recorded on the seismograph is given in Figure 3.1. Note that the curve shows three distinct sections, each representing different types of wave patterns. Earthquake waves are basically of two types: body waves and surface waves. Body waves are generated due to the release of energy at the focus and move in all directions traveling through the body of the Earth, hence the name body waves. The body waves interact with the surface rocks and generate new set of waves called surface waves. These waves move along the surface. The velocity of waves changes as they travel through materials with different densities. The denser the material, the higher is the velocity. Their direction also changes as they reflect or refract when coming across materials with different densities. There are two types of body waves. They are called P and S waves. P waves move faster and are the first to arrive at the surface. These are also called primary waves. The P waves are similar to sound waves. They travel through gaseous, liquid, and solid materials. S waves arrive at the surface with some time lag. These are called secondary waves. An important fact about S waves is that they can travel only through solid materials. This characteristic of the S waves is quite important. It has helped scientists to understand the structure of the interior of the Earth. Reflections cause waves to rebound, whereas refraction makes waves move in different directions. The variations in the direction of waves are inferred with the help of their record on seismograph. The surface waves are the last to report on seismograph. These waves are more destructive. They cause displacement of rocks, and hence the collapse of structures occurs. Propagation of earthquake waves. Different types of earthquake waves travel in different manners. As they move or propagate, they cause vibration in the body of the rocks through which they pass. P waves vibrate parallel to the direction of the wave. This exerts pressure on the material in the direction of the propagation. As a result, it creates density differences in the material, leading to stretching and squeezing of the material. Other three waves vibrate perpendicular to the direction of propagation. The direction of vibrations on S waves is perpendicular to the wave direction in the vertical plane. Hence, they create troughs and crests in the material through which they pass. Surface waves are considered to be the most damaging waves. Emergence of shadow zone. Earthquake waves get recorded in seismographs located at far-off locations. However, there exist some specific areas where the waves are not reported. Such a zone is called the shadow zone. The study of different events revealed that for each earthquake, there exists an altogether different shadow zone. Figure 3.2 A and B show the shadow zones of P and S waves. It was observed that seismographs located at any distance within 105 degrees from the epicenter recorded the arrival of both P and S waves. However, the seismographs located beyond 145 degrees from epicenter record the arrival of P waves, but not that of S waves. Thus, a zone between 105 degrees and 145 degrees from epicenter was identified as the shadow zone for both the types of waves. The entire zone beyond 105 degrees does not receive S waves. The shadow zone of S wave is much larger than that of the P waves. The shadow zone of P waves appears as a band around the Earth between 105 degrees and 145 degrees away from the epicenter. The shadow zone of S waves is not only larger in extent, but it is also a little over 40% of the Earth's surface. You can draw the shadow zone for any earthquake, provided you know the location of the epicenter. See the activity box on page 28 to know how to locate the epicenter of a quake event. Types of earthquakes. 1. The most common ones are the tectonic earthquakes. These are generated due to sliding of rocks along a fault plane. 2. A special class of tectonic earthquake is sometimes recognized as volcanic earthquake. However, these are confined to areas of active volcanoes. 3. In the areas of intense mining activity, sometimes the roofs of underground mines collapse, causing minor tremors. These are called collapse earthquakes. 4. Ground shaking may also occur due to the explosion of chemical or nuclear devices. Such tremors are called explosion earthquakes. 5. The earthquakes that occur in the areas of large reservoirs are referred to as reservoir-induced earthquakes. Measuring earthquakes. The earthquake events are scaled either according to the magnitude or intensity of the shock. The magnitude scale is known as the Richter scale. The magnitude relates to the energy released during the quake. The magnitude is expressed in numbers, 0 to 10. The intensity scale is named after Mercalli, an Italian seismologist. The intensity scale takes into account the visible damage caused by the event. The range of intensity scale is from 1 to 12. Effects of earthquake. Earthquake is a natural hazard. The following are the immediate hazardous effects of earthquake. 1. Ground shaking. 2. Differential ground settlement. 3. Land and mudslides. 4. Soil liquefaction. Ground lurching. 6. Avalanches. 7. Ground displacement. 8. Floods from dam and levee failures. 9. Fires. 10. Structural collapse. 11. Falling objects. 12. Tsunami. The first 6 listed above have some bearings upon landforms, while others may be considered the effects causing immediate concern to life and properties of people in the region. The effect of tsunami would occur only if the epicenter of the tremor is below oceanic waters and the magnitude is sufficiently high. Tsunamis are waves generated by the tremors and not an earthquake in itself. Though the actual quake activity lasts for a few seconds, its effects are devastating, provided the magnitude of the quake is more than 5 on the Richter scale. Frequency of earthquake occurrences. The earthquake is a natural hazard. If a tremor of high magnitude takes place, it can cause heavy damage to the life and property of people. However, not all the parts of the globe necessarily experience major shocks. We shall be discussing the distribution of earthquakes and volcanoes with some details in the next chapter. Notice that the quakes of high magnitude, i.e. 8+, are quite rare. They occur once in 1 to 2 years, whereas those of tiny types occur almost every minute. Structure of the Earth. The crust. It is the outermost solid part of the Earth. It is brittle in nature. The thickness of the crust varies under the oceanic and continental areas. Oceanic crust is thinner as compared to the continental crust. The mean thickness of oceanic crust is 5 kilometers, whereas that of the continental is around 30 kilometers. The continental crust is thicker in the areas of major mountain systems. It is as much as 70 kilometers thick in the Himalayan region. It is made up of heavier rocks having density of 3 grams/centimeters. Oceanic crust is basalt. The mean density of material in oceanic crust is 2.7 grams per cubic centimeter. The mantle. The portion of the interior beyond the crust is called the mantle. The mantle extends from Moho's discontinuity to a depth of 2,900 kilometers. The upper portion of the mantle is called asthenosphere. The word astheno means weak. It is considered to be extending up to 400 kilometers. It is the main source of magma that finds its way to the surface during volcanic eruptions. It has a density higher than the crusts, 3.4 grams per cubic centimeter. The crust and the uppermost part of the mantle are called lithosphere. Its thickness ranges from 10 to 200 kilometers. The lowest mantle extends beyond the asthenosphere. It is in solid state. The core. As indicated earlier, the earthquake wave velocities helped in understanding the existence of the core of the Earth. The core mantle boundary is located at the depth of 2,900 kilometers. The outer core is in liquid state, while the inner core is in solid state. The density of material at the mantle core boundary is around 5 grams per cubic centimeter, and at the center of the Earth at 6,300 kilometers, the density value is around 13 grams per cubic centimeter. The core is made up of very heavy material, mostly constituted by nickel and iron. It is sometimes referred to as the knife layer. Volcanoes and volcanic landforms. You may have seen photographs or pictures of volcanoes on a number of occasions. A volcano is a place where gases, ashes, and/or molten rock material, lava, escape to the ground. A volcano is called an active volcano if the materials mentioned are being released or have been released out in the recent past. The layer below the solid crust is mantle. It has higher density than that of the crust. The mantle contains a weaker zone called asthenosphere. It is from this that the molten rock materials find their way to the surface. The material in the upper mantle portion is called magma. Once it starts moving towards the crust or it reaches the surface, it is referred to as lava. The material that reaches the ground includes lava flows, pyroclastic debris, volcanic bombs, ash and dust, and gases such as nitrogen compounds, sulfur compounds, and minor amounts of chlorine, hydrogen, and argon. Volcanoes. Volcanoes are classified on the basis of nature of eruption and the form developed at the surface. Major types of volcanoes are as follows. Shield volcanoes. Bearing the basalt flows, the shield volcanoes are the largest of all the volcanoes on the earth. The Hawaiian volcanoes are the most famous examples. These volcanoes are mostly made up of basalt, a type of lava that is very fluid when erupted. For this reason, these volcanoes are not steep. They become explosive if somehow water gets into the vent. Otherwise, they are characterized by low explosivity. The upcoming lava moves in the form of a fountain and throws out the cone at the top of the vent and develops into a cinder cone. Composite volcanoes. These volcanoes are characterized by eruptions of cooler and more viscous lava than basalt. These volcanoes often result in explosive eruptions. Along with lava, large quantities of pyroclastic material and ashes find their way to the ground. This material accumulates in the vicinity of the vent openings, leading to formation of layers, and this makes the mounts appear as composite volcanoes. Caldera. These are the most explosive of Earth's volcanoes. They are usually so explosive that when they erupt, they tend to collapse on themselves rather than building any tall structure. The collapsed depressions are called calderas. Their explosiveness indicates that the magma chamber supplying the lava is not only huge, but is also close in vicinity. Flood basalt provinces. These volcanoes outpour highly fluid lava that flows for long distances. Some parts of the world are covered by thousands of square kilometers of thick basalt lava flows. There can be a series of flows, with some flows attaining the thickness of more than 50 meters. Individual flows may extend for hundreds of kilometers. The Deccan Traps from India, presently covering most of the Maharashtra plateau, are a much larger flood basalt province. It is believed that initially the trap formations covered a much larger area than the present. Mid-ocean ridge volcanoes. These volcanoes occur in the oceanic areas. There is a system of mid-ocean ridges more than 70,000 kilometers long that stretches through all the ocean basins. The central portion of this ridge experiences frequent interruptions. We shall be discussing this in detail in the next chapter. Volcanic landforms. Intrusive forms. The lava that is released during volcanic eruptions on cooling develops into igneous rocks. The cooling may take place either on reaching the surface or also while the lava is still in the crustal portion. Depending on the location of the cooling of the lava, igneous rocks are classified as volcanic rocks, cooling at the surface, and plutonic rocks, cooling in the crust. The lava that cools within the crustal portions assumes 5 different forms. These forms are called intrusive forms. Some of the forms are shown in Figure 3.5. Batholiths. A large body of magmatic material that cools in the deeper depth of the crust develops in the form of large domes. They appear on the surface only after the denudational processes remove the overlying materials. They cover large areas and at times assume depth that may be several kilometers. These are granitic bodies. Batholiths are the cooled portion of magma chambers. Laccoliths. These are large dome-shaped intrusive bodies with a level base and connected by a pipe-like conduit from below. It resembles the surface volcanic domes of composite volcano. Only these are located at deeper depths. It can be regarded as the localized source of lava that finds its way to the surface. The Karnataka Plateau is spotted with domal hills of granite rocks. Most of these, now exfoliated, are examples of laccoliths or batholiths. Lapilith, faccolith, and sills. As and when the lava moves upwards, a portion of the same may tend to move in a horizontal direction wherever it finds a weak plane. It may get rested in different forms. In case it develops into a saucer shape, concave to the sky body, it is called lapilith. A wavy mass of intrusive rocks, at times, is found at the base of synclines or at the top of anticline in folded igneous country. Such wavy materials have a definite conduit to source beneath in the form of magma chambers, subsequently developed as batholiths. These are called the faccoliths. The near horizontal bodies of the intrusive igneous rock are called sill or sheet, depending on the thickness of the material. The thinner ones are called sheets, while the thick horizontal deposits are called sills. Dikes. When the lava makes its way through cracks and the fissures developed in the land, it solidifies almost perpendicular to the ground. It gets cooled in the same position to develop a wall-like structure. Such structures are called dikes. These are the most commonly found intrusive forms in the western Maharashtra area. These are considered the feeders for the eruptions that led to the development of the Deccan Traps. Exercises. Number 1. Multiple choice questions. 1. Which one of the following earthquake waves is more destructive? A. P waves, B. S waves, C. Surface waves, D. None of the above. Two. Which one of the following is a direct source of information about the interior of the Earth? A. Earthquake waves, B. Volcanoes, C. Gravitational force, D. Earth magnetism. Three. Which type of volcanic eruptions have caused Deccan Trap formations? A. Shield, B. Flood, C. Composite, D. Caldera. Four. Which one of the following describes the lithosphere? A. Upper and lower mantle, B. Crust and upper mantle, C. Crust and core, D. Mantle and core. Number 2. Answer the following questions in about 30 words. 1. What are body waves? 2. Name the direct sources of information about the interior of the Earth. 3. Why do earthquake waves develop shadow zone? 4. Briefly explain the indirect sources of information on the interior of the Earth other than those of seismic activity. Number 3. Answer the following questions in about 150 words. 1. What are the effects of propagation of earthquake waves on the rock mass through which they travel? 2. What do you understand by intrusive forms? Briefly describe various intrusive forms. Chapter 4. Distribution of Oceans and Continents. In the previous chapter, you studied the interior of the Earth. You are already familiar with the world map. You know that continents cover 29% of the surface of the Earth, and the remainder is under oceanic waters. The positions of the continents and the ocean bodies, as we see them in the map, have not been the same in the past. Moreover, it is now a well-accepted fact that oceans and continents will not continue to enjoy their present positions in times to come. If this is so, the question arises, what were their positions in the past? Why and how did they change their positions? Even if it is true that the continents and oceans have changed and are changing their positions, you may wonder as to how scientists know this. How have they determined their earlier positions? You will find the answers to some of these and related questions in this chapter. Continental drift. Observe the shape of the coastline of the Atlantic Ocean. You will be surprised by the symmetry of the coastlines on either side of the ocean. No wonder many scientists thought of this similarity and considered the possibility of the two Americas, Europe and Africa, to be once joined together. From the known records of the history of science, it was Abraham Ortelius, a Dutch mapmaker, who first proposed such a possibility as early as 1596. Antonio Pellegrini drew a map showing the three continents together. However, it was Alfred Wegener, a German meteorologist, who put forth a comprehensive argument in the form of the continental drift theory in 1912. This was regarding the distribution of the oceans and the continents. According to Wegener, all the continents formed a single continental mass, and a mega-ocean surrounded the same. The supercontinent was named Pangaea, which meant all earth. The mega-ocean was called Panthasaula, meaning all water. He argued that, around 200 million years ago, the supercontinent Pangaea began to split. Pangaea first broke into two large continental masses, as Laurasia and Gondwanaland forming the northern and southern components respectively. Subsequently, Laurasia and Gondwanaland continued to break into various smaller continents that exist today. A variety of evidence was offered in support of the continental drift. Some of these are given below. Evidence in support of the continental drift. The matching of continents. Jigsaw fit. The shorelines of Africa and South America facing each other have a remarkable and unmistakable match. It may be noted that a map produced using a computer program to find the best fit of the Atlantic margin was presented by Bullard in 1964. It proved to be quite perfect. The match was tried at 1,000 fathom line instead of the present shoreline. Rocks of same age across the oceans. The radiometric dating methods developed in the recent period have facilitated correlating the rock formation from different continents across the vast ocean. The belt of ancient rocks of 2,000 million years from Brazil coast matches those from Western Africa. The earliest marine deposits along the coastline of South America and Africa are of the Jurassic Age. This suggests that the ocean did not exist prior to that time. Tillite. It is a sedimentary rock formed out of deposits of glaciers. The Gondwana system of sediments from India is known to have its counterparts in 6 different land masses of the southern hemisphere. At the base, the system has thick tillite indicating extensive and prolonged glaciation. Counterparts of this succession are found in Africa, Falkland Island, Madagascar, Antarctica, and Australia. Overall resemblance of the Gondwana-type sediments clearly demonstrates that these land masses had remarkably similar histories. The glacial tillite provides unambiguous evidence of paleoclimates and also of drifting of continents. Placer deposits. The occurrence of rich placer deposits of gold in the Ghana coast and the absolute absence of source rock in the region is an amazing fact. The gold-bearing veins are in Brazil, and it is obvious that the gold deposits of the Ghana are derived from the Brazil Plateau when the two continents lay side by side. Distribution of fossils. When identical species of plants and animals adapted to living on land or in fresh water are found on either side of the marine barriers, a problem arises regarding accounting for such distribution. The observations that lemurs occur in India, Madagascar, and Africa led some to consider a contiguous landmass, Lemuria, linking these three landmasses. Mesosaurus was a small reptile adapted to shallow brackish water. The skeletons of these are found only in two localities, the southern Cape Province of South Africa and Iraver formations of Brazil. The two localities are presently 4,800 kilometers apart with an ocean in between them. Force for drifting. Wegener suggested that the movement responsible for the drifting of the continents was caused by pole fleeting force and tidal force. The polar fleeting force relates to the rotation of the Earth. You are aware of the fact that the Earth is not a perfect sphere. It has a bulge at the equator. This bulge is due to the rotation of the Earth. The second force that was suggested by Wegener, the tidal force, is due to the attraction of the moon and the sun that develops tides in oceanic waters. Wegener believed that these forces would become effective when applied over many million years. However, most of scholars consider these forces to be totally inadequate. Post-drift studies. It is interesting to note that for continental drift, most of the evidence was collected from the continental areas in the form of distribution of flora and fauna or deposits, like tillite. A number of discoveries during the post-World War II period added new information to geological literature. Particularly, the information collected from the ocean floor mapping provided new dimensions for the study of distribution of oceans and continents. Convectional current theory. Arthur Holmes in 1930s discussed the possibility of convection currents operating in the mantle portion. These currents are generated due to radioactive elements causing thermal differences in the mantle portion. Holmes argued that there exists a system of such currents in the entire mantle portion. This was an attempt to provide an explanation to the issue of force, on the basis of which contemporary scientists discarded the continental drift theory. Mapping of the ocean floor. Detailed research of the ocean configuration revealed that the ocean floor is not just a vast plain, but it is full of relief. Expeditions to map the oceanic floor in the post-World War II period provided a detailed picture of the ocean relief and indicated the existence of submerged mountain ranges as well as deep trenches, mostly located closer to the continent margins. The mid-oceanic ridges were found to be most active in terms of volcanic eruptions. The dating of the rocks from the oceanic crust revealed the fact that they are much younger than the continental areas. Rocks on either side of the crest of oceanic ridges and having equidistant location from the crest were found to have remarkable similarities both in terms of their constituents and their age. Ocean floor configuration. In this section, we shall note a few things related to the ocean floor configuration that help us in the understanding of the distribution of continents and oceans. You will be studying the details of ocean floor relief in Chapter 13. The ocean floor may be segmented into three major divisions based on the depth as well as the forms of relief. These divisions are continental margins, deep-sea basins, and mid-ocean ridges. Continental margins. These form the transition between continental shores and deep-sea basins. They include continental shelf, continental slope, continental rise, and deep oceanic trenches. Of these, the deep oceanic trenches are the areas which are of considerable interest in so far as the distribution of oceans and continents is concerned. Abyssal plains. These are extensive plains that lie between the continental margins and mid-ocean ridges. The abyssal plains are the areas where the continental sediments that move beyond the margins get deposited. Mid-oceanic ridges. This forms an interconnected chain of mountain system within the ocean. It is the longest mountain chain on the surface of the earth, though submerged under the oceanic waters. It is characterized by a central rift system at the crest, a fraction plateau and flank zone all along its length. The rift system at the crest is the zone of intense volcanic activity. In the previous chapter, you have been introduced to this type of volcanoes as mid-oceanic volcanoes. Distribution of earthquakes and volcanoes. Study the maps showing the distribution of seismic activity and volcanoes given in Figure 4.2. You will notice a line of dots in the central part of the Atlantic Ocean, almost parallel to the coastlines. It further extends into the Indian Ocean. It bifurcates a little south of the Indian subcontinent, with one branch moving into East Africa and the other meeting a similar line from Myanmar to New Guinea. You will notice that this line of dots coincides with the mid-oceanic ridges. The shaded belt showing another area of concentration coincides with the alpine Himalayan system and the rim of the Pacific Ocean. In general, the foci of the earthquake in the areas of mid-oceanic ridges are at shallow depths, whereas along the alpine Himalayan belt as well as the rim of the Pacific, the earthquakes are deep-seated ones. The map of volcanoes also shows a similar pattern. The rim of the Pacific is also called Rim of Fire due to the existence of active volcanoes in this area. Concept of seafloor spreading. As mentioned above, the post-drift studies provided considerable information that was not available at the time Wegener put forth his concept of continental drift. Particularly, the mapping of the ocean floor and paleomagnetic studies of rocks from oceanic regions revealed the following facts. 1. It was realized that all along the mid-oceanic ridges, volcanic eruptions are common and they bring huge amounts of lava to the surface in this area. 2. The rocks equidistant on either sides of the crest of mid-oceanic ridges show remarkable similarities in terms of period of formation, chemical compositions, and magnetic properties. Rocks closer to the mid-oceanic ridges have normal polarity and are the youngest. The age of the rocks increases as one moves away from the crest. 3. The ocean crust rocks are much younger than the continental rocks. The age of rocks in the oceanic crust is nowhere more than 200 million years old. Some of the continental rock formations are as old as 3,200 million years. 4. The sediments on the ocean floor are unexpectedly very thin. Scientists were expecting, if the ocean floors were as old as the continent, to have a complete sequence of sediments for a period of much longer duration. However, nowhere was a sediment column found to be older than 200 million years. 5. The deep trenches have deep-seated earthquake occurrences, while in the mid-oceanic ridge areas, the quake foci have shallow depths. These facts and a detailed analysis of magnetic properties of the rocks on either sides of the mid-oceanic ridge led Hess, 1961, to propose his hypothesis known as the sea floor spreading. Hess argued that constant eruptions at the crest of oceanic ridges caused the rupture of the oceanic crust and the new lava wedges into it, pushing the oceanic crust on either side. The ocean floor thus spreads. The younger age of the oceanic crust, as well as the fact that the spreading of one ocean does not cause the shrinking of the other, made Hess think about the consumption of the oceanic crust. He further maintained that the ocean floor gets pushed due to volcanic eruptions at the crest, sinks down at the oceanic trenches, and gets consumed. The basic concept of seafloor spreading has been depicted in Figure 4.3. Plate tectonics. Since the advent of the concept of seafloor spreading, the interest in the problem of distribution of oceans and continents was received. It was in 1967 Mackenzie and Parker, and also Morgan, independently collected the available ideas and came out with another concept termed plate tectonics. A tectonic plate, also called lithospheric plate, is a massive, irregularly shaped slab of solid rock, generally composed of both continental and oceanic lithosphere. Plates move horizontally over the asthenosphere as rigid units. The lithosphere includes the crust and top mantle, with its thickness range varying between 5 and 100 kilometers in oceanic parts, and about 200 kilometers in the continental areas. A plate may be referred to as the continental plate or oceanic plate, depending on which of the two occupy a larger portion of the plate. Pacific Plate is largely an oceanic plate, whereas the Eurasian Plate may be called a continental plate. The theory of plate tectonics proposed that the Earth's lithosphere is divided into 7 major and some minor plates. Young fold mountain ridges, trenches, and/or faults surround these major plates. Figure 4.5. The major plates are as follows. 1. Antarctica and the surrounding oceanic plate. 2. North American, with western Atlantic floor separated from the South American plate along the Caribbean islands, plate. 3. South American, with western Atlantic floor separated from the North American plate along the Caribbean islands, plate. 4. Pacific plate. 5. India, Australia, New Zealand plate. 6. Africa with the eastern Atlantic floor plate. 7. Eurasia and the adjacent oceanic plate. Some important minor plates are listed below. 1. Cocos plate, between Central America and Pacific plate. 2. Nazca plate, between South America and Pacific plate. 3. Arabian plate, mostly Saudi Arabian landmass. 4. Philippine plate, between the Asiatic and Pacific plate. 5. Caroline plate, between the Philippine and Indian plate, north of New Guinea. 6. Fuji plate, northeast of Australia. These plates have been constantly moving over the globe throughout the history of the Earth. It is not the continent that moves as believed by Wegener. Continents are part of a plate, and what moves in the plate. Moreover, it may be noted that all the plates, without exception, have moved in the geological past and shall continue to move in the future as well. Wegener had thought of all the continents to have initially existed as a supercontinent in the form of Pangaea. However, later discoveries revealed that the continental masses resting on the plates have been wandering all through the geological period, and Pangaea was a result of converging of different continental masses that were parts of one or the other plates. Scientists using the paleomagnetic data have determined the positions held by each of the present continental landmass in different geological periods. Figure 4.4. Position of the Indian subcontinent, mostly peninsular India, is traced with the help of rocks analyzed from the Nagpur area. There are 3 types of plate boundaries. Divergent boundaries, where new crust is generated as the plates pull away from each other. The sites where the plates move away from each other are called spreading sites. The best known example of divergent boundaries is the Mid-Atlantic Ridge. At this, the American plates is/are separated from the Eurasian and African plates. Convergent boundaries, where the crust is destroyed as one plate dived under another, the location where sinking of a plate occurs is called a subduction zone. There are 3 ways in which convergence can occur. There are 1. Between an oceanic and continental plate, 2. Between 2 oceanic plates, and 3. Between 2 continental plates. Transform boundaries, where the crust is neither produced nor destroyed as the plates slide horizontally past each other. Transform faults are the planes of separation generally perpendicular to the mid-oceanic ridges. As eruptions do not take all along the entire crust at the same time, there is a differential movement of a portion of the plate away from the axis of the Earth. Also, the rotation of the Earth has its effect on the separated blocks of the plate portions. How do you think the rate of plate movement is determined? Rates of plate movement. The strips of normal and reverse magnetic field that parallel the mid-oceanic ridges help scientists determine the rates of plate movement. These rates vary considerably. The Arctic ridge has the slowest rate, less than 2.5 centimeters per yard, and the East Pacific rise near Easter Island in the South Pacific about 3,400 kilometers west of Chile has the fastest rate, more than 15 centimeters per year. Force for the plate movement. At the time that Wegener proposed his theory of continental drift, most scientists believed that the Earth was a solid, motionless body. However, concepts of seafloor spreading and the unified theory of plate tectonics have emphasized that both the surface of the Earth and the interior are not static and motionless, but are dynamic. The fact that the plates move is now a well-accepted fact. The mobile rock beneath the rigid plates is believed to be moving in a circular manner. The heated material rises to the surface, spreads, and begins to cool, and then sinks back into deeper depths. This cycle is repeated over and over to generate what scientists call a convection cell or convective flow. Heat within the Earth comes from two main sources, radioactive decay and residual heat. Arthur Holmes first considered this idea in the 1930s, which later influenced Harry Hess's thinking about seafloor spreading. The slow movement of hot, softened mantle that lies below the rigid plates is the driving force behind the plate movement. Movement of the Indian Plate. The Indian Plate includes peninsular India and the Australian continental portions. The subduction zone along the Himalayas form the northern plate boundary in the form of continent-continent convergence. In the east, it extends through Rakhine Mountains of Myanmar towards the island arc along the Java Trench. The eastern margin is a spreading site lying to the east of Australia in the form of an oceanic ridge in SW Pacific. The western margin follows Kirtar Mountain of Pakistan. It further extends along the Makrana coast and joins the spreading site from the Red Sea Rift southeastward along the Chagos Archipelago. The boundary between India and the Antarctic plate is also marked by oceanic ridge, divergent boundary, running in roughly WE direction and merging into the spreading site a little south of New Zealand. India was a large island situated off the Australian coast in a vast ocean. The Tethys Sea separated it from the Asian continent till about 225 million years ago. India is supposed to have started her northward journey about 200 million years ago, at the same time when Pangaea broke. India collided with Asia about 40 to 50 million years ago, causing rapid uplift of the Himalayas. The positions of India since about 71 million years till the present are shown in the figure 4.6. It also shows the position of the Indian subcontinent and the Eurasian plate. About 140 million years before the present, the subcontinent was located as south as 50 degrees south latitude. The two major plates were separated by the Tethys Sea, and the Tibetan block was closer to the Atlantic landmass. During the movement of the Indian plate towards the Eurasian plate, a major event that occurred was the outpouring of lava and formation of the Deccan Traps. This started somewhere around 60 million years ago and continued for a long period of time. Note that the subcontinent was still close to the equator. From 40 million years ago and thereafter, the event of formation of the Himalayas took place. Exercises. Number 1. Multiple choice questions. 1. Who amongst the following was the first to consider the possibility of Europe, Africa, and America having been located side by side? A. Alfred Wegener. B. Antonio Pellegrini. C. Abraham Ortelius. D. Edmund Hess. Two. Polar fleeing force relates to A. Revolution of the Earth. B. Gravitation. C. Rotation of the Earth. D. Tides. 3. Which one of the following is not a minor plate? A. Nazca. B. Arabia. C. Philippines. D. Antarctica. 4. Which one of the following facts was not considered by those while discussing the concept of seafloor spreading? A. Volcanic activity along the mid-oceanic ridges. B. Stripes of normal and reverse magnetic field observed in rocks of ocean floor. C. Distribution of fossils in different continents. D. Age of rocks from the ocean floor. 5. Which one of the following is the type of plate boundary of the Indian plate along the Himalayan mountains? A. Ocean-continent convergence. B. Divergent boundary. C. Transform boundary. D. Continent-continent convergence. Number 2. Answer the following questions in about 30 words. 1. What were the forces suggested by Wegener for the movement of the continents? 2. How were the convectional currents in the mantle initiated and maintained? 3. What is the major difference between the transform boundary and the convergent or divergent boundaries of plates? 4. What was the location of the Indian landmass during the formation of the Deccan Traps? 3. Answer the following questions in about 150 words. 1. What are the evidences in support of the continental drift theory? 2. Bring about the basic difference between the drift theory and plate tectonics. 3. What were the major post-drift discoveries that rejuvenated the interest of scientists in the study of distribution of oceans and continents? Project work. Prepare a collage related to damages caused by an earthquake.
Unit 3 Landforms. This unit deals with rocks and minerals, major types of rocks and their characteristics, landforms and their evolution, geomorphic process, weathering, mass, wasting, erosion and deposition, soils formation. Chapter 5 Minerals and Rocks. The Earth is composed of various kinds of elements. These elements are in solid form in the outer layer of the Earth and in hot and molten form in the interior. About 98% of the total crust of the Earth is composed of 8 elements like oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. Table 5.1. And the rest is constituted by titanium, hydrogen, phosphorus, manganese, sulfur, carbon, nickel, and other elements. The elements in the Earth's crust are rarely found exclusively, but not usually combined with the other elements to make various substances. These substances are recognized as minerals. Thus, a mineral is a natural occurring organic and inorganic substance, having an orderly atomic structure and a definite chemical composition and physical properties. A mineral is composed of 2 or more elements, but sometimes single element minerals like sulfur, copper, silver, gold, graphite, etc. are found. Though the number of elements making up the lithosphere are limited, they are combined in many different ways to make up many varieties of minerals. There are at least 2,000 minerals that have been named and identified in the Earth's crust. but almost all the commonly occurring ones are related to 6 major mineral groups that are known as major rock-forming minerals. The basic source of all minerals is the hot magma in the interior of the earth. When the magma cools, crystals and minerals appear and systematic series of minerals are found in the sequence to solidify so as to form rocks. Minerals such as coal, petroleum, and natural gas are organic substances found in solid, liquid, and gaseous forms, respectively. A brief information about some important minerals in the term of their nature and physical characteristics is given below. Physical characteristics. External crystal form. Determined by internal arrangement of the molecules, cubes, octahedrons, hexagonal prisms, etc. 2. Cleavage, tendency to break in given directions, producing relatively plane surfaces, result of internal arrangement of the molecules. May cleave in one or more directions and at any angle to each other. 3. Fracture. Internal molecular arrangement is complex. There are no planes of molecules. The crystal will break into an irregular manner, not along planes of cleavage. 4. Luster. Appearance of the material without regard to color. Each mineral has a distinctive luster like metallic, silky, glossy, etc. 5. Color. Some minerals have characteristics color determined by their molecular structure, malachite, azurite, chalcopyrite, etc. And some minerals are colored by impurities. For example, because the impurities, quartz may be white, green, yellow, red, etc. Streak. Color of the ground powder of any mineral. It may be of the same color as the mineral or may differ. Malachite is green and gives green streak. Fluorite is purple or green but gives a white streak. 7. Transparency. Transparent. Light rays pass through so that objects can see plainly. Translucent. Light rays pass through but will get diffused so the objects cannot be seen. Opaque. Light will not pass at all. 8. Structure. Particular arrangement of the individual crystals. Fine, medium, or coarse-grained. Fibrous, separable, divergent, radiating. 9. Hardness. Relative resistance. Being scratched, 10 minerals are selected to measure the degree of hardness from 1 to 10. They are 1. Talc, 2. Gypsum, 3. Calcite, 4. Fluorite, 5. Apatite, 6. Feldspar, 7. Quartz, 8. Topaz, 9. Conundrum, 10. Diamond. Compared to this, for example, a fingernail is 2.5 and glass or knife blade is 5.5. 10. Specific gravity. The ratio between the weight of the given object and the weight of an equal volume of water. Object weighed in air and then weighed in water, and divided weight in air by difference of the two weights. Some major minerals and their characteristics. Feldspar. Silicon and oxygen are common elements in all types of feldspar, and sodium, potassium, calcium, aluminum, etc. are found in specific feldspar variety. Half of the Earth's crust is composed of feldspar. It has light cream to salmon pink color. It is used in ceramics and glass making. Quartz. It is one of the most important components of sand and granite. It consists of silica. It is a hard mineral virtually insoluble in water. It is white or colorless and used in radio and radar. It is one of the most important components of granite. Ferroxene. Ferroxene consists of calcium, aluminum, magnesium, iron, and silica. Ferroxene forms 10% of the Earth's crust. It is commonly found in meteorites. It is in green or black color. Amphibole. Aluminum, calcium, silica, iron, magnesium are the main elements of amphiboles. They form 7% of the Earth's crust. It is in green or black color and is used to asbestos industry. Hornblende is another form of amphiboles. Mica. It comprises of potassium, aluminum, magnesium, iron, silica, etc. It forms 4% of the Earth's crust. It is commonly found in the igneous and metamorphic rocks. It is used in electrical instruments. Olivine. Magnesium, iron, and silica are major elements of olivine. It is used in jewelry. It is usually a greenish crystal often found in basaltic rocks. Beside these main minerals, other minerals like chlorite, calcite, magnite, hematite, bauxite, and baryte are also present in some quantities in the rocks. Metallic minerals. These minerals contain metal content and can be subdivided into 3 types. 1. Precious metals, gold, silver, platinum, etc. 2. Ferrous metals. Iron and other metals often mix with iron to form various kinds of steel. 3. Non-ferrous metals include metals like copper, lead, zinc, tin, aluminum, etc. Non-metallic minerals. These minerals do not contain metal content. Sulfur, phosphates, and nitrates are examples of non-metallic minerals. Cement is a mixture of non-metallic minerals. Rocks. The Earth's crust is composed of rocks. A rock is an aggregate of one or more minerals. Rock can be hard or soft and in varied colors. For example, granite is hard, soapstone is soft. Gabbro is black, and quartzite can be milky white. Rocks do not have definite composition of mineral constitutes. Feldspar and quartz are the most common minerals found in rocks. Petrology is science of rocks. A petrologist studies rocks in all their aspects, viz. Mineral composition, texture, structure, origin, occurrence, alteration, and relationship with other rocks. As there is a close relation between rocks and landforms, rocks and soil, a geographer requires basic knowledge of rocks. There are many different kinds of rocks which are not grouped under the 3 families on the basis of their mode formation. They are 1. Igneous rock, solidified from magma and lava. 2. Sedimentary rocks, the result of the deposition of fragments of rocks by exogenous process. 3. Metamorphic rock, formed out by existing rocks undergoing recrystallization. Igneous rock. As igneous rocks form out of magma and lava from the interior of the earth, they are known as primary rocks. The igneous rocks, ignis in Latin means fire, are formed when magma cools and solidifies. You already know what magma is. When magma in its upward movement cools and turns into solid form, it is called igneous rock. The process of cooling and solidification can happen in the Earth's crust or on the surface of the Earth. Igneous rocks are classified based on texture. Texture depends upon size and arrangement of grains or other physical conditions of the materials. If molten material is cooled slowly at great depths, mineral grains may be very large. Sudden cooling at the surface results in small and smooth grains. Intermediate conditions of cooling would result in intermediate sizes of grains, making up igneous rocks. Granite, gabbro, pegmite, basalt, volcanic breccia, and tuff are some of the examples of igneous rock. Sedimentary rocks. The word sedimentary is derived from the Latin word sedimentum, which means settling. Rocks, igneous, sedimentary, and metamorphic, of the Earth's surface are exposed to denudatial agents and are broken up into various sizes of fragments. Such fragments are transported by different exogenous agencies and deposited. These deposits, through compaction, turn into rock. This process is called lithification. In many sedimentary rocks, the layers of deposits retain their characters even after lithification. Hence, we see a number of layers of varying thickness in sedimentary rocks like sandstone, shale, etc. Depending upon the mode of formation, sedimentary rocks are classified into three major groups. 1. Mechanically formed sandstone, conglomerate, limestone, shale, loess, etc. are examples. 2. Organically formed Jassite, chalk, limestone, coal, etc. are some examples. 3. Chemical formed chert, limestone, halite, potash, etc. are some examples. Metamorphic rocks. The word metamorphic means change of form. These rocks from under the action of pressure, volume, and temperature, PVT, changes. Metamorphism occurs when rocks are forced down to lower levels by tectonic processes or when molten magma rising through the crust comes in contact with the crustal rocks, or the underlying rocks are subjected to the great amounts of pressure by overlying rocks. Metamorphism is a process by which already consolidated rocks undergo recrystallization and reorganization of materials within original rocks. Mechanical disruption and reorganization of the original minerals within rocks due to breaking and crushing without any appreciable chemical changes is called dynamic metamorphism. The materials of rocks chemically altered and recrystallized due to thermal metamorphism. There are two types of thermal metamorphism: contact metamorphism and regional metamorphism. In contact metamorphism, the rocks come in contact with hot, intruding magma and lava, and the rock materials recrystallize under high temperatures. Quite often, new materials form out of magma or lava are added to the rocks. In regional metamorphism, rocks undergo recrystallization due to deformation caused by tectonic shearing together with high temperature or pressure or both. In the process of metamorphism, in some rocks, grains or minerals get arranged in layers or lines. Such an arrangement of minerals or grains in metamorphic rocks is called foliation or lineation. Sometimes minerals or materials of different groups are arranged into alternating thin to thick layers appearing in light and dark shades. Such a structure in metamorphic rocks is called banding, and rocks displaying banding are called banded rocks. Types of metamorphic rocks depend upon original rocks that were subjected to metamorphism. Metamorphic rocks are classified into two major groups: foliated rocks and non-foliated rocks. Nesoid, granite, syenite, slate, schist, marble, quartzite, etc. are some examples of metamorphic rocks. Rock cycle. Rocks do not remain in their original form for long, but may undergo transformation. Rock cycle is a continuous process through which old rocks are transformed into new ones. Igneous rocks are primary rocks, and other rocks, sedimentary and metamorphic, form from these primary rocks. Igneous rocks can be changed into metamorphic rocks. The fragments derived out of the igneous and metamorphic rocks form into sedimentary rocks. Sedimentary rocks themselves can turn into fragments, and the fragments can be a source of formation of sedimentary rocks. The crustal rocks, igneous, metamorphic, and sedimentary, once formed, may be carried down into the mantle, interior of the earth. Through subduction process, parts or whole of crustal plates going down under another plate in zones and plate convergence. And the same melt down due to increase the temperature in the interior and turn into molten magma, the original source for the igneous rock.
Exercises. Question 1. Multiple choice questions. Bit 1. Which one of the following are the two main constituents of granite? A. Iron and nickel. B. Iron and silver. C. Silica and aluminium. D. Iron oxide and potassium. Bit 2. Which one of the following is the salient feature of metamorphic rocks? A. Changeable. B. Quiet. C. Crystalline. D. Foliation. Bit 3. Which one of the following is not a single element mineral? A. Gold. B. Silver. C. Mica or mica. D. Graphite. 4. Which one of the following is the hardest mineral? A. Topaz. B. Diamond. C. Quartz. D. Feldspar. Bit 5. Which one of the following is not a sedimentary rock? A. Tillite. B. Borax. C. Breccia. D. Marble. Number 2. Answer the following questions in about 30 words. Bit 1. What do you mean by rocks? Name the 3 major classes of rocks. Bit 2. What is an igneous rock? Describe the method of formation and characteristics of igneous rock. Bit 3. What is meant by sedimentary rock? Describe the mode of formation of sedimentary rock. Bit 4. What relationship explained by rock cycle between the major type of rock? 3. Answer the following questions in about 150 words. Bit 1. Define the term mineral and name the major classes of minerals with their physical characteristics. Bit 2. Describe the nature and mode of origin of the chief type of rocks at the Earth's crust. How will you distinguish them? Bit 3. What are metamorphic rocks? Describe the types of metamorphic rock and how they are formed. Project work. Collect different rock samples and try to recognize them from their physical characteristics and identify their family.
Chapter 6: Geomorphic Process. After learning about how the Earth was born, how it evolved its crust and other inner layers, how its crustal plates moved and are moving, and other information on earthquakes, the forms of volcanism, and about the rocks and minerals the crust is composed of, it is time to know in detail about the surface of the Earth on which we live. Let us start with this question: why is the surface of the Earth uneven? The Earth's crust is dynamic. You are all very well aware that it is moved and moves vertically and horizontally. Of course, it moved a bit faster in the past than the rate at which it is moving now. The differences in the internal forces operating from within the Earth which build up the crust have been responsible for the variations of the outer surface of the crust. The Earth's surface is being continuously subjected in internal forces induced basically by energy, sunlight. Of course, the internal forces are still active, though, with different intensities. That means the Earth's surface is being continuously subjected to by the external forces originating within the Earth's atmosphere and by internal forces from within the Earth. The external forces are known for exogenic forces, and the internal forces are known as endogenic forces. The actions of the exogenic forces result in wearing down, degradation of relief elevations, and filling up aggradation of basins, depression, on the Earth's surface. The phenomenon of wearing down of relief variations of the surface of the Earth through erosion is known gradation. The endogenic forces continuously elevate or build up parts of the Earth's surface, and hence the exogenic processes fail to even out of the relief variations of the surface of the Earth. So, variations remain as long as the opposing actions of exogenic and endogenic forces continue. In general terms, the endogenic forces are mainly land-building forces, and the exogenic process are mainly land-wearing forces. The surface of the Earth is sensitive. Humans depend on it for their sustenance and have been using it extensively and intensely. So it is essential to understand its nature in order to use it effectively without disturbing its balance and diminishing its potential for the future. Almost all organisms contribute to sustain the Earth's environment. However, humans have caused extensive damage to the environment through overuse of resources. Use we must, but must also leave it potential enough to sustain life through the future. Most of the surface of the Earth had and has been shaped over very long periods of time, hundreds and thousands of years, and because of its use and misuse by humans, its potential is being diminished at a fast rate. If the processes which shaped and are shaping the surface of the Earth into varieties of forms, shapes, and the nature of materials of which it is composed of are understood, precautions can be taken to minimize the detrimental effects of human use and preserve it for posterity. Geomorphic process. You would like to know the meaning of the geomorphic process, the endogenic and exogenic forces causing physical stresses and chemical actions on Earth materials, and bringing about changes in the configuration of the surface of the Earth are known as geomorphic processes. Diastrophism and volcanism are endogenic geomorphic processes. These have already been discussed in brief in the preceding unit. Weathering, mass, wasting, erosion, and deposition are exogenic geomorphic processes. These exogenic processes are dealt with in detail in this chapter. Any exogenic element of nature, like water, ice, wind, etc., capable of acquiring and transporting earth materials, can be called a geomorphic agent. When these elements of nature become mobile due to gradients, they remove the materials and transport them over slopes and deposit them at lower level. Geomorphic processes and geomorphic agents, especially exogenic, unless stated separately, are one and the same. A process is a force applied on earth materials affecting the same. An agent is a mobile medium, like running water, moving ice masses, wind, waves, and currents, etc., which removes, transports, and deposits earth materials. Running water, groundwater, glaciers, wind, waves, and currents can be called geomorphic agents. Do you think it's essential to distinguish geomorphic agents and geomorphic processes? Gravity, besides being a directional force, also causes stress on the Earth's materials. Indirect gravitational stresses activate wave and tide-induced currents and wind. Without gravity and gradients, there would be no mobility and hence no erosion, transportation, and deposition are possible. So gravitational stresses are as important as the other geomorphic processes. Gravity is the force that is keeping us in contact with the surface, and it is the force that switches on the momentum of all surface material on Earth. All the movements, either within the Earth or on the surface of the Earth, occur due to gradients from higher levels to lower levels, from high pressure to low pressure areas. Endogenic processes. The energy emanating from within the Earth is the main force behind endogenic geomorphic processes. This energy is mostly generated by radioactive, rotational, and tidal friction and primordial heat from the origin of the Earth. This energy, due to geothermal gradients and heat flow from within, induces diastrophism and volcanism in the lithosphere. Due to variations in the geothermal gradients and heat flow from within crustal thickness and strength, the action of endogenic forces are not uniform, and hence the tectonically controlled original crustal surface is uneven. Diastrophism. All processes that move, elevate, or build up portions of the Earth's crust come under diastrophism. They include 1. Orogenic processes involving mountain building through severe folding and affecting long and narrow belts of the Earth's crust. 2. Epeirogenic processes involving uplift or warping of large parts of the Earth's crust. Number 3. Earthquakes involving local relatively minor movements. Number 4. Plate tectonics involving horizontal movements of the crustal plates. In the process of orogeny, the crust is severely deformed into folds. Due to epeirogeny, there may be simple deformation. Orogeny is a mountain building process, whereas epeirogeny is continental building process. Through the process of orogeny, epeirogeny, earthquakes, and plate tectonics, there can be faulting and fracturing in the crust. All these processes cause pressure, volume, and temperature, PVT, changes which in turn induce metamorphism of rocks. Epiorogeny and orogeny cite the differences. Volcanism. Volcanism includes the movement of molten rock, magma, onto or toward the Earth's surface, and also formation of many intrusive and extrusive volcanic forms. Many aspects of volcanic have already been dealt in detail under volcanoes in the Unit 2 and under igneous rocks in the preceding chapter in this unit. What do the words volcanism and volcanoes indicate? Exogenic processes. The exogenic processes derive their energy from atmosphere determined by the ultimate energy from the sun and also the gradients created by tectonic factors. Why do you think that the slopes or gradients are created by tectonic factors? Gravitational force acts upon all Earth materials having a sloping surface and tend to produce movement of matter in downslope direction. Force applied per unit area is called stress. Stress is produced in a solid by pushing or pulling. This induces deformation. Forces acting along the faces of Earth materials are shear stress. Separating forces. It is this stress that breaks rocks and other Earth materials. The shear stresses result in angular displacement or slippage. Besides the gravitational stress, Earth materials become subjected to molecular stresses that may be caused by a number of factors, amongst which temperature changes, crystallization, and melting are the most common. Chemical processes normally lead to loosening of bonds between grains, dissolving the soluble minerals or cementing materials. Thus, the basic reason that leads to weathering, mass movements, and erosion is development of stresses in the body of the Earth materials. Temperature and precipitation are the two most important climatic elements that control various processes. All the exogenic geomorphic processes are covered under a general term, denudation. The word denude means to strip off or to uncover. Weathering, mass wasting movements, erosion, and transportation are included in the denudation. The flowchart figure 6.1 gives the denudation process and their respective driving forces. It should become clear that this chart that for each process there exists a distinctive driving force or energy. As there are different climatic regions owing to variations in thermal gradients created by latitude, seasonal, and land and water spread on the surface of the Earth, and the exogenic geomorphic processes vary from region to region. The density, type, and distribution of the vegetation, which largely depend upon precipitation and temperature, also exert influence indirectly on exogenic geomorphic processes. Within different climatic regions, there may be local variations of the effects of different climatic elements due to altitudinal differences, aspect variations, and the variation in the amount of insolation received by north and south facing slopes, as compared to east and west facing slopes. Further, due to differences in wind velocities and directions, amount of kind of precipitation, its intensity, the relation between precipitation and evaporation, daily range of temperature, freezing and thawing frequency, depth of frost penetration. The geomorphic processes vary within any climatic region. What is the sole driving force behind all the exogenic processes? Climatic factors being equal, the intensity of action of exogenic geomorphic processes depend upon type and structure of rocks. The term structure includes such aspects of rocks as folds, faults, orientation, and inclination of beds, presence or absence of joints, bedding planes, hardness or softness of constituent minerals, chemical susceptible of mineral constitutes, the permeable or impermeability, etc. Different types of rocks with differences in their structure offer varying resistances to various geomorphic processes. A particular rock may be resistant to one process and non-resistant to another. And under varying climatic conditions, particular rocks may exhibit many degrees of resistance to geomorphic processes, and hence they operate at different rates and give rise to differences in topography. The effects of most of the exogenic geomorphic processes are small and slow, and may be imperceptible in a short time span, but will in the long run affect the rock severely due to continued fatigue. Finally, it boils down to one fact that the differences on the surface of the Earth, though originally related to the crustal evolution, continue to exist in some form or other due to differences in the type and structure of Earth materials, differences in geomorphic processes and in their rates of operation. Some of the exogenic geomorphic processes have been dealt in detail here. Weathering. Weathering is action amid elements of weather and climate over other Earth materials. There are a number of processes within weathering, which act either individually or together to affect the Earth materials in order to reduce them to fragmental state. Weathering is defined as the mechanical disintegration and chemical decomposition of rocks through the actions of various elements of weather and climate. As very little or no motion of materials takes place in weathering, it is an institute or on-site process. In this little motion, which can occur sometimes due to weathering synonyms with transportation, if not why. Weathering processes are conditioned by many complex geological, climatic, topographic, and vegetative factors. Climate is of particular importance. Not only weathering processes differ from climate to climate, but also the depth of weathering mantle. Figure 6. There are three major groups of weathering processes. 1. Chemical, 2. Physical or mechanical, and 3. Biological weathering processes. Very rarely does any one of these processes ever operate completely by itself, but quite often a dominance of one process can be seen. Chemical weathering processes. A group of weathering processes, viz. Solution, carbonation, hydration, oxidation, and reduction, act on the rocks to decompose, dissolve, or reduce them to a fine clastic state through chemical reactions by oxygen. Surface and or soil, water, and other acids, water and air, oxygen and carbon dioxide, along with heat must be represented to speed up all chemical reactions. Over and above the carbon dioxide present in the air, decomposition of plants and animals increase the quantity of carbon dioxide underground. These chemical reactions on various minerals are very much similar to chemical reactions in laboratory. Solution. When something is dissolved in water or acids, the water or acid with dissolved contents is called solution. The process involves removal of soils in solution and depends upon solubility of mineral in water or weak acids. On coming in contact with water, many solids disintegrate and mix up as suspension in water. Soluble rock-forming minerals like nitrates, sulfates, and potassium, etc., are affected by this process. So these minerals are easily leached out without leaving any residue in rainy climates and accumulate in dry regions. Minerals like calcium carbonate and calcium magnesium bicarbonate represent in limestones are soluble in water containing carbonic acid formed with the addition of carbon dioxide and water, and are carried away in water as solution. Carbon dioxide produced by decaying organic matter along with soil water greatly aids in this reaction. Common salt, sodium chloride, is also a rock-forming mineral and is susceptible to this process of solution. Carbonation. Carbonation is the reaction of carbonate and bicarbonate with minerals and is a common process helping the breaking down of feldspars and carbonate minerals. Carbon dioxide from the atmosphere and soil air is absorbed by water to form carbonic acid that acts a weak acid. Calcium carbonates and magnesium carbonates are dissolved in carbon acid and are removed in a solution without leaving any residue, resulting in cave formation. Hydration. Hydration is the chemical addition of water. Minerals take up water and expand. This expansion causes an increase in the volume of the material itself, or rock. Calcium sulfate takes in water and turns to gypsum, which is more unstable than calcium sulfate. This process is reversible and long. Continued repetition of this process causes fatigue in the rocks and may lead to their disintegration. Many clay minerals swell and contract during wetting and drying, and repetition of this process results in cracking of overlying materials. Salts and pore spaces undergo rapid and repeated hydration and help in rock fracturing. The volume changes in minerals due to hydration will also help in physical weathering through exfoliation and granular disintegration. Oxidation and reduction. In weathering, oxidation means a combination of mineral with oxygen to form oxides or hydroxides. Oxidation occurs when there is ready access to the atmosphere in oxygenated waters. In minerals, most commonly involved in this process are iron, manganese, sulfur, etc. In the process of oxidation, rock breakdown occurs due to the disturbance caused by addition of oxygen. Red color of iron upon oxidation turns to brown or yellow. When oxidized minerals are placed in an environment where oxygen is absent, reduction takes place. Such conditions exist usually below the water table, in areas of stagnant water and waterlogged ground. Red color of iron upon reduction turns to greenish or bluish green. These weathering processes are interrelated. Hydration, carbonation, and oxidation go hand in hand in hastening the weathering process. Can we give iron rusting as an example of oxidation? How essential is water in chemical weathering processes? Can chemical weathering processes dominate in water-scarce hot deserts? Physical weathering processes. Physical or chemical weathering processes depend on some applied forces. The applied forces could be 1. Gravitational forces such as overburden pressure, load and shearing stress. 2. Expansion forces due to temperature changes, crystal growth or animal activity. 3. Water pressures controlled by wetting and drying cycles. Many of these forms are applied both at the surface and within different earth materials, leading to rock fracture. Most of the physical weathering processes are caused by thermal expansion and pressure release. These processes are low and slow, but can cause great damage to the rocks because of continued fatigue. The rocks suffer due to repetition of contraction and expansion. Unloading and expansion. Removal of overlying rocks load because of continued erosion causes vertical pressure. Release with the result that the upper layers of the rock expand, producing disintegration of rock masses. Fracture will develop roughly parallel to the ground level surface. In areas of curved ground surface, arched fractures tend to produce massive sheets or exfoliation slabs of rock. Exfoliation sheets resulting from expansion due to unloading and pressure release may measure hundreds or even thousands of meters in horizontal extent. Large, smooth, rounded domes called exfoliation domes, figure 6.3, result due to this process. Temperature changes and expansion. Various minerals and rocks possesses their own limits of expansion and contraction. With rising temperature, every mineral expands and pushes against its neighbor, and as temperature falls, a corresponding contraction takes place. Because of diurnal changes in the temperature, this internal movement among the mineral grains of the superficial layers of rocks takes place regularly. This process is most effective in dry climates and high elevations where diurnal temperatures changes are drastic. As has been mentioned earlier, through these movements are very small. They make the rocks weak due to continued fatigue. The surface layers of the rocks tend to expand more than the rock at depth, and this leads to the formation of stress within the rocks, resulting in heavy and fracturing parallel to the surface. Due to differential heating and resulting expansion, the contraction of surface layers and their subsequent exfoliation from the surface results in smooth, rounded surfaces in rocks. In rocks like granites, smooth-surfaced and rounded small to big boulders called tores form due to such exfoliation. What is the difference between exfoliation domes and exfoliated tores? Freezing, thawing, and frost wedging. Frost weathering occurs due to growth of ice within pores and cracks of rocks during repeated cycles of freezing and melting. This process is most effective at high elevations in mid-latitudes where freezing and melting is often repeated. Glacial areas are subject to frost and wedging daily. In this process, the rate of freezing is important. Rapid freezing of air causes its sudden expansion and high pressure. The resulting expansion affects joints, cracks, and small intergranular fractures to become wider and wider till the rock breaks apart. Salt weathering. Salts in rocks expand due to thermal action, hydration, and crystallization. Many salts like calcium, sodium, magnesium, potassium, and barium have a tendency to expand. Expansion of these salts depends on temperature and the thermal properties. High temperature ranges between 30 and 50 degrees Celsius of surface temperature in deserts favor such salt expansion. Salt crystals in near-surface pores cause splitting of individual grains within rocks, which eventually fall off. This process of falling off individual grains may result in granular disintegration of granular foliation. Salt crystallization is most effective of all salt weathering processes. In areas with alternating wetting and drying conditions, salt crystal growth is favored and neighboring grains are pushed aside. Sodium chloride and gypsum crystals in desert areas have heaven up overlying layers of materials, with the result polygonal cracks develop all over the heaven surface. With salt crystal growth, chalk breaks down most readily, followed by limestone, sandstone, shale, gneiss, and granite. Biological activity and weathering. Biological weathering is contribution to or removal of minerals and ions from the weathering environment and physical changes due to growth or movement of organisms. Burrowing and wedging of organisms like earthworms, termites, rodents, etc. help in exposing the new surfaces to chemical attack and assistance. And the penetration of moisture and air. Human beings, by disturbing vegetation, plowing and cultivating soils, also help in mixing and creating new context between air, water, and minerals in the earth materials. Decaying plant and animal matter help in the production of humic, carbonic, and other acids which enhance decay and solubility of some elements. Plant roots exert a tremendous pressure on the earth materials mechanically, breaking them apart. Special effects of weathering. Exfoliation. This has already been explained under physical weathering processes of unloading, thermal contraction and expansion, and salt weathering. Exfoliation is a result, but not a process. Flaking off of more or less curved sheets of shells from over rocks or bedrock results in smooth and rounded surfaces. Exfoliation can occur due to expansion and contraction induced by temperature changes. Exfoliation domes and tores result due to loading and thermal expansion respectively. Significance of weathering. Weathering processes are responsible for breaking down the rocks into smaller fragments and preparing the way for formation of not only regolith and soils, but also erosion and mass movements. Biomes and biodiversity is basically a result of forest vegetation, and forests depend upon the depth of weathering mantles. Erosion cannot be significant if the rocks are not weathered. That means weathering aids mass wasting. Erosion and reduction of relief and changes in landforms are consequence of erosion. Weathering of rocks and deposition helps in the enrichment and concentrations of certain valuable ores of iron, manganese, aluminum, copper, etc., which are of great importance for the national economy. Weathering is an important process in formation of soils. When rocks undergo weathering, some materials are removed through chemical or physical leaching by underground water, and thereby the concentration of remaining valuable materials increases. Without such a weathering taking place, the concentration of the same valuable material may not be sufficient and economically viable to exploit, process, and refine. This is what is called enrichment. Mass movements. These movements transfer the mass of rock debris down the slopes under the direct influence of gravity. That means air, water, or ice do not carry debris with them from place to place, but on the other hand, the debris may carry with it air, water, or ice. The movements of mass may range from slow to rapid, affecting shallow to deep columns of materials, and include creep, flow, slide, and fall. Gravity exerts its force on all matter, both bedrock and products of weathering. So weathering is not a prerequisite for mass movement, though it aids mass movements. Mass movements are very attractive over weathered slopes rather than over unweathered materials. Mass movements are aided by gravity and no geomorphic agent like running water. Glaciers, wind, waves, and currents participate in the process of mass movements. That means mass movements do not come under erosion, though there are a shift, aided by gravity, of materials from one place to another. Materials over the slopes have their own resistance to disturbing forces and will yield only when force is greater than the shearing resistance of materials. Weak, unconsolidated materials, thinly bedded rocks, faults, steeply dipping beds, vertical cliffs or steep slopes, abundant precipitation, and torrential rains and scarcity of vegetation, etc. favor mass movements. Several activating causes precede mass movements. They are 1. Removal of support from below to materials above through natural or artificial means. 2. Increasing gradient and height of slopes. 3. Overloading through addition of materials naturally or by artificial filling. 4. Overloading due to heavy rainfall, saturation, and lubrication of slope materials. 5. Removal of materials or load from over the original slope surfaces. 6. Occurrence of earthquakes, explosions, or machinery. 7. Excessive natural seepage. 8. Heavy drawdown of water from lakes, reservoirs, and rivers, leading to slow outflow of water from under the slopes or riverbanks. 9. Indiscriminate removal of natural vegetation. Heave. Heaving up the soils due to frost, growth, and other causes. Flow and slide are the 3 forms of movements. Figure 6.5 shows the relationships among different types of mass movements, the relative rates of movement, and moisture limits. Mass movements can be grouped under 2 major classes: slow movements and rapid movements. Slow movements. Creep is one type of under this category, which can occur on moderately steep soil-covered slopes. Movement of materials is extremely slow and imperceptible except through extended observation. Materials involved can be soil or rock debris. Have you ever seen fence posts, telephone poles lean downslope from their vertical position and in their linear alignment? If you have, that is due to the creep effect. Depending upon the type of material involved, several types of creep, viz., soil creep, talus creep, rock glacier creep, etc., can be identified. Also included in the group is solidification, which involves slowed down slopes following soil mass or fine-grained rock debris, saturated or lubricated with water. This process is quite common in most temperate areas where surface melting is of deeply frozen ground and long continued rain respectively occurred frequently. When the upper portions get saturated and when the lower parts are impervious to water percolation, flowing occurs in the upper parts. Rapid movements. These movements are mostly prevalent in humid climatic regions and occur over gentle to steep slopes. Movement of water-saturated, clayey, or silty earth materials down low-angled terraces or hillsides is known as earth flow. Quite often, the materials slump, making step-like terraces and leaving arcuate scarps at their heads and an accumulation bulge at the toe. When slopes are steeper, when the bedrock, especially of soft sedimentary rocks like shale or deeply weathered igneous rock, may slide downslope. Another type in this category is mudflow. In the absence of vegetation cover and with heavy rainfall, thick layers of weathered materials get saturated with water and either slow or rapidly flow down along definite channels. It looks like a stream of mud within a valley. When the mud flows emerge out of a channel onto the Piedmont or plains, they can be very destructive, engulfing roads, bridges, and houses. Mudflows occur frequently on the slopes in erupting or recently erupted volcanoes. Volcanic ash, dust, and other fragments turn into mud due to heavy rains and flow down as tongues or streams of mud, causing great destruction to human habitations. The third type is the debris avalanche, which is more characteristic of human regions with or without vegetation cover and occurs in narrow tracts on steep slopes. This debris avalanche can be much faster than the mudflow. Debris avalanche is similar to snow avalanche. In Andes Mountains of South America and the Rockies Mountains of North America, there are a few volcanoes which erupted during the last decade, and very devastating mudflows occurred down their slopes during eruption as well as after eruption. Landslides. These are relatively rapid and perceptible movements. The materials involved are relatively dry. The size and shape of the detached mass depends on the nature of discontinuities in the rock, the degree of weathering, and the steepness of slope. Depending upon the type of movement of materials, several types are identified in this category. Slump is slipping off one or several units of rock debris with a backward rotation with respect to the slope over which the movement takes place, figure 6.6. Rapid rolling or sliding of earth debris without backward rotation of mass is known as debris slide. Debris fall is nearly a free fall of earth debris from a vertical or overchanging face. Sliding of individual rock masses down bedding, joint, or fault surfaces is rock slide. Over steep slopes, rock sliding is very fast and destructive. Figure 6.7 shows landslide scars over steep slopes. Slides occur as planar failures along discontinuities, like bedding planes that dip steeply. Rockfall is free falling of rock blocks over any steep slope, keeping itself away from the slope. Rock falls occur from the superficial layers of the rock phase, an occurrence that distinguishes it from rockslide, which affects material up to a substantial depth. Between mass wasting and mass movements, which term do you feel is most appropriate? Why? Can solution be included under rapid flow movements? Why it can be seen and can't be. In our country, debris avalanches and landslides occur very frequently in Himalayas. There are many reasons for this. 1. The Himalayas are tectonically active. They are mostly made up of sedimentary rocks and unconsolidated and semi-consolidated deposits. The slopes are very steep. Compared to the Himalayas, the Nilgiris bordering Tamil Nadu, Karnataka, Kerala, and the Western Ghats along the west coast are relatively tectonically stable and are mostly made up of very hard rocks. But still, debris avalanches and landslides occur, though not as frequently as in the Himalayas, in the hills. Why? Many slopes are steeper with almost vertical cliffs and escarpments in the western Ghats and Nilgiris. Mechanical weathering due to temperature changes and ranges is pronounced. They received heavy amounts of rainfall over short periods, so there is almost direct rock fall quite frequently in those places, along with landslides and debris avalanches. Erosion and deposition. Erosion involves acquisition and transportation of rock debris. When massive rocks break into smaller fragments through weathering and any other process, erosional geomorphic agents like running water, groundwater, glaciers, wind, and waves remove and transport it to other places depending upon the dynamics of each of these agents. Abrasion of rock debris carried by these geomorphic agents also aids greatly in erosion. By erosion, relief degrades, i.e., the landscape is worn down. That means, though weathering aids erosion, it is not a precondition for erosion to take place. Weathering, mass wasting, and erosion are degradational processes. It is erosion that is largely responsible for continuous changes that the Earth's surface is undergoing. As indicated in Figure 6.1, denudational processes like erosion and transportation are controlled by kinetic energy. The erosion and transportation of earth materials is brought about by wind, running water, glaciers, waves, and groundwater. Of these first three agents are controlled by climatic conditions. They represent three states of matter: gaseous, wind, liquid, running water, and solid glacier respectively. Can you compare the three climatically controlled agents? The erosion can be defined as application of the kinetic energy associated with the agent to the surface of the land along which it moves. Kinetic energy is computed as Ke equals half mv squared, where m is the mass and v is the velocity. Hence, the energy available to perform work will depend on the mass of the material and the velocity with which it is moving. Obviously, then you will find the glaciers move at very low velocities due to tremendous mass are more effective as the agents of erosion, and wind, being gaseous state, is less effective. The work of the other two agents of erosion, waves, and groundwater is not controlled by climate. In case of waves, it is the location along the interface of litho and hydrosphere, coastal region, that will determine the work of waves, whereas the work of groundwater is determined more by the lithological character of the region. If the rocks are permeable and soluble and water is available only, then the karst topography develops. In the next chapter, we shall be dealing with the landforms produced by each of these agents of erosion. Deposition is consequence of erosion. The erosional agents lose their velocity and hence energy on gentler slopes, and the materials carried by them start to settle themselves. In the other words, deposition is not actually the work of any agent. The coarser materials get deposited first and finer ones later. By deposition, depression get filled up. The same erosion agents, viz., running water, glaciers, wind, waves, and groundwater, act as aggradational or depositional agents also. What happens to the surface of Earth due to the erosion and deposition is elaborated in the next chapter on landforms and their evolution. There is a shift of materials and mass movements as well as an erosion from one place to another. So, why can't both be treated as one and the same? Can there be appreciable erosion without rocks undergoing weathering? Soil formation, soil and soil contents. You see plants growing in soils. You play in the ground and come into contact with soil. You touch and feel soil and soil your clothes while playing. Can you describe it? A pedologist who studies soil defines soil as a collection of nature's natural bodies of the Earth's surface containing living and or dead matter and support or capable of supporting plants. Soil is a dynamic medium in which many chemical, physical, and biological activities go on constantly. Soil is a result of decay. It is also the medium for growth. It is a changing and developing body. It has many characteristics that fluctuate with the seasons. It may be alternatively cold and warm or dry and moist. Biological activity is slowed or stopped if the soil becomes too cold or too dry. Organic matter increases when the leaves fall or grasses die. The soil chemistry, the amount of organic matter, the soil flora and fauna, the temperature and moisture all exchange with the seasons as well as with more extended periods of time. That means soil becomes adjusted to conditions of climate, landform, and vegetation, and will change entirely when these controlling conditions change. Process of soil formation. Soil formation or pedogenesis depends first on weathering. It is the weathering mantle depth of the weathered material which is basic input for soil to form. First, the weathered material or transported deposits are colonized by bacteria and other inferior plant bodies like mosses and lichens. Also, several minor organisms may take shelter within the mantle and deposits. The dead remains of organisms. The plants help in humus accumulations. Minor grasses and ferns may grow. Later, bushes and trees will start growing through seeds brought in by birds and wind. Plant roots penetrate down, burrowing animals, bringing up particles. Mass of material becomes porous and sponge-like with a capacity to retain water and to permit the passage of air, and finally a mature soil. A complex mixture of mineral and organic products forms. Is weathering solely responsible for soil formation? If not, why? Pedology is soil science. A pedologist is a soil scientist. Soil forming factors. 5 basic factors control the formation of soils. 1. Parent material. 2. Topography. 3. Climate. 4. Biological activity. 5. Time. In fact, soil-forming factors act in union and affect the action of one another. Parent material. Parent material is a passive control factor in soil formation. Parent materials can be in any in situ or on-site weathered rock debris, residual soils, or transported deposits, transported soils. Soil formation depends upon the texture, size of debris, and structure, disposition of individual grains, particles of debris, as well as the mineral and chemical composition of the rock debris deposits. Nature and rate of weathering and depth of weathering mantle are important considerations under parent materials. There may be differences in soil over similar bedrock, and dissimilar rocks may have similar soils above them. But when soils are very young and have not matured, these show strong links with the type of parent rock. Also, in cases some limestone areas where the weathering processes are specific and peculiar, soils will show clear relation with the parent rock. Topography. Topography, like parent materials, is another passive control factor. The influence of topography is felt through the amount of exposure of a surface covered by parent materials to sunlight and the amount of surface and subsurface drainage over and through the parent materials. Soils will be thin on steep slopes and thick over flat upland areas. Over gentle slopes where erosion is slow and percolation of water is good, soil formation is very favorable. Soils over flat areas may develop a thick layer of clay with good accumulation of organic matter, giving the soil dark color. In middle latitudes, the south-facing slopes exposed to sunlight have different conditions of vegetation and soils, and the north-facing slopes with cool, moist conditions have some other soils and vegetation. Climate. Climate is an important active factor in soil formation. The climatic elements involved in soil development are 1. Moisture in terms of its intensity, frequency, and duration of precipitation, evaporation and humidity. 2. Temperature in terms of seasonal and diurnal variations. Precipitation gives soil its moisture content, which makes the chemical and biological activities possible. Excess of water helps in the downward transportation of soil components through the soil, elevation, and deposits the same down below, elevation. In climates like wet, equatorial, rainy areas with high rainfall, not only calcium, sodium, magnesium, potassium, etc., but also a major part of silica is removed from the soil. Removal of silica from the soil is known as desiccation in dry climates because of high temperature. Evaporation exceeds precipitation, and hence groundwater is brought up to the surface by capillary action, and in the process of water evaporates, leaving behind salt in the soil. Such salts form into a crust in the soil known as hardpans. In tropical climates, in areas intermediate precipitation conditions, calcium carbonate noodles cracker are formed. Temperature acts in two ways: increasing or reducing chemical and biological activity. Chemical activity is increased in higher temperatures, reduced in cooler temperatures, with an exception of carbonation, and stops in freezing conditions. That is why tropical soils with higher temperatures show deeper profiles, and in the frozen tundra regions, soils contain inherently mechanically broken materials. Biological activity. The vegetative cover and organisms that occupy the parent materials from the beginning and also at later stages help in adding organic material, moisture retention, nitrogen, etc. Dead plants provide humus, the finely divided organic matter of the soil. Some organic acids, which form during humidification, aid in decomposing the minerals of the soil parent materials. Intensity of bacterial activity shows up differences between soils in cold and warm climates. Humus accumulates in cold climates as bacterial growth is slow, with undercomposed organic matter because of low bacterial activity. Layers of peat developed in subarctic and tundra climates. In humid tropical and equatorial climates, bacterial growth and action is intense, and dead vegetation is rapidly oxidized, leaving very low humus content in the soil. Further, bacteria and other soil organisms take gaseous nitrogen from the air and convert it into a chemical form that can be used by plants. This process is known as nitrogen fixation. Rhizobium, a type of bacteria, lives in the root noodles of leguminous plants and fixes nitrogen beneficial to the host plant. The influence of large animals like ants, termites, earthworms, rodents, etc. is mechanical, but it is nevertheless important in soil formation as they rework the soil up and down. In case the earthworms, as they feed on soil, the texture and chemistry of soil that comes out of their body exchanges. Time. Time is the third important controlling factor in soil formation. The length of time the soil forming processes operate determines maturation of soils and profile development. A soil becomes mature when all soil forming processes act for a sufficiently long time, developing a profile. Soils developing from recently deposited alluvium or glacial till are considered young, and they exhibit no horizons or only poorly developed horizons. No specific length of time in absolute terms can be fixed for soils to develop and mature.
Is it necessary to separate the process of soil formation and the soil forming control factors? Why are time, topography, and parent material considered as passive control factors in soil formation? Exercises. Number 1. Multiple choice questions. Bit 1. Which one of the following processes is a graduational process? A. Deposition. B. Diastrophism. C. Volcanism. D. Erosion. Bit 2. Which one of the following materials is affected by hydration process? A. Granite. B. Clay. C. Quartz. D. Salts. Bit 3. Debris avalanche can be induced in the category of A. Landslides. B. Slow flow mass movements. C. Rapid flow mass movements. D. Subsidence. 2. Answer the following questions in about 30 words. Bit 1. It is weathering that is responsible for biodiversity on the earth. How? Bit 2. What are mass movements that are real, rapid, and perceptible? List. Bit 3. What are the various mobile and mighty exogenic geomorphic agents and what is the prime job they perform? Bit 4. Is weathering essential as a prerequisite in the formation of soils? Why? 3. Answer the following questions in about 150 words. Bit 1. Our Earth is a playfield for two opposing groups of geomorphic processes. Discuss. Bit 2. Exogenic geomorphic processes derive their ultimate energy from the sun's heat. Explain. Bit 3. Are physical and chemical weathering processes independent of each other? If not, why? Explain with examples. Bit 4. How do you distinguish between the process of soil formation and soil forming factors? What is the role of climate and biological activity as two important control factors in the formation of soils? Project work. Depending upon the topography and materials around you, observe and record climate, possible weathering process, and soil contents and characteristics.
Chapter 7: Landforms and Their Evolution. After weathering processes have had their actions on the earth materials making up the surface of the earth, the geomorphic agents like running water, groundwater, wind, glaciers, waves perform erosion. It is already known to you that erosion causes changes on the surface of the earth. Deposition follows erosion, and because of deposition too, changes occur on the surface of the earth. As this chapter deals with landforms and their evolution, first start with the question, what is a landform? In simple words, small to medium tracts or parcels of the Earth's surface are called landforms. If landform is a small to medium-sized part of the surface of the Earth, what is a landscape? Several related landforms together make up landscapes, large tracts of Earth's surface. Each landform has its own physical shape, size, materials, and is a result of the action of certain geomorphic processes and agents. Actions of most of the geomorphic processes and agents are slow, and hence the results take a long time to take shape. Every landform has a beginning. Landforms, once formed, may change in their shape, size, and nature slowly or fast due to continued action of geomorphic processes and agents. Due to changes in climatic conditions and vertical or horizontal movements of land masses, either the intensity of processes or the processes themselves might change, leading to new modifications in the landforms. Evolution here implies stages to transformation of either a part of the Earth's surface from one landform into another, or transformation of individual landforms after they are once formed. That means each and every landform has a history of development and changes through time. A landmass passes through stages of development somewhat comparable to the stages of life: youth, mature, and old age. What are the two important aspects of the evolution of landforms? The evolutionary history of the continually changing surface of the earth is essential to be understood in order to use it effectively without disturbing its balance and diminishing its potential for the future. Geomorphology deals with the reconstruction of the history of the surface of the earth through a study of its forms, the materials of which it is made up of, and the processes that shape it. Changes on the surface of the earth owe mostly to erosion by various geomorphic agents. Of course, the process of deposition too, by covering the land surfaces and filling the basins, valleys, or depressions, brings changes in the surface of the land. Deposition follows erosion, and the depositional surface too are ultimately subjected to erosion. Running water, groundwater, glaciers, wind, and waves are powerful erosional and depositional agents shaping and changing the surface of the earth, aided by weathering and mass wasting processes. These geomorphic agents, acting over long periods of time, produce systematic changes, leading to sequential development of landforms. Each geomorphic agent produces its own assemblage of landforms. Not only does each geomorphic process and agent leave their distinct imprints on the landforms they produce. You know that most of the geomorphic processes are imperceptible functions that and can only be seen and measured through their results. What are the results? These results are nothing but landforms and their characteristics. Hence, a study of landforms will reveal to us the process and agent which has made or been making those landforms. Most of the geomorphic processes are imperceptible. Cite a few processes which can be seen and a few which can't be seen. As the geomorphic agents are capable of erosion and deposition, two sets, erosional or destructional and depositional or constructional, of landforms are produced by them. Many varieties of landforms develop by the action of each of the geomorphic agents, depending upon especially the type and structure, i.e., folds, faults, joints, fractures, hardness and softness, permeability and impermeability, etc. There are some other independent controls like 1. Stability of sea level, 2. Tectonic stability of land masses, and 3. Climate, which influence the evolution of landforms. Any disturbance in any of these 3 controlling factors can upset the systematic and sequential stages in the development and evolution of landforms. In the following pages, under each of the geomorphic regimes, i.e., running water, groundwater, glaciers, waves, and winds, first a brief discussion is presented as to how land masses are reduced in their relief through erosion, and then development of some of the erosional and depositional landforms is dealt with. Running water. In humid regions which receive heavy rainfall, running water is considered the most important of the geomorphic agents in bringing about the degradation of the land surface. There are 2 components of running water. One is overland flow on general land surface as a sheet. Another is linear flow as a streams and rivers and valleys. Most of the erosional landforms made by running water are associated with vigorous and youthful rivers flowing over steep gradients. With time, stream channels over steep gradients turn gentler due to continued erosion and, as a consequence, lose their velocity, facilitating active deposition. There may be depositional forms associated with streams following over steep slopes, but these phenomena will be on a small scale compared to those associated with rivers flowing over medium to gentle slopes. The gentler the river channels in gradient or slope, the greater is the deposition. When the stream beds turn gentler due to continued erosion, downward cutting becomes less dominant and later erosion of banks increases, and as a consequence, the hills and valleys are reduced to plains. Is complete reduction of relief of a high landmass possible? Overland flow causes sheet erosion. Depending upon irregularities of the land surface, the overland flow may concentrate into narrow to wide paths. Because of shear friction of the column of flowing water, minor or majority quantities of materials from the surface of the land are removed in the direction of flow, and gradually small and narrow rills will form. These rills will gradually develop into long and wide gullies. The gullies will further deepen, widen, lengthen, and unite to give rise to a network of valleys. In the early stages, down-cutting dominates during which irregularities such as waterfalls and cascades will be removed. In the middle stages, streams cut their beds slower, and lateral erosion of valley sides becomes severe. Gradually, the valley sides are reduced to lower and lower slopes. The divides between drainage basins are likewise lowered until they are almost complete, flattened, leaving finally a lowland of faint relief with some low resistance remains, called monadnocks, standing out here and there. This type of plain forming as a result of stream erosion is called peneplain and almost plain. The characteristics of each of the stages of landscapes developing in running water regimes may be summarized as follows. Youth. Streams are few during this stage with poor interrogation and flow over original slopes, showing shallow V-shaped valleys with no floodplains or with very narrow floodplains along trunk streams. Streams divides are broad and flat with marshes, swamp, and lakes. Meanders if present, develop over these broad upland surfaces. These meanders may eventually entrench themselves into the uplands. Waterfalls and rapids may exist where local hard rock bodies are exposed. Mature. This stage streams are plenty with good integration. The valleys are still V-shaped but deep. Trunk streams are broad enough to have wider floodplains within which streams may flow in meanderings confined within the valley. The flat and broad interstream areas and swamps and marshes of youth disappear, and the stream divides turn sharp. Waterfalls and rapids disappear. Old. Smaller tributaries during old age are few with gentle gradients. Streams meander freely over vast floodplains, showing natural levees, oxbow lakes, etc. Divides are broad and flat with lakes, swamps, and marshes. Most of the landscape is at or slightly above sea level. Erosional landforms. Valleys. Valleys start as small and narrow rills. The rills will gradually develop into long and wide gullies. The gullies will further deepen, widen, and lengthen to give rise to valleys, depending upon dimension and shape. Many types of valleys, like V-shaped valley, gorge, canyon, etc., can be recognized. A gorge is a deep valley with very steep to straight sides, figure 7.1, and a canyon is characterized by steep step-like side slopes, figure 7.2, and may be as deep as a gorge. A gorge is almost equal in width at its top as well as its bottom. In contrast, a canyon is wider at its top than at its bottom. In fact, a canyon is a variant of gorge. Valley types depend upon the type and structure of rocks in which they form. For example, canyons commonly form in horizontal bedded sedimentary rocks and gorges form in hard rocks. Potholes and plunge pools. Over the rocky bends of hill streams, more or less circular depressions called potholes form because of stream erosion aided by the abrasion of rock fragments. Once a small and shallow depression forms, pebbles and boulders get collected in those depressions and get rotated by flowing water, and consequently the depressions grow in dimensions. A series of such depressions eventually join and the stream valley gets deepened. At the foot of waterfalls also, large potholes, quite deep and wide, form because of the sheer impact of water and rotation of boulders. Such large and deep holes at the base of waterfalls are called plunge pools. These pools also help in the deepening of valleys. Waterfalls are also transitory like any other landform and will recede gradually and bring the floor of the valley above waterfalls to the level below. Incised and entrenched meanders. In streams that flow rapidly over steep gradients, normally erosion is concentrated on the bottom of the stream channel. Also, in the case of steep gradient streams, lateral erosion on the sides of the valleys is not much when compared to the streams flowing on low and gentle slopes. Because of active lateral erosion, streams flowing over gentle slopes develop sinuous or meandering courses. It is common to find meandering courses over floodplains and delta plains where stream gradients are very gentle. But very deep and wide meanders can also be found cut in hard rocks. Such meanders are called incised or entrenched meanders. Figure 7.2. Meander loops develop over original gentle surfaces in the initial stages of development of streams, and the same loops get entrenched into the rocks normally due to erosion or slow continued uplift of the land over which they start. They widen and deepen over time and can be found as deep gorges and canyons in hard rock areas. They give an indication on the status of original land surfaces over which streams have developed. What are the differences between incised meanders and meanders over flood and delta plains? River terraces. River terraces are surfaces marking old valley floor or floodplain levels. They may be bedrock surfaces without any alluvial cover or alluvial terraces consisting of stream deposits. River terraces are basically products of erosion as they result due to vertical erosion by the stream into its own depositional floodplain. There can be a number of such terraces at different heights indicating former riverbed levels. The river terraces may occur at the same elevation on either side of the rivers, in which case they are called paired terraces. Figure 7.3. When a terrace is present only on one side of the stream and with none on the other side, or one at quite a different elevation on the other side, the terraces are called unpaired terraces. Unpaired terraces are typical in areas of slow uplift of land or where the water column changes are not uniform along both the banks. The terraces may result due to 1. Receding water after a peak flow, 2. Changing in hydraulical regime due to climatic changes, 3. Tectonic uplift of land, 4. Sea level changes in case of river closer to the sea. Depositional landforms. Alluvial fans, figure 7.4, are formed when streams flowing from higher levels break into foot slope plains of low gradient. Normally, very coarse load is carried by streams flowing over mountain slopes. This load becomes too heavy for the streams to be carried over gentler gradients and gets dumped and spread as a broad low to high cone-shaped deposit called alluvial fan. Usually, the streams which flow over fans are not confined to their original channels for long and shift their position across the fan, forming many channels called distributaries. Alluvial fans is humid areas shown normally low cones with gentle slope from head to toe, and they appear as high cones with steep slope in arid and semi-arid climates. Deltas. Deltas are like alluvial fans but developed at a different location. The load carried by the rivers is dumped and spread into the sea. If this load is not carried away far into the sea or distributed along the coast, it spreads and accumulates as a low cone. Unlike in alluvial fans, the deposits making up deltas are very well sorted, with clear stratification. The coarsest materials settle out first and the finer fractions like slits and clays are carried out into the sea. As the delta grows, the river distributaries continue to increase in length, figure 7.5, and delta continues to build up into the sea. Floodplains, natural levees, and point bars. Deposition develops a floodplain just as erosion makes valleys. Floodplain is a major landform of river deposition. Large-sized materials are deposited first when stream channel breaks into a gentle slope. Thus, normally fine-sized materials like sand, slit, and clay are carried by relatively slow-moving waters in gentler channels, usually found in the plains, and deposited over the bed, and when the waters spill over the banks during flooding above the bed. A river bed made of river deposits is the active floodplain. The floodplain above the bank is inactive floodplain. Inactive floodplain above the banks basically contain two types of deposits: flood deposits and channel deposits. In plains, channels shift laterally and change their courses occasionally, leaving cut-off courses which get filled up gradually. Such areas over floodplains built up by abandoned or cut-off channels contain coarse deposits. The flood deposits of spilled waters carry relatively finer materials like slit and clay. The flood plains in the delta are called delta plains. Natural levees and point bars, figure 7.6, are some of the important landforms found associated with floodplains. Natural levees are found along the banks of large rivers. They are low, linear, and parallel ridges of coarse deposits along the banks of rivers, quite often cut into individual mounds. During flooding, as the water spills over the bank, the velocity of the water comes down and large-sized and high specific gravity materials get dumped in the immediate vicinity of bank as ridges. They are high near the banks and slope gently away from the river. The levee deposits are coarser than the deposits spread by flood waters away from the river. When rivers shift laterally, a series of natural levees can form. Point bars are also known as mender bars. They are found on the concave side of menders of large rivers and are sediments deposited in a linear fashion by flowing waters along the bank. They are almost uniform in profile and in width and contain mixed sizes of sediments. If there is more than one ridge, narrow and elongated depressions are found in between the point bars. Rivers build a series of them depending upon the water flow and supply of sediment. As the rivers build the point bars on the concave side, the bank on the convex side will erode actively. In which way do natural levees differ from point bars? Menders. In large flood and delta plains, rivers rarely flow in straight courses. Loop-like channel patterns called menders develop over flood and delta plains, figure 7.7. Mender is not a landform, but is only a type of channel pattern. This is because of 1. Propensity of water flowing over very gentle gradients to work laterally on the banks. 2. Unconsolidated nature of alluvial deposits making up the banks with many irregularities, which can be used by water exerting pressure laterally. 3. Coriolis force acting on the fluid water, deflecting it like it deflects the wind. When the gradient of the channel becomes extremely low, water flows leisurely and starts working laterally. Slight irregularities along the bank slowly get transformed into small curvated into the banks. The curvature depends due to deposition on the inside of the curve and erosion along the bank on the outside. If there is no deposition and no erosion or undercutting, the tendency is to mender is reduced. Normally, in menders of large rivers, there is active deposition along the concave bank and undercutting along the convex bank. The concave bank is known as a cutoff bank, which shows up as a steep scarp, and the convex bank presents a low, gentle profile, figure 7.8. As menders grow into deep loops, the same way may get cut off due to erosion at the inflection points and are left as oxbow lakes. Braided channels. When rivers carry coarse material, there can be selective deposition of coarser materials, causing formation of central bar, which diverts the flow towards the banks, and this flow increases lateral erosion on the banks. As the valley widens, the water column is reduced and more materials get deposited as islands and lateral bars, developing a number of separated channels of water flowing. Deposition and lateral erosion of banks are essential for the formation of braided pattern, or alternatively, when the discharge is less and load is more in the valley. Channel bars and islands of sand, gravel, and pebbles develop on the floor of the channel, and the water flow is divided into multiple threads. These thread-like streams of water rejoin and subdivide repeatedly to give a typical braided pattern. Figure 7.9. Groundwater. Here, the interest is not groundwater as a resource. Our focus is on the work of groundwater in the erosion of land masses and evolution of landforms. The surface water percolates well when the rocks are permeable, thinly bedded, and highly jointed and cracked. After vertically going down some depth, the water under the ground flows horizontally through the bedding plants, joints, or through the materials themselves. It is a downward and horizontal movement of water which causes the rocks to erode. Physical or mechanical removal of materials by moving groundwater is insignificant in developing landforms. That is why the results of work of groundwater cannot be seen in all types of rocks, but in rocks like limestones or dolomites rich in calcium carbonate, the surface water as well as groundwater through the chemical process of solution and precipitation, deposition develop varieties of landforms. These two processes of solution and precipitation are active in limestones or dolomites, occurring either exclusively or interbedded with other rocks. Any limestone or dolomitic region showing typical landforms produced by the action of groundwater through the process of solution and deposition is called karst topography. After the typical topography developed in limestone, rocks of karst region in the Balkans adjacent to Adriatic Sea. The karst topography is also characterized by erosional and depositional landforms. Erosional landforms: pools, sinkholes, lapides, and limestone pavements. Small to medium-sized round to sub-rounded shallow depressions called swallow holes from on the surface on limestones through solution. Sinkholes are very common in limestone karst areas. A sinkhole is an opening more or less circular at the top and funnel-shaped towards the bottom, with sizes varying in area from a few square meters to a hectare, and with depth from a less than half a meter to 30 meters or more. Some of these form solely through solution action, solution sinks, and others might start as solution forms first, and at the bottom of a sinkhole forms the roof of a void or cave underground, it might collapse, leaving a large hole opening in a cave or a void below a collapsed sink. Quite often, sinkholes are covered up with soil mantle and appear as shallow water pools. Anybody stepping over such pools would go down like it happens in quicksands in deserts. The term doline is sometimes used to refer to collapsed sinks. Solution sinks are more common than collapsed sinks. Quite often, the surface run of simply goes down swallow and sinkholes and flow as underground streams and re-emerge at a distance downstream through a cave opening. When sinkholes and dolines join together because the slumping of materials along their margins or due to roof collapse of caves, long narrow to wide trenches called valley sinks or uvulaes form. Gradually, most of the surface of limestone is eaten away by these pits and trenches, leaving it extremely irregular with a maze of points, grooves, and ridges or lapes. Especially these ridges or lapes form due to differential solution activity along parallel to subparallel joints. The lappy field may eventually turn into somewhat smooth limestone pavements. Caves. In areas where there are alternating beds of rocks, shale sandstones, quartzes with limestones, or dolomites in between, or in areas with limestones are dense, massive, and occurring as thick beds. Cave formation is prominent. Water percolates down either through the materials or through cracks and joints and moves horizontally along bedding planes. It is along these bedding planes that the limestone dissolves in long and narrow to wide gaps, called caves. Result. There can be a maze of caves at different elevations depending upon the limestone beds and intervening rocks. Caves normally have an opening through which cave streams are discharged. Caves have openings at both ends are called tunnels. Depositional landforms. Many depositional forms develop within the limestone caves. The chief chemical in limestone is calcium carbonate, which is easily soluble in carbonate water. Carbon dioxide absorbs rainwater. This calcium carbonate is deposited when the water carrying it in solution evaporates or loses its carbon dioxide as it trickles over rough rocks, stalactites, stalagmites, and pillars. Stalactites hang as icicles of different diameters. Normally, they are broad at their bases and taper towards their free ends, showing up in a variety of forms. Stalagmites rise up from the floor of the cave. In fact, stalagmites form due to dripping water from the surface or through the thin pipe of the stalactite immediately below it. Figure 7.111. Stalagmites may take the shape of a column, a disc, with either a smooth, rounded, bulging end or a miniature crater that like depression. The stalagmite and stalactites eventually fuse to give rise in columns and pillars of different diameters. Glaciers. Masses of ice moving as sheets over the land, continental glacier or Piedmont glacier, if a vast sheet of ice is spread over the plains at the foot of the mountain, or as linear flows down the slope of mountains in broad tuff-like valleys. Mountain and valley glaciers are called glaciers. The movement of glaciers is slow, unlike water flow. The movement could be a few centimeters to a few meters a day, or even less or more. Glaciers move basically because of the force of gravity. We have many glaciers in our country moving down the slopes and the valleys in Himalayas. Higher reaches of Arunachal Himachal Pradesh and Jammu and Kashmir are places to see some of them. Do you know where one can see River Bhagirathi is basically fed by meltwaters from under the snout, Kalmak, of the Gantori Glacier. In fact, Alkpuri Glacier feeds waters to Alkananda River. Rivers Alkananda and Bhagirathi join to make River Ganga near Deeprayag. Erosion by glaciers is tremendous because of friction caused by sheer weight of ice. The material plucked from the land by glaciers, usually large-sized angular blocks and fragments, get dragged along the floors or sides of the valleys and cause great damage through abrasion and plugging. Glaciers can cause significant damage to even unweathered rocks and can reduce high amounts into low hills and plains. As glaciers continue to move, debris gets removed, divides get lower, and eventually the slope is reduced to such an extent that glaciers will stop moving, leaving only a mass of low hills and vast outwash plains along with other depositional features. Figures 7.13 and 7.14 show various glacial, erosional, and depositional forms described in the text. Erosional landforms. Crick. Cricks are the most common of landforms in glaciated mountains. The cricks quite often are found at the heads of glacial valleys. The accumulated ice cuts these cricks while moving down the mountain tops. They are deep, long, and wide troughs or basins with very steep concave to vertically dropping high walls at its head as well as sides. A lake of water can be seen quite often within the cricks after the glacier disappears. Such lakes are called crick or tarn lakes. There can be two or more cricks, one leading into another down below in a stepped sequence. Horns and serrated ridges. Horns form through headward erosion of the crick walls. If three or more radiating glaciers cut headward until their cricks meet, high, sharp-pointed, and steep-sided peaks called horns form. The divides between crick side walls or head walls get narrow because of progressive erosion and turn into serrated or saw-toothed ridges, sometimes referred to as arates with very sharp crest and a zigzag outline. The highest peak in the Alps, Matterhorn, and the highest peak in the Himalayas, Everest, are in fact horns formed through headward erosion and radiating cricks. Glacial valleys and troughs. Glaciated valleys are trough-like and U-shaped with broad floors and relatively smooth and steep sides. The valleys may contain littered debris or debris shaped as mountain moraines with swampy appearance. There may be lakes gouged out of rocky floor or formed by debris within the valleys. There can be hanging valleys at an elevation on one or both sides of the main glacial valley. The faces of divides or spurs of such hanging valleys opening into main glacial valleys are quite often truncated to give them an appearance like triangular facets. Very deep glacial troughs filled with sea water and making up shorelines in high latitudes are called fjords. What are the basic differences between glacial valleys and river valleys? Depositional landforms. The unassorted coarse and fine debris dropped by melting glaciers is called glacial till. Most of the rock fragments are angular to subangular in form. Streams may form by melting ice at bottom sides or lower ends of glaciers. Some amounts of rock debris small enough to be carried by such meltwater streams is washed down and deposited. Such glacial fill of deposits are called outwash deposits. Unlike till deposits, the outwash deposits are roughly stratified and assorted. The rock fragments in outwash deposits are somewhat rounded at their edges. Figure 7.14 shows a few depositional landforms commonly found in glaciated areas. Moraines. They are long ridges and deposits of glacial till. Terminal moraines are long ridges and debris deposited at the toe of the glaciers. Lateral moraines form along the sides parallel to the glacial valleys. The lateral moraines may join a terminal moraine, forming a horseshoe-shaped ridge. Figure 7.13. There can be many lateral moraines on either side of the glacial valley. These moraines partly or fully owe their origin to glacial fluvial waters pushing up materials to the sides of glaciers. Many valley glaciers retreating rapidly leave an irregular sheet of till over their valley floors. Such deposits, varying greatly in thickness and in surface topography, are called ground moraines. The moraine in the center of the glacial valley, flanked by lateral moraines, is called medial moraine. They are imperfectly formed as compared to lateral moraines. Sometimes medial moraines are indistinguishable from ground moraines. Eskers. When glaciers melt in summer, the water flows on the surface of the ice or seeps down along the margins or even moves through holes in the ice. These waters accumulate beneath the glacier and flow like streams in a channel beneath the ice. Such streams flow over the ground, not in a valley cut in the ground, with ice forming in its banks. Very coarse materials like boulders and blocks, along with some minor fractures of rock debris carried into the stream, settle in the valley of ice beneath the glacier, and after the ice melts, can be found as a sinuous ridge called esker. Outwash plains. The plains at the foot of glacial mountains or beyond the limits of continental ice sheets are covered with glacial-fluvial deposits in the form of broad, flat alluvial fans, which may join to form outwash plains of gravel, silt, sand, and clay. Distinguish between river alluvial plains and glacial outwash plains. Drumlins. Drumlins are smooth, oval-shaped, ridge-like features composed mainly of glacial till with some masses of gravel and sand. The long axes of drumlins are parallel to the direction of ice movement. They may measure up to 1 kilometer in length and 30 meters or so in height. One end of the drumlins facing the glaciers, called stoss, end is blunter and steeper than the other end, called tail. The drumlins form due to dumping of rock debris beneath heavily loaded ice through fissures in the glacier. The stoss end gets blunted due to pushing by moving ice. Drumlins give an indication of glacier movements. What is the difference between till and alluvium? Waves and currents. Coastal processes are most dynamic and hence most destructive. So don't you think it is important to know about the coastal processes and forms? Some of the changes along the coast take place very fast. At one place, there can be erosion in one season and deposition in another. Most of the changes along the coast are accomplished by waves. When waves break, the water is thrown with great force into the shore, and simultaneously there is a great churning of sediments on the sea bottom. Constant impact of breaking waves drastically affects the coast. Storm waves and tsunami waves can cause for far-reaching changes in a short period of time than normal breaking waves. As wave environment changes, the intensity of the force of breaking waves changes. Do you know about the generating forces behind waves and currents? If not, refer to the chapter on movements in ocean waters. Other than the action of waves, the coastal landforms depend upon 1. The configuration of land and seafloor, 2. Whether the coast is advancing, emerging seaward, or retreating, submerging landward. Assuming sea level to be constant, 2 types of coasts are considered to explain the concept of evolution of coastal landforms. 1. High rocky coast, submerged coast. 2. Low, smooth, and gentle sloping sedimentary coast, emerged coast. High rocky coast. Along the high rocky coast, the rivers appear to have been drowned with highly irregular coastline. The coastline appears highly indented with extension of water into the land, where glacial valleys, fjord are present. The hillside drop off sharply into the water. Shores do not show any depositional landforms initially. Erosion features dominate. Along high rocky coasts, waves break with great force against the land, shaping the hillsides into cliffs. With constant pounding by waves, the cliffs recede, leaving a wave-cut platform in front of the sea cliff. Waves gradually minimize the irregularities along the shore. The materials which fall off and removed from the sea cliffs gradually break into smaller fragments and roll to roundness, will get deposited in the offshore. After a considerable period of cliff development and retreat, when coastline turns somewhat smooth, with the addition of some more material to this deposit in the offshore, a wave-built terrace would develop in front of wave-cut terrace. As the erosion along the coast takes place, a good supply material becomes available to longshore currents and waves to deposit them as beaches along the shore and as bars, long ridges of sand and or shingle parallel to the coast. In the near-shore zone, bars are submerged features, and when bars show up above water, they are called barrier bars. Barrier bar, which keep up to the headland of the bay, is called a spit. When barrier bars and spits form at the mouth of a bay and block it, a lagoon forms. The lagoons would gradually get filled up by sediments from the land, giving rise to a coastal plain. Low sedimentary coast. Along low sedimentary coasts, the rivers appear to extend their length by building coastal plains and deltas. The coastline appears smooth with occasional incursions of water in the form of lagoons and tidal creeks. The land slopes gently into the water. Marshes and swamps may abound along the coast. Depositional features dominate. When waves break over gentle sloping sedimentary coasts, the bottom sediments get churned and move readily, building bars, barrier bars, spits, and lagoons. Lagoons would eventually turn into a swamp, which would subsequently turn into a coastal plain. The maintenance of these depositional features depend upon the steady supply of materials. Storm and tsunami waves cause drastic changes, irrespective of supply of sediments. Large rivers which bring lots of sediment build deltas along low sedimentary coasts. The west coast of our country is a high, rocky, retreating coast. Erosional forms dominate in the west coast. The east coast of India is a low sedimentary coast. Depositional forms dominate in the east coast. What are the various differences between a high rocky coast and a low sedimentary coast in terms of processes and landforms? Erosional landforms: cliffs, terraces, caves, and stacks. Wave-cut cliffs and terraces are two forms usually found where erosion is the dominant shore process. Almost all sea cliffs are steep and may range from a few meters to 30 meters or even more. At the foot of such cliffs, there may be a flat or gently sloping platform covered by rock debris derived from the sea cliff behind. Such platforms occurring at elevations above the average height of waves is called a wave-cut terrace. The lashing of waves against the base of the cliff and the rock debris that gets smashed against the cliff along the lashing waves create hollows, and these hollows get widened and deepened to form sea caves. The roofs of caves collapse and the sea cliffs recede further inland. Retreat of the cliff may leave some remnants of rock standing isolated as small islands just off the shore. Such resistant masses of rock, originally parts of a cliff or hill, are called sea stacks. Like all other features, sea stacks are also temporary, and eventually coastal hills and cliffs will disappear because of wave erosion, giving rise to narrow coastal plains, and with onrush of deposits from over the land behind may get covered up by alluvium or may get covered up by shingle or sand to form wide beach. Depositional landforms: beaches and dunes. Beaches are characteristics of shorelines that are dominated by deposition but may occur as patches along even the rugged shores. Most of the sediment making up the beaches comes from land carried by the streams and rivers or from wave erosion. Beaches are temporary features. The sandy beach, which appears so permanent, may be reduced to a very narrow strip of coarse pebbles in some other season. Most of the beaches are made up of sand-sized materials. Beaches called shingle beaches contain excessively small pebbles and even cobbles. Just behind the beach, the sands lifted and winnowed from over the beach surfaces will be deposited as sand dunes. Sand dunes forming long ridges parallel to the coastlines are common along low sedimentary coasts. Bars, barriers, and spits. A ridge of sand and shingle formed in the sea of the offshore zone from the position of low tidal waterline to seaward, lying approximately parallel to the coast, is called an offshore bar. An offshore bar is which is exposed to due to further addition of sand is termed a barrier bar. The offshore bars and barriers commonly form across the mouth of the river or at the entrance of the bay. Sometimes such bars get keyed up to one end of the bay when they are called spits. Figure 7.15. Spits may also develop attached to headlands, hills. The barriers, bars, and spits at the mouth of the bay gradually extend, leaving only a small opening of the bay into the sea, and the bay will eventually develop into a lagoon. The lagoons get filled up gradually by sediment coming from the land or from the beach itself, aided by wind. And a broad and wide coastal plain may develop, replacing a lagoon. Do you know the coastal offshore bars offer the first buffer or defense against storm or tsunami by absorbing most of their destructive force? Then come the barriers, beaches, beach dunes, and mangroves, if any, to absorb the destructive force of storm and tsunami waves. So if we do anything which disturbs the sediment budget, the mangroves along the coast, these coastal forms will get eroded away, leaving human habitations to bear first strike of storm and tsunami waves. Winds. Winds is one of the two dominant agents in hot deserts. The desert floors get heated up too much and too quickly because of being dried up and barren. The heated floors heat up the air directly above them and result in upward movements in the hot, lighter air with turbulence, and any obstructions in its path set up eddies, whirlwinds, updrafts, and downdrafts. Winds also move along the desert floors with great speed, and the obstruction in their path create turbulence. Of course, there are storm winds which are very destructive. Winds cause such deflation, abrasion, and impact. Deflation includes lifting and removal of dust and smaller particles from the surface of rocks. In the transportation process, sand and silt act as effective tools to abrade the land surface. The impact is simply sheer force of momentum, which occurs when sand is blown into or against a rock surface. It is similar to sand blasting operation. The wind action creates a number of interesting erosional and depositional features in the deserts. In fact, many features of the deserts owe their formation to mass wasting and running water. As sheet floods. Though rain is scarce in deserts, it comes down torrentially in a short period of time. The desert rocks devoid of vegetation exposed to mechanical and chemical weathering processes due to drastic diurnal temperature changes, decay faster, and the torrential rains help it removing the weather materials easily. That means the weathered debris in deserts is moved by not only winds but also by rain sheet wash. The wind moves fine materials, and generally mass erosion is accomplished mainly through sheet floods or sheet wash. Stream channels in desert areas are broad, smooth and indefinite, and flow for a brief time after it rains. Erosional landforms. Pediments and pedoplains. Landscapes evolution in deserts is primarily concerned with the formation and extension of pediments. Gently inclined rocky floors close to the mountains at their foot, with or without a thin cover of debris, are called pediments. Such rocky floors form through the erosion of mountain front through a combination of lateral erosion by streams and sheet flooding. Erosion starts along the steep margins of the landmass or the steep sides of the tectonically controlled steep incision features over the landmass. Once pediments are formed with a steep wash slope followed by cliff or free face above it, the steep wash slope and free face retreat backwards. This method of erosion is termed as parallel retreat of slopes through back wasting. So, through parallel retreat of the slopes, the pediments extend backwards at the expense of mountain front, and gradually the mountain gets reduced, leaving an Inselberg, which is a remnant of the mountain. That's how the high relief in desert areas is reduced to low featureless plains called pedoplains. Playas. Plains are by far the most prominent landforms in the desert, in basins with mountains and hills around and along. The drainage is towards the center of the basin, and due to gradual deposition of sediment from basin margins, a nearly level plain forms at the feature of the basin. In times of sufficient water, this plain is covered up by a shallow water body. Such types of shallow lakes are called as playas, where water is retained only for a short duration due to evaporation, and quite often the playas contain good deposition of salts. The playa plain covered up by salts is called alkali flats, deflation hollows, and caves. Weathered mantle from over the rocks or bare soil gets blown out by persistent movement of wind currents in one direction. This process may create shallow depressions called deflation hollows. Deflation also creates numerous small pits or cavities over rock surfaces. The rock faces suffer impact and abrasion. of wind-borne sand, and first shallow depressions called blowouts are created, and some of the blowouts become deeper and wider, fit to be called caves. Mushroom, table, and pedestal rocks. Many rock outcrops in the deserts, easily susceptible to wind deflation and abrasion, are worn out quickly, leaving some remnants of resistant rocks polished beautifully in the shape of mushroom, with a slender stalk and a broad and rounded pear-shaped cap above. Sometimes the top surface is broad like a tabletop, and quite often the remains stand out like pedestals. List the erosional features carved out by wind action and action of sheet floods. Depositional landforms. Wind is a good sorting agent. Depending upon the velocity of wind, different sizes of grains are moved along the floors by rolling or saltation and carried in suspension, and in the process of transportation itself, the materials get sorted when the wind slows or begins to die down. Depending upon the grains and their critical velocities, the grains will begin to settle. So, in depositional landforms made by wind, good sorting of grains can be found. Since wind is there everywhere and wherever there is good source of sand, and with constant wind directions, depositional features in arid regions can develop anywhere. Sand dunes. Dry, hot deserts are good places for sand dune formation. Obstacles to initiate dune formation are equally important. There can be a great variety of dunes forms. Figure 7.16. Crest-shaped dunes called barchans, with the points or wings directed away from the wind direction, i.e., downwind, form where the wind direction is constant and moderate, and when the original surface over which sand is moving is almost uniform. Parabolic dunes form when sandy surfaces are partially covered with vegetation. That means parabolic dunes are reversed, barchans with wind direction being the same. Siph is similar to barchan with a similar difference. Siph has only one wing or point. This happens when there is a shift in wind conditions. The long wings of siph can grow very long and high. Longitudinal dunes form when supply of sand is poor and wind direction is constant. They appear as long ridges of considerable length but low in height. Transverse dunes are aligned, perpendicular to wind direction. These dunes form when the sand is an elongated feature at right angles to the wind direction. They may be very long and low in height. When sand is plenty, quite often the regular shaped dunes coalesce and lose their individual characteristics. Most of the dunes in the desert shift, and a few of them will get stabilized, especially near human habitation.
Exercises 1. Multiple choice questions. Bit 1. In which of the following stages of landform development downward cutting is dominated? A. Youth stage. B. Late mature stage. C. Early mature stage. D. Old stage. Bit 2. A dip valley characterized by step-like side slopes is known as A. U-shaped valley. B. Gorge. C. Blind valley. D. Canyon. Bit 3. In which of the following regions the chemical weathering process is more dominant than the mechanical process? A. Humid region. B. Limestone region. C. Arid region. D. Glacier region. Bit 4. Which one of the following sentences best defines the term lapis? A. A small to medium-sized shallow depression? B. A landform whose opening is more or less circular at the top and funnel-shaped towards bottom. C. A landform formed due to dripping water from surface. D. An irregular surface with sharp pinnacles, grooves and ridges. Bit 5. A deep, long and wide trough or basin with very steep, concave high walls at its head as well as in sides is known as A. Cirque, B. Glacial valley, C. Lateral moraine, D. Esker. Question 2. Answer the following questions in about 30 words. Bit 1. What do incised meanders in rocks and meanders in plains of alluvium indicate? Bit 2. Explain the evolution of valley sinks or uvalas. Bit 3. Underground flow of water is more common than surface runoff in limestone areas. Why? Bit 4. Glacial valleys show up many linear depositional forms. Give their locations and names. Bit 5. How does wind perform its task in desert areas? Is it the only agent responsible for the erosional features in the deserts? Question 3. Answer the following questions in about 150 words. Bit 1. Running water is by far the most dominating geomorphic agent in shaping the Earth's surface in humid as well as in arid climates. Explain. Bit 2. Limestones behave differently in humid and arid climates. Why? What is the dominant and most exclusive geomorphic process in limestone areas and what are its results? 3. Bit 3. How do glaciers accomplish the work of reducing high mountains into low hills and plains? Project work. Identify the landforms, materials, and processes around your area.
Unit 4. Climate. This unit deals with atmosphere, compositions and structure, elements of weather and climate, insolation, angle of incidence and distribution, heat budget of the Earth, heating and cooling of atmosphere, conduction, convection, terrestrial, radiation, advection, temperature, factors controlling temperature, distribution of temperature, horizontal and vertical, inversion of temperature, pressure, pressure belts, winds planetary, seasonal and local, air masses and fronts, tropical and extratropical cyclones, precipitation, evaporation, condensation, dew, frost, fog, mist and cloud, rainfall, types and world distribution, world climates, classification, Köppen, greenhouse effect, global warming, and climate changes. Chapter 8. Composition and structure of atmosphere. Can a person live without air? We eat food 2 to 3 times a day and drink water more frequently, but breathe every few seconds. Air is essential to the survival of all organisms. Some organisms, like humans, may survive for some time without food and water, but can't survive even a few minutes without breathing air. That shows the reason why we should understand the atmosphere in greater detail. Atmosphere is a mixture of different gases, and it envelopes the Earth all around. It contains life-giving gases like oxygen for humans and animals, and carbon dioxide for plants. The air is an integral part of the Earth's mass, and 99% of the total mass of the atmosphere is confined to the height of 32 kilometers from the Earth's surface. The air is colorless and odorless, and can be felt only when it blows as wind. Can you imagine what will happen to us in the absence of ozone in the atmosphere? Composition of the atmosphere. The atmosphere is composed of gases, water, vapor, and dust particles. Table 8.1 shows details of various gases in the air, particularly in the lower atmosphere. The proportion of gases changes in the higher layers of the atmosphere in such a way that oxygen will be almost negligible quantity at the height of 120 kilometers. Similarly, carbon dioxide and water vapor are found only up to 90 kilometers from the surface of the Earth. Gases. Carbon dioxide is meteorologically a very important gas, as it is transparent to the incoming solar radiation, but opaque to the outgoing terrestrial radiation. It absorbs a part of terrestrial radiation and reflects back some part of it towards the Earth's surface. It is largely responsible for the greenhouse effect. The volume of other gases is constant, but the volume of carbon dioxide has been rising in the past few decades, mainly because of the burning of fossil fuels. This has also increased the temperature of the air. Ozone is another important component of the atmosphere, found between 10 and 50 kilometers above the Earth's surface, and acts as a filter and absorbs the ultraviolet rays radiating from the sun and prevents them from reaching the surface of the Earth. Water vapor. Water vapor is also a variable gas in the atmosphere, which decreases with altitude. In the warm and wet tropics, it may account for 4% of air by volume, while in the dry and cold areas of desert and polar regions, it may be less than 1% of the air. Water vapor also decreases from the equator towards the poles. It also absorbs parts of the insolation from the sun and preserves the Earth's radiated heat. It thus acts like a blanket, allowing the Earth neither to become too cold nor too hot. Water vapor also contributes to the stability and instability in the air. Dust particles. Atmosphere has a sufficient capacity to keep small solid particles, which may originate from different sources and include sea salts, fine salt, soil, smoke soot, ash, pollen, dust, and disintegrated particles of meteors. Dust particles are generally concentrated in the lower layers of the atmosphere, yet conventional air currents may transport them to great heights. The higher concentration of dust particles is found in subtropical and temperate regions due to dry winds in comparison to equatorial and polar regions. Dust and salt particles act as hygroscopic nuclei around which water vapor condenses to produce clouds. Structures of the atmosphere. The atmosphere consists of different layers with varying density and temperature. Density is highest near the surface of the Earth and decreases with increasing altitude. The column of the atmosphere is divided into 5 different layers, depending upon the temperature condition. They are troposphere, stratosphere, mesosphere, thermosphere, and exosphere. The troposphere is the lowermost layer of the atmosphere. Its average height is 13 kilometers and extends roughly to a height of 8 kilometers near the poles and about 18 kilometers of the equator. Thickness in the troposphere is greatest at the equator because heat is transported to the great heights by strong conventional currents. This layer contains dust particles and water vapor, All changes in the climate and weather take place in this layer. The temperature in this layer decreases at the rate 1 degree for every 165 meters of height. This is the most important layer for all biological activity. The zone separating the troposphere from stratosphere is known as the tropopause. The air temperature at the tropopause is about minus 80 degrees Celsius over the equator and about minus 45 degrees Celsius over the poles. The temperature here is nearly constant, and hence it is called the tropopause. The stratosphere is found above the tropopause and extends up to a height of 50 kilometers. One important feature of the stratosphere is that it contains the ozone layer. This layer absorbs ultraviolet radiation and shields life in the earth from intense, harmful form of energy. The mesosphere lies above the stratosphere, which extends up to a height of 80 kilometers. In this layer, once again, temperature starts decreasing with the increase in altitude and reaches up to minus 100 degrees Celsius at the height of 80 kilometers. The upper limit of mesosphere is known as the mesopause. The ionosphere is located between 80 and 400 kilometers above the mesopause. It contains electrically charged particles known as ions, and hence it is known as ionosphere. Radio waves transmitted from the Earth are reflected back to the Earth by this layer. Temperature here starts increasing with the uppermost layer at the atmosphere above the thermosphere is known as the exosphere. This is the highest layer, but very little is known about it. Whatever contents are there, these are extremely rarefied in this layer, and it gradually merges with the outer space. Although all layers of the atmosphere must be exercising influence on us, geographers are concerned with the first two layers of the atmosphere. Elements of weather and climate. The main elements of atmosphere which are subject to change with influence human life on Earth are temperature, pressure, winds, humidity, clouds, and precipitation. These elements have been dealt in detail in chapters 9, 8, 10, and 11.
Exercises 1. Multiple choice questions. Bit 1. Which one of the following gases constitutes the major portion of the atmosphere? A. Oxygen, B. Nitrogen, C. Argon, D. Carbon dioxide. Bit 2. Atmospheric layer important for human beings is A. Stratosphere, B. Mesosphere, C. Troposphere, D. Ionosphere. Bit 3. Sea salt, pollen, ash, smoke, soot, fine soil. These are associated with A. Gases, B. Dust particles, C. Water vapor, D. Meteors. Bit 4. Oxygen gas is a negligible quantity at the height of atmosphere. A. 90 km, B. 120 km, C. 100 km, D. 150 km. Bit 5. Which one of the following gases is transparent to incoming solar radiation and opaque to outgoing terrestrial radiation? A. Oxygen, B. Nitrogen, C. Helium, D. Carbon dioxide. Question 2. Answer the following questions in about 30 words. Bit 1. What do you understand by atmosphere? Bit 2. What are the elements of weather and climate? Bit 3. Describe the composition of atmosphere. Bit 4. Why is troposphere the most important of all layers of the atmosphere? Question 3. Answer the following questions in about 150 words. Bit 1. Describe the composition of the atmosphere. Bit 2. Draw a suitable diagram for the structure of the atmosphere and label it and describe it.
Chapter 9. Solar radiation, heat balance, and temperature. Do you know that you feel the air around you? Do you know that we live in the bottom of huge pile of air? We inhale and exhale, but we feel the air when it's in motion. It means air in motion is wind. You have already learned about the fact that Earth is surrounded by the air all around. This envelope of air is atmosphere, which is composed of numerous gases. These gases support life over Earth's surface. Earth receives almost all of its energy from the sun. The Earth in turn radiates back to space the energy received from the sun. As a result, the Earth neither warms up nor does it get cooled down over a period of time. Thus, the amount of heat received by the different parts of Earth is not the same. This variation causes pressure differences in the atmosphere. This leads to a transfer of heat from one region to the other by winds. This chapter explains the process of heating and cooling of the atmosphere and the resultant temperature distribution over the Earth's surface. Solar radiation. The Earth's surface receives most of its energy in short wavelengths. The energy received by the Earth is known as incoming solar radiation, which in short terms is isolation. As the Earth is a geode resembling a sphere of the sun's rays that fall obliquely at the top of the atmosphere, and the Earth intercepts a very small portion of the sun's energy, on an average the Earth receives 1.94 calories per square centimeter per minute at the top of the atmosphere. The solar output received at the top of the atmosphere varies slightly in a year due to the variations in distance between the Earth and the sun. During its revolution around the sun, the Earth is farthest from the sun on July 4th. This position of the sun is called aphelion. On the 3rd of January, the Earth is nearest to the sun. This position is called perihelion. Therefore, the annual isolation received by the Earth on the 3rd of January is slightly more than the amount received on the 4th of July. However, the effect of the variation in solar output is marked by the other factors like the distribution of land and sea and the atmospheric calculation. Hence, this is the variation in solar output does not have the great effect on daily weather changes on the surface of the Earth. Variability of isolation at the surface of the Earth. The amount and the intensity of the isolation vary during a day, and a season, and a year. The factors that cause these variation in isolation are: number 1, the rotation of Earth on its axis; number 2, the angle of inclination of the sun's rays; number 3, the length of the day; number 4, the transparency of the atmosphere; number 5, the configuration of land in terms of its aspect. The last two, however, have less influence. The fact that Earth's axis makes an angle of 66.5 with the plane of its orbit around the sun has greater influence on the amount of isolation received at the different latitudes. Note that the variation in duration of the day at the different latitudes on solstice given in the table 9.1. The second factor that determines the amount of isolation received in the angle of the inclination over the rays. This depends on the latitude of the place. The higher the latitude, the less an angle of the surface of the Earth, resulting in slant sun rays. The area covered by the vertical rays is always less than the slant rays. If more area is covered, the energy gets distributed and the net energy received per unit area decreases. Moreover, the slant rays are required to pass through a greater depth of atmosphere, resulting in more absorption, scattering, and diffusion. The passage of solar radiation through the atmosphere. The atmosphere is largely transparent to short wavelength solar radiation. The incoming solar radiation passes through the atmosphere before striking the Earth's surface. Within the troposphere, water vapor, ozone, and the other gases absorb much more near-infrared radiation. Very small suspended particles in the troposphere scatter visible spectrum both to space and towards the Earth's surface. This process adds the color to the sky. The red color of the rising and setting sun and the blue color of the sky are the result of scattering light within the atmosphere. Spatial distribution of the isolation at the Earth's surface. The isolation received at the surface varies about 320 watt in the tropics, about 70 watt in the poles. Maximum isolation is received over the subtropical deserts, where the cloudiness is at the least. Equator receives the comparatively less isolation than the tropics. Generally, at the same latitude, the isolation is more over the continent than over the oceans. In the winter, the middle and higher latitudes receive less radiation in the summer. Heating and cooling of the atmosphere. There are different ways of heating and cooling on the atmosphere. The Earth, after being heated by the isolation, transmits the heat at the atmospheric layers near to the Earth's long-form wave. The air in contact uppers the land gets heated slowly, and the upper layers in contact with the lower layers also get heated. This process is called conduction. Conduction takes place when two bodies of unequal temperatures are in contact with one another. There are a flow of energy with the warmer cool to the body. The transfer of heat continues until the both bodies attain the same temperature or the contact is broken. Conduction is important in heating the lower layers of the atmosphere. The air is in conduction with the Earth rises vertically on the Earth, heating in the currents and further transmits the heat in the atmosphere. This process of the vertical heating, the transformation, is also known as convection. The convective transfer of the energy is confined only to the troposphere. The transfer of the heat through the horizontal movement is called advection. Horizontal movement in the air is relatively important than the vertical movement. In the middle latitudes, most of the diurnal variation in the daily weather has caused by advection alone. In tropical regions, particularly in the northern India during the summer season, long winds called lu in the outcome of advection process. Terrestrial radiation. The isolation received by the Earth is in short wave forms and heats up its surface. The Earth, after being heated itself, becomes a radiating body. It radiates energy to the atmosphere in long wavelengths. This energy heats up the atmosphere form below. This process is known as terrestrial radiation. The long wave radiation is absorbed by the atmospheric gases, particularly by carbon dioxide and other greenhouse gases. Thus, the atmosphere is indirectly heated by the Earth's radiation. The atmosphere in turn radiates the transmits heat to the Earth's surface until finally the amount of heat received from the Earth is returned to space, thereby maintaining a constant temperature at the Earth's surface in the atmosphere. Heat budget of the planet Earth. Figure 9.2 depicts the Earth budget of the planet Earth. The Earth as a whole is not accumulate or lose heat. It maintains its temperature. This can only happen if the amount of heat received by the form of isolation equals the amount of lost by the terrestrial radiation. Consider that the isolation received at the top atmosphere is 100%. While passing through the atmosphere, some amount of energy is reflected, scattered, and absorbed. The only remaining part reaches the Earth. Roughly 35 units are reflected back to space even before reaching the Earth's surface. Of these, 27 units are reflected back to the Earth's clouds, 2 units from the snow and covered by areas on Earth. The reflected amount of radiation is called a layer of Earth. The remaining 65% or units are absorbed. In the 16 units between the atmosphere and 51 by the Earth's surface, the Earth radiates back 51 units of the form of terrestrial radiation of these. Of these, 17 units are radiated to space directly and the remaining 34 are absorbed by the atmosphere. Absorbed directly in the atmosphere, 9 units through the convection and turbulence and 19 units through the latent of the condensation. 48 units absorbed by the atmosphere and also radiate back into space. Thus, the total radiation returning from the Earth and the atmosphere, respectively, is 74 plus 48 is 65 units, which balance the total of 65 units received from the Sun. This has tempered the heat budget or the heat balance of Earth. This explains why Earth neither warms nor cools down despite the huge transfer of heat that it takes place. variation in the net height of the budget at the Earth's surface. As explained earlier, there are variations in the amount of radiation received at the Earth's surface. Some part of the Earth has surplus radiation balance while the other part has deflect. Figure 9.3 reflects the latitudinal variation in the net radiation balance of Earth in the atmospheric system. This figure shows that there are slopes of net radiation balance between 40 degrees north and south, and the regions near the poles have deflect. The slopes heat energy from the tropics and redistributed polewards as a result of tropics do not get progressively heated up to the accumulation of heat, and the high latitudes get permanently frozen due to the excess deflect. Temperature. The interaction of isolation with the atmosphere and the Earth's surface creates the heat, which is measured in terms of temperature. While the heat represents molecular movement of particles compressing a substance, the temperature is measurement in degrees how hot or cold a thing is. Factors controlling temperature distribution. The temperature of air at any place is influenced by the latitude of the place. The latitude of the place, the distance of the sea, the air mass circulation, the presence of warm and cold currents are local aspects. The latitude. The temperature of the place depends on the isolation received. It has been explained that earlier the isolation varies according to the latitude, hence the temperature also varies accordingly. The altitude. The atmosphere is indirectly heated by the terrestrial radiation from below. Therefore, the places near the sea level record higher temperature than the other places situated at higher elevations. In other words, the temperature generally decreases during the increasing height. The rate of decreased temperature with the height is tempered as a normal lapse rate. It is 6.5 Celsius per 1,000 meters. Distance from the sea. Another fact that influences temperature is the location placed with respect to the sea. Compared to land, the sea gets heated slowly and loses therefore the radiation temperature over the sea unless compared to land. The places situated near the sea comes under the moderating influence of the sea and land breeze, which moderate the temperature. Air mass and ocean currents. Like the land and sea breeze, the passage of air also affects the temperature. The places which come under the influence of warm air masses experience higher temperature, and the places that come out under the influence of cold air masses also expect lower temperature. Similarly, the places located on the coast where the warm ocean currents flow higher temperature, the places located on the coast is where the cold currents flow. Distribution of temperature. The global distribution of temperature can also be understood by studying the temperature determined in July and January. The temperature distribution is generally shown on the map with the help of isotherms. The isotherms are line joining places having equal temperature. Figure 9.4 and B show the distribution of the surface air temperature in the month of July and January. In general, the effect of latitude on the temperature is well pronounced on the map, as the isotherms are generally parallel to the latitude. The deviation from the general trend is more pronounced in January than July, especially on the northern hemisphere. In the northern hemisphere, the land surface is much larger than the southern hemisphere. Hence, the effect of land masses and ocean currents are well pronounced. In January, the isotherms deviate from the north to the ocean to the south over the continent. This can be seen over the North Atlantic Ocean. The presence of the warm ocean's currents, Gulf Stream, and the Atlantic Ocean warmer, and the isotherms bend toward the north. All over the land, the temperature decreases sharply and the isotherms bend over to Europe. It is much pronounced at the Serbian plain. The mean of January temperature along 60 east latitude is minus 20 Celsius, both 80% degree north and 50 degree north latitudes. This means monthly temperature of January is over 27 Celsius in equilateral oceans, over 24 Celsius in tropics, and 2 Celsius to 0 Celsius in the middle latitudes, and negative 18 Celsius to negative 48 Celsius in the Eurasian continental interior. The effects of the ocean is well pronounced in the southern hemisphere. Here are isotherms that have more or less parallel to the latitudes, in the variation in temperature is more gradual than the northern hemisphere. The isotherm of 20 Celsius and 10 Celsius and 0 Celsius runs parallel to 55 south and 57 south in the 60 degrees south latitude respectively. In the July, the isotherms generally run the parallel to the latitude. The equatorial oceans record warmer temperatures. More than 27 Celsius over land, more than 30 Celsius is noticed in the subtropical continental region of Asia. Along the 30 north latitude, along with the 40 north, runs the isotherm of 10 Celsius, along with 40 south, the temperature is 10 Celsius. Figure 9.5 shows the range of temperature between January and July. The highest range of temperature is more than 60 Celsius over the northeastern part of Eurasian continent. This is due to the continentality. The least range of temperature, 3 Celsius, is found between 20 south and 15 north. Inversion of temperature. Normally, temperature decreases with the increase in elevation. This is normally lapse rate. At times, the situation is received and reversed. The normal lapse rate is inversed. It is called the inversion of temperature. Inversion is usually of short duration but quite common nonetheless. As a long winter night with clear skies and the air is still ideal for the situation inversion, the heat of the day is radiated off through the night. In early morning hours, and the earth is cooler than the air above. Over polar areas, temperature inversion is normal throughout the year. Surface inversion promotes stability in the lower layers of the atmosphere. Smoke and dust particles get collected beneath the inversion layers and spread horizontally to fill the lower strata in the atmosphere. Dense fogs, the mornings are common occurring, especially during the winter season. This inversion commonly lasts a few hours until the sun comes up, belonging to the warmth of the earth. The inversion takes place in the hills, mountains during the air drainage. Cold air at the hills and mountains produced during the night. The flows under the influence of gravity. Being heavy, dense, and the cold air affects almost like water and moves down the slope to pile up deeply in pockets and valleys bottoms with the warm air above. This is called air drainage. This protects plants and forest damages.
Planck's law states that hotter a body, the more energy it will radiate, and shorter the wavelength of that radiation. Specific heat is the energy needed to raise the temperature of 1 gram of substance by 1 Celsius. Exercises. 1. Multiple choice questions. Bit 1. The sun is directly overhead at noon on 21st June at A. the equator, B. 23.5 degrees south, C. 23.5 degree north, D. 66.5 degree north. Bit 2. In which one of the following cities are the days the longest? A. Tiruvananthapuram, B. Chandigarh, C. Hyderabad, D. Nagpur. Bit 3. The atmosphere is mainly heated by the A. Short-wave solar radiation, B. Reflected solar radiation, C. Long-wave terrestrial radiation, D. Scattered solar radiation. Bit 4. Make correct pairs from the following two columns. Column A has terms. Bit 1. Insolation. Bit 2. Albedo. Bit 3. Isotherm. Bit 4. Annual range. Column B has the options A. The difference between the mean temperature of the warmest and the coldest months. B. The lines joining the places of equal temperature. C. The incoming solar radiation. D. The percentage of visible light reflected by the object. Bit 5. The main reason that the Earth experiences highest temperatures in the subtropics in the northern hemisphere rather than at the equator is A. Subtropical areas tend to have less cloud cover than equatorial areas. B. Subtropical areas have longer day hours in the summer than the equatorial. C. Subtropical areas have an enhanced greenhouse effect compared to equatorial areas. D. Subtropical areas are nearer to the oceanic areas than the equatorial locations. 2. Answer the following questions in about 30 words. Bit 1. How does the unequal distribution of heat over the planet Earth in space and time cause variations in weather and climate? Bit 2. What are the factors that control temperature distribution on the surface of the Earth? Bit 3. In India, why is the day temperature maximum in May and why not after the summer solstice? Bit 4. Why is the annual range of temperature high in the Siberian plains? 3. Answer the following questions in about 150 words. Bit 1. How do the latitude and the tilt in the axis of rotation of the Earth affect the amount of radiation received at the Earth's surface? Bit 2. Discuss the process through which the Earth atmosphere system maintains heat balance. Bit 3. Compare the global distribution of temperature in January over the northern and the southern hemisphere of the Earth. Project work. Select a meteorological observatory located in your city or near your town. Tabulate the temperature data as given in the climatological table of observatories. Bit 1. Note the altitude, latitude of the observatory and the period for which the mean is calculated. Bit 2. Define the terms related to temperature as given in the table. Bit 3. Calculate the daily mean monthly temperature. Bit 4. Draw a graph to show the daily mean maximum, the daily mean minimum, and the mean temperature. Bit 5. Calculate the annual range of temperature. Bit 6. Find out in which months the daily range of temperature is the highest and the lowest. Bit 7. List out the factors that determine the temperature of the place and explain the possible causes for temperature variation in the months of January, May, July, and October. Example: observatory is at New Delhi, Safdarjung, latitude 28° 35° north. Based on observation 1951 to 1980. Altitude above mean sea level 216 meters. There are 5 columns with the heading. First column has heading month. Second column has heading mean of Delhi maximum temperature in degrees Celsius. Third column mean of Delhi minimum temperature in degrees Celsius. Highest recorded temperature in degrees Celsius. Lowest recorded temperature in degrees Celsius. For example, in the month part, we can take 2 months, January and May. Mean of Delhi maximum temperature in January is 21.1 degrees Celsius and in May 39.6 degrees Celsius. Mean of Delhi minimum temperature in month of January it is 7.3 degrees Celsius and in May it is 25.9 degrees Celsius. Highest recorded temperature in month of January 29.3 degrees Celsius and in May 47.2 degrees Celsius. Lowest recorded temperature in month of January is 0.6 while in May is 17.5 degrees Celsius. Daily mean temperature monthly. January is equal to 21.1 plus 7.3 by 2 is equal to 14.2 degrees Celsius. And for the month of May, it is 39.6 plus 25.9 by 2 is equal to 32.75 degrees Celsius. Annual range of temperature. Mean maximum temperature in May minus mean temperature in January. Annual range of temperature is equal to 32.75 degrees Celsius minus 14.2 degrees Celsius is equal to 18.55 degrees Celsius.
Chapter 10, Atmospheric Circulation in Weather Systems. After Chapter 9 described the uneven distribution of temperature over the surface of the Earth, air expands when heat gets compressed and cooled. This results in variation in the atmospheric pressure. The result is that it causes movement of air from high pressure to low pressure, setting in air in motion. You already know that air's horizontal motion is wind. Atmospheric pressure also determines when the heat and moisture across the planet, thereby maintaining a constant temperature for the planet as a whole. The vertical rising moist air also cools down from its form of clouds and bringing precipitation. This chapter has been devoted to explain the causes of pressure differences, the forces that control the atmospheric circulation, the turbulent patterns of wind, and the formulation of air masses and the distribution whether when air masses interact with each other, and the phenomenon of violent tropical storms. Atmospheric pressure. Do you realize that our body is suspected to a lot of air pressure? As one moves up, the air gets varied and one feels breathless. The weight of a column air contained in a unit area from a mean sea level to the top of the atmosphere is called atmospheric pressure. The atmospheric pressure expresses in unit in millibars. At the sea level, the average atmospheric pressure is 1,013.2 millibars. Due to the gravity, the air at the surface is denser and has higher pressure. Air pressure is measured with the help of mercury barometer of an Andron barometer. Consult your book, Practical Work in Geography Part 1, and learn about these instruments. The pressure decreases with height. At any elevation, it varies from place to place, and the variation is primarily caused by the air motion. Wind, which also moves high pressure areas to low areas. Vertical variation of pressure. In the lower atmosphere, the pressure decreases rapidly with the height. The decrease amount to about 1 mb for each 10 meters increase in elevation. It does not always decrease at the same rate. Table 10.1 gives the average pressure and the temperature at the selected levels of elevation for a standard atmosphere. Table 10.1. The vertical pressure gradient force is much larger than the horizontal pressure gradient, but in general balanced by the near equal but the opposite gravitational force, hence we do not experience strong upward winds. Horizontal distribution of pressure. Small differences in pressure are highly significant in terms of the wind direction and velocity. Horizontal distribution of pressure is studied by the drawings in isobars at the constant levels. Isobars are lines connecting the places having equal pressure. In order to eliminate the effect of altitude on pressure, it is measured at any station after being reduced to sea level for purposes of comparison. The sea level pressure distribution is shown on the weather maps. Figure 10.1 shows the patterns of isobars corresponding to the pressure system. The low pressure system is enclosed by one or more isobars with the lowest pressure in the center. High pressure system is also enclosed by one or more isobars with the highest pressure in center. World distribution of sea level pressure. The world distribution of sea level pressure in January and July have only been shown in figures 10.2 and 10.3. Near the equator, the sea level pressure is low in areas known as an equilateral low. Along 30 north and 30 south are found the high-pressure areas known as the subtropical heights. Further polewards along 60 north and 60 south. The low-pressure belts are termed as the subpolar lows. Near the lows, the pressure is high, known as a polar high. These pressure belts are not permanent in nature. These accelerate with the apparent movement of the sun. In the northern hemisphere in the winter, they move southernwards, and in summer they move northernwards. Forces affecting the velocity and direction of wind. You already know that the air is set in motion due to the differences in atmospheric pressure. The air in the motion is called wind. The wind blows from a high pressure to low pressure. The wind at the surface experiences friction. In addition, rotation of the earth also affects the wind movement. The force exerted by the rotation of earth is also known as the Coriolis effect. Thus, horizontal winds near the earth's surface respond to the combined effect of three forces: the pressure gradient force, the frictional force, and the Coriolis force. In addition, the gravitational force acts downward. Pressure gradient force. The differences in atmospheric pressure produces a force. The rate of change in the pressure with the respective distance in the pressure gradient. The pressure gradient is also strong. The isobars are close to each other and apart, and is weak where the isobars are apart. Frictional force. It affects the speed of wind. It is the greatest the surface, and the influence generally extends up to an elevation of 1 to 3 kilometers. Over the sea surface is a frictional and minimal. Coriolis effect. The rotation of the earth about its axis affects the direction of the wind. The force is called Coriolis effect force after the French psychologist who described it in 1844. It deflects the wind to the right direction in the north hemisphere and to the left of the southern hemisphere. The deflection is more when the wind's velocity is high. The Coriolis force is directly proportional to the angle of the latitude. It is maximum at the poles and absent at the equator. The Coriolis force acts perpendicular to the pressure gradient force. The pressure gradient force is perpendicular to the isobar. The higher the pressure gradient force, the more the velocity of the wind, and the larger is the deflection of the direction of the wind. As a result, these two forces operating perpendicular to each other is low pressure area. The wind blows around it. At the equator, the Coriolis effect is zero, and the wind blows perpendicular to the isobars. The low pressure gets filled instead of getting filled. And that is the reason why tropical cyclones are not formed near the equator. Pressure and wind. The velocity and direction of the wind are net results of the wind generating forces. The wind in the upper atmosphere is 2 to 3 kilometers above the surface and are free from frictional effect of the pressure and controlled mainly by the general and pressure of the gradient and Coriolis force. When the isobars are straight and there is no friction, the pressure gradient is balanced by the Coriolis force and the resultant wind blows parallel to the isobar. This wind is known as a geographic wind. The wind circulation around is low as called cyclone and cyclonic circulation. Around a high, it is called an anticyclonic circulation. The directions of a wind around such system changes according to the location of the different hemispheres. The wind circulation at the Earth's surface are low and high on many occasions is closely related to the wind circulation at higher level. Generally, over a low pressure area, the wind is converged and rife. Over the high pressure area, the wind will subside from the above and divergent of the surface. Apart from the convergence, some eddies, convection currents, aphogatic uplift, and uplift along front causing the rising of air, which is essential for the formation of clouds and precipitation. General circulation of the atmosphere. The pattern of planetary winds largely depends on number 1, latitudinal variation of the atmospheric heating, number 2, emergence of the pressure belts, number 3, the migration of belts following the apparent path of the sun, number 4, the distribution of continents and oceans, number 5, the rotation of Earth. The patterns of movements of the planetary wind is called the general circulation of the atmosphere. The general circulation of the atmosphere also sets the motion of the water in the ocean circulation, which influences the Earth's climate. A schematic description of the general circulation is shown in the figure 10.6. 10.6. The air at the intertropical convergence zone rises because of the convection caused by the high isolation and the low pressure is created. The wind from the tropical convergence at this low pressure zone, the convergent air rises along the convective cell. It reaches the top of the troposphere up to in a latitude of 16 kilometers and moves forward towards the poles. This causes accumulation of air at the northern of 30 degrees in the south. Part of the accumulated air skids to the ground and forms a subtropical high. Another reason for sinking is the cooling of air when it reaches 30 north and 30 south latitudes. Down below, near the land surface, the air blows towards the equator at its easterlies. The easterlies are either sides of the equator converge in the intertropical convergence zone. Such circulations from the surface upward and vice versa are called cells. Such cells in the middle of tropics are called Hartley cells. In the middle latitudes, the circulation is kind of sinking cold air that comes out from the pole and a rising warm air that blows from the subtropical high. At the surface, these ones are called as westerlies, and the cell is known as a Faro cell. At the polar latitudes, the cold dense air subdies near the pole and blows towards the middle latitudes, and the polar easterlies. This cell is called a pattern of polar cell. These three cells patterns are for general circulation of the atmosphere. These transfer heat lower latitudes to higher latitudes, meaning the general circulation. The general circulation of the atmosphere also affects the oceans. The large scale of winds of the atmosphere initiate large and slow movements of currents of the ocean. Ocean, in return, provides input of energy and water vapor into the air. These interactions take place rather slowly on a large portion of land. Seasonal wind. The pattern of wind circulation is modified in different seasons due to the shifting of region of the maximum heating pressure and wind belts. These most pronounced effects are shift noticed as the monsoons, especially over Southeast Asia. You would be studying the details of monsoon in the Book of India Physical Environment. The other local deviations from the general circulation are followers. Local winds. Difference of the circulating and hot and cooling of Earth's surfaces in cycles, those develop over a day or annually, can create common several locally and regional winds. Land and sea breeze. As explained later, the land and sea breeze absorb the later heat differently. During the day, the land heats up faster and becoming warmer at the sea level. Therefore, over land, the air rises, giving the rise to a lower pressure area where the sea is relatively cool and pressure over the sea is relatively high. Thus, pressure gradient from the sea creates the wind from the sea and land breeze. In night, several of the conditions take place. The land loses heat faster and cooler than sea. The gradient is the land to sea and hence the breeze. Mountain and valley winds. In mountain regions, during the day, slopes get heated up and move upslope, and resulting in a gap, and the wind's valley blows in the valley. The wind is known as the valley breeze. During the night, the slopes get cooled and dense air descends into the valley as a mountain wind. The cools into the valley is called a karabatic wind. Another type of wind that occurs in the leeward side of the mountain regions. And the moisture in these winds while crossing the mountain ranges condense and precipitate in the descents of getting the leeward, and this dry air may melt the snow in a short time. Thunderstorms and tornadoes. Other severe local storms are thunderstorms and tornadoes. These are short duration, occurring over a small area, but are violent. Thunderstorms are caused by intense convection on moist, hot days. The thunderstorm is well-grown cumulation clouds producing thunder and lightning. When the cloud extends the heights from sub-zero pressure, pervades in airs and formed across the hailstorm. There are insufficient moisture, and the thunderstorm can generate dust storms. A thunderstorm is characterized by the intense updraft and rising warm air. These causes the clouds to grow bigger and rise greater height. This causes precipitation. Later, downward brings them to earth and cools the air and the rain. From severe thunderstorms and such phenomenon, the tornadoes generally occur in middle latitudes. The tornado over the sea is called water spouts. Potential heat and energies are converted into kinetic energy in these storms, and their resultness of atmospheric again return to the stable state.
Exercises 1. Multiple choice questions. Bit 1. If the surface air pressure is 1000 millibars, the air pressure at 1 kilometer above the surface will be A. 700 millibars, B. 1100 millibars, C. 900 millibars, D. 1300 millibars. Bit 2. The intertropical convergence zone normally occurs A. Near the equator, B. Near the Tropic of Cancer, C. Near the Tropic of Capricorn, D. Near the Arctic Circle. Bit 3. The direction of wind around a low pressure in northern hemisphere is A. Clockwise, B. Perpendicular to isobars, C. Anticlockwise, D. Parallel to isobars. Bit 4. Which one of the following is the source region for the formation of air masses? A. The equatorial forest, B. The Himalayas, C. The Siberian plain, D. The Deccan plateau. 2. Answer the following questions in about 30 words. Bit 1. What is the unit used in measuring pressure? Why is the pressure measured at station level reduced to the sea level in preparation of weather maps? Bit 2. While the pressure gradient force is from north to south, that is, from the subtropical high pressure to the equator in the northern hemisphere, why are the winds northeasterlies in the tropics? Bit 3. What are the geotrophic winds? Bit 4. Explain the land and sea breezes. Question 3. Answer the following questions in about 150 words. Bit 1. Discuss the factors affecting the speed and direction of wind. Bit 2. Draw a simplified diagram to show the general circulation of the atmosphere over the globe. What are the possible reasons for the formation of subtropical high pressure over 30° north and south latitudes? Bit 3. Why does tropical cyclone originate over the seas? In which part of the tropical cyclone do torrential rains and high-velocity winds blow, and why? Project work. Bit 1. Collect weather information over media such as newspaper, TV, and radio for understanding the weather systems. Bit 2. Read the section on weather in any newspaper, preferably one having a map showing a satellite picture. Mark the area of cloudiness. Attempt to infer the atmospheric circulation from the distribution of clouds. Compare the forecast given in the newspaper with the TV coverage. If you have access to TV, estimate how many days in a week where the forecast were accurate.
Chapter 11. Water in the atmosphere. You have already learned that the air contains water vapor. It varies from 0 to 4% by the volume of the atmosphere and plays an important role in the weather phenomena. Water is present in the atmosphere in three forms, namely gases, liquid, and solids. The moisture in the atmosphere is derived by the water bodies through evaporation and from plants through transpiration. Thus, these are continuous change of water between the atmosphere and oceans and contains through the process of evaporation, transportation, condensation, and precipitation. Water vapor present in the air is also known as humidity. It is expressed quantitatively in different ways. The actual amount of water vapor present in the atmosphere is known as absolute humidity. The weight of the vapor per unit of volume air is expressed in terms of grams per cubic meter. The ability of air to hold water vapor depends entirely on its temperature. The absolute humidity differs from place to place in the surface of Earth. The percentage of moisture present in the atmosphere as compared to the full capacity is given temperature as known as a relative humidity. With the exchange of air temperature, the capacity to retain moisture increases, decreases. The relative humidity is also affected in the great over the oceans, least over the continents. The air containing moisture is full of its capacity at the given temperature is said to be saturated. This means that the air given at temperature is incapable of holding any additional amount of moisture at this stage. The temperature at which the saturation occurs in the given temperature is known as a dew point. The amount of vapor in the atmosphere is added or withdrawn due to the evaporation condensively, respectively. Evaporation and condensation. Evaporation is a process of which water is transferred from a liquid to a gaseous state. Heat is maintained at evaporation. The heat and temperature at which the water starts evaporating is referred as the latent heat of evaporation. Increase of the temperature, increase the water absorption, retention of the capacity is given parcel of air. Similarly, if the moisture contact is low, air is potentially absorbing and retaining moisture. Movement of the air replaces the saturated layer of unsaturated layer. Hence, the greater movement of air, the greater is the evaporation. The transformation of water vapor is called the condensation. Condensation is caused by the loss of heat. When the moisture is cooled, it may reach a level where the capacity to hold water increases and the excess water vapor condenses into a formed liquid. If it directly condenses into a solid form, it is known as sublimation. In free air, condensation results in cooling around very small particles termed as hygroscopic condensation nuclei. Particles of dust, smoke, and salt are made in the ocean particularly good nuclei because of the absorbed water. Condensation also takes place when the moisture comes in contact with some colder object that may take place when the temperature is close to the dew point. Condensation therefore depends upon the air and cooling and the relatively humidity of the air. Condensation influenced by the volume of air, temperature, pressure, humidity, and condensation takes place. Number 1, when the temperature of air is reduced to dew the point and volume remaining constant. Number 2, when both of the volume temperature are reduced. Number 3, when the moisture is added to air through evaporation. However, the most favorable condition of condensation is a decrease in air temperature. After condensation, the water vapor or moisture in the atmosphere takes over one forms dew, frost, fog, clouds. Forms of condensation can be classified on the basis of temperature and location. Condensation takes place when the dew point is lower than the freezing point as well as the higher than freezing point. Precipitation. The process of continuous condensation in free air helps condensed particles and particles to grow in size. When the resistance of air falls to hold them against the gravity, they fall on the Earth's surface. So after the condensation of the water vapor, the release of moisture is known as precipitation. This may take place in the liquid or solid form. The precipitation in the water form is called rainfall. When the temperature is lower than 0 Celsius, precipitation takes place in a form of fine flakes of snow called snowfall. Moisture is released in the hexagonal crystals, and these crystals take a form of flakes of snow. Besides rain and snow, though the latter of limited is occurrence of the sporadic both time and space. Sleet is a frozen raindrop in refrozen melted snow water. One layer of air, when is the temperature above freezing point, overrides the sub-freezing layer near the ground. Sometimes drops of rain after being released by the clouds become solidified into small rounded solid pieces with ice called the hailstones. These are formed in rainwater passing through cold layers. Hailstones have several ceramic ice on it and other. World distribution of rainfall. Different places on Earth's surface receive different amounts of rainfall every year in the 2 different seasons. In general, as we proceed from one equator to the other, the rainfall goes decreasing steadily. The coastal areas of the world receive greater amounts of rainfall than the interior of the continents. The rainfall is more over the oceans than landmass over the world because of a greater source of water. On the basis of total amount of annual precipitation, major precipitation rimes of the world are identified as followers. The equatorial belt. The windward slopes of the mountain along the west coast in the cool temperature zone in the coastal areas of monsoon land receive heavy rainfall over 200 centimeters per aluminum, and Anuma interior continental area receives moderate rainfall varying 100 to 200 centimeters per annum. The coastal areas of the continents receive moderate amount of rainfall. The central parts of the tropical land and eastern and western interior parts temperature land receives rainfall varying from 10 centimeters, 50 centimeters, and 100 centimeters per annum. Our areas lying around the rainfall zone, our interior continents and high latitudes receive very slow and low rainfall, less than 50 centimeters per annum. Seasonal distribution of rainfall provide an important aspect to judge the effectiveness. In some regions, rainfall is distributed evenly throughout the year, such as equatorial belt in the western parts of cool temperature and regions.
Exercises 1. Multiple choice questions. Bit 1. Which of the following is the most important constituent of atmosphere for human beings? A. Water vapor. B. Nitrogen. C. Dust particle. D. Oxygen. Bit 2. Which one of the following process is responsible for transforming liquid into vapor? A. Condensation. B. Transpiration. C. Evaporation. D. Precipitation. Bit 3. The air that contains moisture to its full capacity. A. Relative humidity. B. Specific humidity. C. Absolute humidity. D. Saturated air. Bit 4. Which one of the following is the highest cloud in the sky? A. Sirius. B. Stratus. C. Nimbus. D. Cumulus. Question 2. Answer the following questions in about 30 words. Bit 1. Name the 3 types of precipitation. Bit 2. Explain relative humidity. Bit 3. Why does the amount of water vapor decrease rapidly with altitude? Bit 4. How are clouds formed? Classify them. Question 3. Answer the following questions in about 150 words. Bit 1. Discuss the salient features of the world distribution of precipitation. Bit 2. What are forms of condensation? Describe the process of dew and frost formation. Project work. Browse through the newspaper from 1st June to 31st December and note the news about extreme rainfall in different parts of the country.
Chapter 12. World Climate and Climate Change. The world climate can be studied by the organizing information data on climate and synthesizing them in smaller units of easier understanding, description, and analysis. 3 broad approaches from the adopted of classifying climate. These are empirical genetic applied. The empirical triangulation and condensation and classification is based on the observant data, particularly on temperature and precipitation. Genetic classification attempts to organize climates according to their specific causes. Applied classification is for specific purpose. The Köppen scheme of classification of climate. The widely used classification of climate is the empirical classification of climate scheme developed by V. Köppen. Köppen identified a close relationship between the distribution of vegetation and climate. He selected certain values of temperature and precipitation related to the distribution of vegetation and used these values of classifying the climates. In the empirical classification based on the mean annual and mean monthly temperature precipitation data, he introduced the use of capital and small letters to design the climate groups and types. Although developed in 1918, modification and modified over a period of time, Köppen's scheme is still popular in use. Koppen recognized 5 major climate groups, 4 of them based on the temperature and the precipitation. Table 12 lists the climate groups and their characteristics according to Koppen. The letters A, C, D, E denote humid climates and B, dry climates. The climate groups are subdivided into types and designed by small letters based on the seasonality of precipitation, temperature characteristics. The seasons are dryness indicated by the small letters F, M, W, and S, where F corresponds to no dry season. M, monsoon climate, W, winter dry season, the S for dry season. The small letters A, B, C, D refer to the degree of severality and for temperature. The B is for dry climates and subdivided using capital letters, S for steppe or semi-arid, and W for deserts. The climatic types are listed in 12.2, the distribution of climatic groups, and the types is shown in 12.1. Islands of the Easties. Significant amount of rainfall occurs in every month every year as the thunder shows in the afternoon. The temperature is uniformly high and the annual range of temperature is negligible, and the maximum temperature is around 30 Celsius to the minimum of 20 Celsius in the tropical green forest, and the dense canopy cover large biodiversity in the climate. Polar climates. The polar climates exist poleward beyond 70 latitude. Polar climates consist of 2 types, tundra and ice cap. The tundra climate is also called after the vegetation, low-growing mosses, leeches, and flowering plants. These regions permafrost when the subsoil is permanently frozen. The short growing season and water logging support only growing for plants. During the summer, the tundra regions have very long duration of daylight. Ice cap climate. The ice cap climate occurs over interior of Greenland and Antarctica. Even in the summer, the temperature is below freezing point. This area receives very little precipitation. The snow gets accumulated in the mountain pressure before the deformation of ice sheets, and they break. They are moved as icebergs in the float in the Antarctic and Antarctic waters. Plateau Station, Antarctic 79 South portray this climate. Global warming. Due to the presence of greenhouse gases, the atmosphere is behaved like a greenhouse. The atmosphere also transmits the incoming solar radiation but absorbs the vast majority of the long-wave radiation emitted upwards the Earth's surface, and the gases that absorb long waves radiation called the greenhouse gases that process the warm atmosphere often collectively referred the greenhouse effect. Greenhouse gases. Primarily, GHS is a concern of today are carbon dioxide, chlorofluorocarbons, methane, nitrous oxide, and the ozone. Some other gases such as nitric oxide and the carbon monoxide easily react to GHS and affect their concentration in the atmosphere. The effectiveness of any given GHS molecule will depend on its magnitude as it increases its concentration. The lifetime is the atmosphere and the wavelength of the radiation that is absorbed. The chlorofluorocarbons are highly effective. The ozone, in which absorbs ultraviolet radiation in the troposphere, is very effective in observing terrestrial radiation where they're present in lower troposphere. Another important point noted in the more GHS molecule remaining in the atmosphere, the longer it will take for the Earth's atmospheric system to recover from any change brought by the latter. The largest concentration of GHS in the atmosphere is carbon dioxide. The emission of CO2 is mainly by fossil fuels combustion. The forests and oceans sink in for carbon dioxide. This is another cause of serious concern for the world.
Efforts have already been initiated to control the emission of GHGs and to arrest the trend towards global warming. Let us hope the world community responds to this challenge and adopts a lifestyle that leaves behind a livable world for the generations to come. One of the major concerns of the world today is global warming. Let us look at how much the planet has warmed up from the temperature records. Temperature data are available from the middle of the 19th century, mostly from Western Europe. The reference period for this study is 1961 to 90. The temperature anomalies for the earlier and later periods are estimated from the average temperature for the period 1961 to 90. The annual average near surface area temperature of the world is approximately 14 degrees Celsius. The time series shows anomalies of annual near surface temperature over land from 1856 to 2000 relative to the period 1961 to 90 as normal for the globe. An increasing trend in temperature was discernible in the 20th century. The greatest warning of the 20th century was during the two periods 1901 to 44 and 1977 to 1999. Over each of these two periods, global temperatures rose about 0.4 degrees Celsius. In between, there was a slight cooling which was more marked in the northern hemisphere. The globally averaged annual mean temperature at the end of 20th century was about 0.6 degrees Celsius above the recorded at the end of the 19th century. The 7 warmest years during 1856 to 2000 were recorded in the last decade. The year 1998 was the warmest year, probably not only for the 20th century but also for the whole millennium. Exercises. Question 1. Multiple choice questions. Bit 1. Which one of the following is suitable for Koipen's A type of climate? A. High rainfall in all the months. B. Mean monthly temperature of the coldest month more than freezing point. C. Mean monthly temperature of all the months more than 18 degrees Celsius. D. Average temperature for all the months below 10 degrees Celsius. Bit 2. Koipen's system of classification of climates can be termed as A. Applied, B. Systematic, C. Genetic, D. Empirical. Bit 3. Most of the Indian peninsula will be grouped according to Koipen's system under Bit A. AF, Bit B. BSH, Bit C. CFB, Bit D. AM. Bit 4. Which one of the following years is supposed to have recorded the warmest temperature the world over? A. 1990, B. 1998, C. 1885, D. 1950. Bit 5. Which one of the following groups of 4 climates represents humid conditions? A. A, B, C, E, B. A, C, D, E, C. B, C, D, E, D. A, C, D, F. Question number 2. Answer the following questions in about 30 words. Bit 1. Which two climatic variables are used by Koipen for classification of the climate? Bit 2. How is the genetic system of classification different from the empirical one? Bit 3. Which types of climates have very low range of temperature? Bit 4. What type of climatic conditions would prevail if the sun spots increase? Question 3. Answer the following questions in about 150 words. Bit 1. Make a comparison of the climatic conditions between the A and B type of climate. Bit 2. What type of vegetation would you find in the C and A types of climate? Bit 3. What do you understand by the term greenhouse gases? Make a list of greenhouse gases. Project work. Collect information about Kyoto Declaration related to global climatic changes.
Unit 5. Water and Oceans. This unit deals with the hydraulical cycle, oceans, submarine relief, distribution of temperature and salinity, movements of ocean water waves, tides, and currents. Chapter 13. Water and Oceans. Can we think of life without water? It is said that the water is life. Water is an essential component of all life forms that exist over the surface of the earth. The creatures on Earth are lucky that it is a water planet, otherwise we would all have no existence. Water is a rare commodity in our solar system. There is no water on the sun or anywhere else in our solar system. The Earth fortunately has an abundant supply of water on its surface. Hence our planet is called the blue planet. The hydraulical cycle. Water is a cyclic source. It can be used and reused. Water also undergoes a cycle from the ocean to land and land to ocean. The hydraulical cycle describes the movement of water on, in, and above Earth. The water cycle has been working for billions of years, and all the life on Earth depends on it. Next to air, water is the most important element required for the existence of life on Earth. The distribution of water on Earth is quite uneven. Many locations have plenty of water, while others have very limited quantity. The hydraulical cycle is the circulation of water within the Earth's hydrosphere in different forms, the liquid, solid, and the gaseous phases. It also refers to the continuous exchange of water between the oceans, atmosphere, land surface, and subsurface, and the organisms. Table 13.1 shows the distribution of water on the surface of the Earth. About 71% of the planetary water is found in the oceans. The remaining is held as fresh water in glaciers and ice caps, groundwater sources, lakes, soil moisture, atmosphere, streams, and within life. Nearly 59% of the water that falls on land returns to the atmosphere through evaporation from over the oceans as well as from other places. The remainder runs off on the surface, infiltrates into the ground, or a part of it becomes the glacier. It is to be noted that renewable water on Earth is constant while the demand is increasing tremendously. This leads to water crisis in different parts of the world, spatially and temporally. The pollution of river waters has further aggravated the crisis. How can you intervene in improving the water quality and augmenting the available quantity of water? Relief of the ocean floor. The oceans are confined to the great depressions of the Earth's outer layer. In this section, we shall see the nature of the ocean basins of the Earth and their topography. The oceans, unlike the continents, merge so naturally into one another that it is hard to demarcate them. The geographers have divided the oceanic part of the Earth into 5 oceans, namely the Pacific, the Atlantic, the Indian, Southern Ocean, and the Arctic. The various seas, bays, gulfs, and other inlets are a part of these 4 large oceans. A major portion of the ocean floor is found between 3 to 6 kilometers below sea level. The land under the waters of the oceans, that is, the ocean floor, exhibits complex and varied features as those observed over land. The floors of the ocean are rugged with the world's largest mountain ranges, deepest trenches, and largest plains. These features are formed, like those of the continents, by the factors of tectonic, volcanic, and depositional processes. Divisions of the ocean floors. The ocean floors can be divided into 4 major divisions: the continental shelf, the continental slope, the deep sea plain, the oceanic deeps. Besides these divisions, there are also major and minor relief features in the ocean floors like ridges, hills, seamounts, guyots, trenches, canyons, etc. The continental shelf. The continental shelf is the extended margin of each continent occupied by relatively shallow seas and gulfs. It is the shallowest part of the ocean, showing an average gradient of 1 degree or even less. The shelf typically ends at the very steep slope called the shelf break. The width of the continental shelves vary from one ocean to another. The average width of a continental shelf is about 80 kilometers. The shelves are almost absent or very narrow along some of the margins like the coast of Chile, the west coast of Sumatra, etc. On the contrary, the Siberian Shelf in the Arctic Ocean, the largest in the world, stretches to 1,500 kilometers in width. The depth of the shelves also varies. It may be as shallow as 30 meters in some areas, while in some areas it is as deep as 600 meters. The continental shelves are covered with variable thickness of sediments brought down by rivers, glaciers, and wind from the land and distributed by waves and currents. Massive sedimentary deposits received over a long time by the continental shelves become the source of fossil fuels. Continental slope. The continental slope connects the continental shelf and the ocean basins. It begins where the bottom of the continental shelf sharply drops off into a steep slope. The gradient of the slope region varies between 2 to 5 degrees. The depth of the slope region varies between 200 to 3,000 meters. The slope boundary indicates the end of the continent. Canyons and trenches are observed in this region. Deep sea plain. Deep sea plains are gently sloping areas of the ocean basins. These are the flattest and smoothest regions of the world. The depths vary between 3,000 to 6,000 meters. These plains are covered with fine-grained sediments like clay and silt. Oceanic deeps or trenches. These areas are the deepest parts of the oceans. The trenches are relatively steep-sided, narrow basins. They are some 3 to 5 kilometers deeper than the surrounding ocean floor. They occur at the bases of a continental slopes and along island arcs and are associated with active volcanoes and strong earthquakes. This is why they are very significant in the study of plate movements. As many as 57 deeps have been explored so far, of which 32 are in the Pacific Ocean, 19 in the Atlantic Ocean, and 6 in the Indian Ocean. Minor relief features. Apart from the above-mentioned major relief features of the ocean floor, some minor but significant features predominate in different parts of the oceans. Mid-oceanic ridges. A mid-oceanic ridge is composed of two chains of mountains separated by a large depression. The mountain ranges can have peaks as high as 2,500 meters, and some even reach above the ocean surface. Iceland, a part of the mid-Atlantic ridge, is an example. Seamount. It is a mountain with pointed summits rising from the seafloor that does not reach the surface of the ocean. Seamounts are volcanic in origin. These can be 3,000 to 4,500 meters tall. The Emperor Seamount, an extension of the Hawaiian Islands in the Pacific Ocean, is a good example. Submarine canyons. These are deep valleys, some comparable to the Grand Canyon of the Colorado River. They are sometimes found cutting across the continental shelves and slopes, often extending from the mouths of the large rivers. The Hudson Canyon is the best-known submarine canyon in the world. Guyots. It is a flat-topped seamount. They show evidences of gradual subsidence going through stages to become flat-topped submerged mountains. It is estimated that more than 10,000 seamounts and guyots exist in the Pacific Ocean alone. Atoll. These are low islands found in the tropical oceans consisting of coral reefs surrounded by a central depression. It may be part of a sea or sometimes form enclosing a fresh, brackish, and highly saline water body. Temperature of ocean waters. This section deals with the spatial and vertical variations of temperature in various oceans. Ocean waters get heated up by the solar energy just as land. The process of heating and cooling of the oceanic water is slower than land. Factors affecting temperature distribution. The factors which affect the distribution of temperature of ocean water are: latitude, the temperature of the surface water decreases from the equator towards the poles because of the amount of insolation decreases poleward. Unequal distribution of land and water. The oceans in the northern hemisphere receive more heat due to their contact with the larger extent of land than the oceans in the southern hemisphere. Prevailing wind. The winds blowing away from the land towards the oceans drive warm surface water away from the coast, resulting in the upwelling of cold water from below. It results in the longitudinal variation in temperature. Contrary to this, the onshore winds pile up warm water near the coast, and this raises the temperature. Ocean currents. Warm ocean currents raise the temperature in cold areas, while the cold currents decrease the temperature in the warm ocean areas. Gulf Stream raises the temperature near the eastern coast of North America and the western coast of Europe, while the Labrador Current lowers the temperature near the northeast coast of North America. All these factors influence the temperature of the ocean currents locally. The enclosed seas in the low latitudes record relatively higher temperature than the open seas, whereas the enclosed seas in the high latitudes have lower temperature than the open seas. Horizontal and vertical distribution of temperature. The temperature depth profile for the ocean water shows how the temperature decreases with the increasing depth. The profile shows a boundary region between the surface waters of the ocean and the deep layers. The boundary usually begins around 100 to 400 meters below the sea surface and extends several hundred meters downward. The boundary region from where this is a rapid decrease of temperature is called thermocline. About 90% of the total volume of water is found below the thermocline in the deep ocean. In this zone, temperatures approach 0 degrees. The temperature structure of oceans over middle and low latitudes can be described as a three-layer system from surface to the bottom. The first layer represents the top layer of warm oceanic water, and it is about 500 meters thick, with temperatures ranging between 20 degrees to 25 degrees Celsius. This layer within the tropical region is present through the year, but in mid-latitudes it develops only during summer. The second layer, called the thermocline layer, lies below the first layer and is characterized by the rapid decrease in temperature with increasing depth. Thermocline is 500 to 1,000 meters thick. The third layer is very cold and extends up to the deep ocean floor. In the Arctic and Antarctic circles, the surface water temperatures are close to 0 degrees, and so the temperature change with the depth is very slight. Here, only one layer of cold water exists, which extends from the surface to the deep ocean floor. The average temperature of surface water of the oceans is about 27 degrees Celsius, and it gradually decreases from the equator towards the poles. The rate of decrease of temperature with increasing latitude is generally 0.5 Celsius per latitude. The average temperature is around 22 degrees Celsius at 20 degrees latitudes, 14 degrees Celsius at 40 degree latitudes, and 0 degrees Celsius near the poles. The oceans in the northern hemisphere record relatively higher temperature than in the southern hemisphere. The highest temperature is not recorded at the equator, but slightly towards the north of it. The average annual temperatures for the northern and southern hemisphere are around 19 degrees Celsius and 16 degrees Celsius respectively. This variation is due to the unequal distribution of land and water in the northern and southern hemispheres. Figure 13.4 shows the spatial pattern of surface temperature of the oceans. It is a well-known fact that the maximum temperature of the oceans is always at the surfaces because they directly receive the heat from the sun, and the heat is transmitted to the lower sections of the oceans through the process of convection. It results into a decrease of temperature with the increasing depth, but the rate of decrease is not uniform though. The temperature falls rapidly up to the depth of 200 meters, and thereafter the rate of decrease of temperature is slowed down. Salinity of ocean waters. All waters in nature, whether rainwater or ocean water, contain dissolved mineral salts. Salinity is the term used to define the total content of dissolved salts in the seawater. It is calculated as the amount of salt dissolved in 1,000 gm seawater. It is usually expressed as part of per 1,000 or ppt. Salinity is an important property of seawater. Salinity of 24.7 degrees has been considered as the upper limit to demarcate brackish water. Factors affecting ocean salinity are mentioned below. The salinity of water in the surface layer of oceans depend mainly on evaporation and precipitation. Surface salinity is greatly influenced in the coastal regions by the freshwater flow from rivers, and in polar regions by the process of freezing and thawing of ice. Wind also influences salinity of an area by transferring water to other areas. The ocean currents contribute to the salinity variations. Salinity, temperature, and density of water are interrelated. Hence, any change in the temperature or density influences the salinity of water in an area. Horizontal distribution of salinity. The salinity for normal open ocean ranges between 33 degrees and 37 degrees. In the landlocked Red Sea, it is as high as 41 degrees, while in estuaries in the Arctic, the salinity fluctuates from 0 to 35 degrees seasonally. In hot and dry regions where evaporation is high, the salinity sometimes reaches to 70 degrees. The salinity variation in the Pacific Ocean is mainly due to its shape and larger area extent. Salinity decreases from 35 degrees to 31 degrees on the western parts of the northern hemisphere because of the influx of melted water from the Arctic region. In the same way, after 15 degrees to 20 degrees south, it decreases to 30 degrees. The average salinity of the Atlantic Ocean is around 36 degrees. The highest salinity is recorded to be between 15 degrees and 20 degrees latitudes. Maximum salinity, 37 degrees, is observed between 20 degrees north and 30 degrees north and 20 degrees west to 60 degrees west. It gradually decreases towards the north. The North Sea, in spite of its location in higher latitudes, records higher salinity due to more saline water brought by the northern Atlantic drift. Baltic Sea records low salinity due to the influx of river waters in large quantity. The Mediterranean Sea records higher salinity due to the high evaporation. Salinity is, however, very low in the Black Sea due to enormous freshwater influx by rivers. See the atlas to find out the rivers joining Black Sea. The average salinity of the Indian Ocean is 35 degrees. The low salinity trend is observed in the Bay of Bengal due to influx of river water. On the contrary, the Arabian Sea shows higher salinity due to high evaporation and low influx of fresh water. Figure 13.5 shows the salinity of the world's oceans. Vertical distribution of salinity. Salinity changes with depth, but the way it changes depends upon the location of the sea. Salinity at the surface increases by the loss of water to ice or evaporation, or decreased by the input of fresh waters, such as from the rivers. Salinity at the depth is very much fixed because there is no way that the water is lost or the salt is added. There is a marked difference in salinity between the surface zones and the deep zones of the oceans. The lower salinity water rests above the higher salinity dense water. Salinity generally increases the depth, and there is a distinct zone called the Halos line where salinity increases sharply. Other factors being constant, increasing salinity of seawater causes its density to increase. High salinity seawater generally sinks below the low salinity seawater. This leads to stratification by salinity. Exercises. Number 1. Identify the element which is not part of the hydraulical cycle. A. Evaporation. B. Hydration. C. Precipitation. And D. Condensation. Number 2. The average depth of the continental slope varies between A. 2 to 20 meters, B. 200 to 2,000 meters, C. 20 to 200 meters, or D. 2,000 to 20,000 meters. Number 3. Which one of the following is not a minor relief feature in the ocean? A. Seamount. B. Atoll. C. Oceanic deep. And D. Guyot. Number 4. Salinity is expressed as the amount of salt in grams dissolved in seawater per A. 10 grams, B. 1,000 gm, C. 100 gm, or D. 10,000 gm. Number 5. Which of the following is the smallest ocean? A. The Indian Ocean. B. The Arctic Ocean. C. The Atlantic Ocean. Or D. The Pacific Ocean. Answer the following questions in about 30 words. Number 1. Why do we call the Earth a blue planet? Number 2. What is a continental margin? Number 3. List out the deepest trenches of various oceans. Number 4. What is a thermocline? Number 5. When you move into the ocean, what thermal layers would you encounter? Why the temperature varies with depth? Number 5. Number 6. What is the salinity of seawater? Answer the following questions in about 150 words. Number 1. How are various elements of the hydraulical cycle interrelated? Number 2. Examine the factors that influence the temperature distribution of the oceans. Project work. Number 1. Consult the atlas and show ocean floor relief on the outline of the world map. Number 2. Identify the areas of the mid-ocean ridges, oceanic ridges from the Indian Oceans. Chapter 14. Movements of the ocean water. The ocean water is dynamic. Its physical characteristics like temperature, salinity, density, and the external forces like of the sun, moon, and the winds influence the movement of ocean water. The horizontal and vertical motions are common in ocean water bodies. The horizontal motion refers to the ocean currents and waves. The vertical motion refers to tides. The ocean currents are the continuous flow of a huge amount of water in a definite direction, while the waves are the horizontal motion of water. Water moves ahead from one place to another through ocean currents, while the water in the waves does not move, but the wave trains move ahead. The vertical motion refers to the rise and fall of water in the oceans and seas. Due to attraction of the sun and the moon, the ocean water is raised up and falls down twice a day. The upwelling of cold water from subsurface and the sinking of the surface water are also forms of vertical motion of water. Waves. Waves are actually the energy, not the water as such, which moves across the ocean surface. Water particles only travel in a small circle as a wave passes. Wind provides energy to the waves. Wind causes waves to travel in the ocean and the energy is released on shorelines. The motion of the surface water seldom affects the stagnant deep bottom water of the oceans. As a wave approaches the beach, it slows down. This is due to the friction occurring between the dynamic water and the seafloor. And when the depth of the water is less than half the wavelength of the wave breaks. The largest waves are found in the open oceans. Waves continue to grow larger as they move and absorb energy from the wind. Most of the waves are caused by the wind driving against water. When a breeze of 2 knots or less blows over calm water, small ripples form and grow as the wind speed increases until white caps appear in the breaking waves. Waves may travel thousands of kilometers before rolling ashore, breaking and dissolving as surf. A wave's size and shape reveal its origin. Steep waves are fairly young ones and are probably formed by local wind. Slow and steady waves originate from far away places, possibly from another hemisphere. The maximum wave height is determined by the strength of the wind, how long it blows, and the area over which it blows in a single direction. Waves travel because wind pushes the water body in its course while gravity pulls the crest of the waves downward. The following water pushes the former troughs upward and the wave moves into a new position. The actual motion of the water beneath the waves is circular. It indicates that things are carried up and forward as the wave approaches and down and back as it passes. Characteristics of waves. Wave crest and trough. The highest and lowest points of the wave are called the crest and trough, respectively. Wave height. It is the vertical distance from the bottom of the trough to the top of the crest of the wave. Wave amplitude. It is 1/2 of the wave height. Wave period. It is merely the time interval between 2 successive wave crests or troughs as they pass a fixed point. Wavelength. It is the horizontal distance between 2 successive crests. Wave speed. It is the rate at which the wave moves through the water and is measured in knots. Wave frequency. It is the number of waves passing a given point during a non-1 second time interval. Tides. The periodical rise and fall of the sea level once or twice a day, mainly due to the attraction of the sun and moon, is called a tide. Movement of water caused by meteorology effects are called surges. Surges are not regular like tides. The study of tides is very complex, spatially and temporally, as it has great variations in frequency, magnitude, and height. The moon's gravitational pull, to a great extent, and to a lesser extent the sun's gravitational pull, are the major causes for the occurrence of tides. Another factor is centrifugal force, which is the force that acts to counterbalance the gravity. Together, the gravitational pull and the centrifugal force are responsible for creating the 2 major tidal bulges on the Earth. On the side of the Earth facing the moon, a tidal bulge occurs, while on the opposite side, through the gravitational attraction of the moon, is less as it is farther away. The centrifugal force causes the tidal bulge on the other side. The tide generating force is the difference between these 2 forces, the gravitational attraction of the moon and the centrifugal force. On the surface of the Earth, nearest the moon, pull or the attractive force of the moon is greater than the centrifugal force, and so there is a net force causing a bulge towards the moon. On the opposite side of the Earth, the attractive force is less, as it is farther away from the moon. The centrifugal force is dominant. Hence, there is a net force away from the moon. It creates the second bulge away from the moon. On the surface of the Earth, the horizontal tide generating forces are more important than the vertical forces in generating the tidal bulges. The tidal bulges on wide continental shelves have greater height. When tidal bulges hit the mid-oceanic islands, they become low. The shape of the bays and estuaries along a coastline can also magnify the intensity of tides. Funnel-shaped bays are greatly changing tidal magnitudes. When the tide is channeled between islands or into bays and estuaries, they are called tidal currents. Tides of Bay of Fundy, Canada. The highest tides in the world occur in the Bay of Fundy in Nova Scotia, Canada. The tidal bulge is 15 to 16 meters because there are 2 high tides and 2 low tides every day. Then a tide must come in within about a 6-hour period. As a rough estimate, the tide rises above 240 centimeters an hour. If you had walked down a beach with a steep cliff alongside, make sure you watch the tides. If you walk for about an hour, then notice that the tide is coming in. The water will be over your head before you get back to where you started. Types of tides. Tides vary in their frequency, direction, and movement from place to place and also from time to time. Tides may be grouped into various types based on their frequency of occurrence in 1 day or 24 hours or based on their height. Tides based on frequency. Semi-diurnal tide, the most common tidal pattern featuring 2 high tides and 2 low tides each day. The successive high or low tides are approximately of the same height. Diurnal tide. There is only 1 high tide and 1 low tide during each day. The successive high and low tides are approximately of the same height. Mixed tide. Tides of variations in height are known as mixed tides. These tides generally occur along the west coast of North America and on many islands of the Pacific Ocean. Tides based on the sun, moon, and earth positions. The height of rising water varies appreciably depending on the position of the sun and moon with respect to the earth. Spring tides and neap tides come under this category. Spring tides. The position of both the sun and moon in relation to the earth has direct bearing on tide height. When the sun and the moon and the earth are in a straight line, the height of the tide will be higher. These are called spring tides, and they occur twice a month on one full moon period and another during new moon period. Neap tides. Normally there is a 7-day interval between the spring tides and neap tides. At this time, the sun and moon are at right angles to each other, and the forces of the sun and moon tend to counteract one another. The moon's attraction, though more than twice as strong as the sun's, diminished by the counteracting force of the sun's gravitational pull. Once in a month, when the moon's orbit is closest to the earth, unusually high and low tides occur. During this time, the tide range is greater than normal. 2 weeks later, the moon is farthest from the earth, and the moon's gravitational force is limited and the tide ranges are less than their average heights. When the earth is closest to the sun, around 3rd January every year, the tide ranges are also much greater, with unusually high and unusually low tides. When the earth is farthest from the sun, around 4th July each year, the tide ranges are much less than average. The time between the high tide and low tide, when the water level is falling, is called the ebb. The time between the low tide and high tide, when the tide is rising, is called the flow or flood. Importance of tides. Since tides are caused by the earth, moon, sun positions, which are known accurately, the tides can be predicted well in advance. This helps the navigators and fishermen plan their activities. Tidal flows are of great importance in navigation. Tidal heights are very important, especially harbors near rivers and within estuaries having shallow bars at the entrance, which prevent ships and the boats from entering into the harbor. Tides are also helpful in desilting the sediments and in removing polluted water from river estuaries. Tides are usually used to generate electrical power. A 3 MW tide power project at Durga Duani in Sundarbans of West Bengal is underway. Ocean currents. Ocean currents are like river flow in oceans. They represent a regular volume of water in a definite path and direction. Ocean currents are influenced by two types of forces, namely primary forces that initiate the movement of water and secondary forces that influence the currents to flow. The primary forces that influence the currents are heating by solar energy, wind, gravity, and the Coriolis force. Heating by solar energy causes the wind to expand. That is why near the equator, the ocean water is about 8 centimeters higher in level than in middle latitudes. This causes a very slight gradient, and water tends to flow down the slope. Wind blowing on the surface of the ocean pushes the water to move. Friction between the wind and the water surface affects the movement of the water body in its course. Gravity tends to pull the water down the pile and create gradient variation. The Coriolis force intervenes and causes the water to move to the right in the northern hemisphere and to the left in the southern hemisphere. These large accumulations of water and the flow around them are called gyres. These produce large circular currents in all the ocean bases. Characteristics of ocean currents. Currents are referred to by their drift. Usually the currents are strongest near the surface and may attain speeds over 5 knots. At depths, currents are known generally slow with their speeds less than 0.5 knots. We refer to the speed of the current as its drift. Drift is measured in terms of knots. The strength of a current refers to the speed of the current. A fast current is considered strong. A current is usually strongest at the surface and decreases in strength with depth. Most currents have speeds less than or equal to 5 knots. Differences in water density affect vertical mobility of ocean currents. Water with high salinity is denser than water with low salinity, and in the same way, cold water is denser than warm water. Denser water tends to sink, while relatively lighter water tends to rise. Colder water ocean currents occur when the cold water at the poles sinks and slowly moves towards the equator. Warm water currents travel out from the equator along the surface, flowing towards the poles to replace the sinking cold water. Types of ocean currents. The ocean currents may be classified based on their depth as the surface currents and deep water currents. Surface currents constitute about 10% of all the water in the ocean. These waters are the upper 400 meters of the ocean. Deep water currents make up the other 90% of the ocean water. These waters move around the ocean basins due to variations in the density and gravity. Deep waters sink into the deep ocean basins at high latitudes where the temperatures are cold enough to cause the density to increase. Ocean currents can be classified based on temperature as cold currents and warm currents. Cold currents bring the cold water into warm water areas. These currents are usually found on the west coast of the continents in the low and middle latitudes, and on the east coast in the higher latitudes in the northern hemisphere. Warm currents bring warm water into cold water areas and are usually observed on the east coast of continents in the low and middle latitudes. In the northern hemisphere, they are found on the west coast of continents in high latitudes. Major ocean currents are greatly influenced by the stresses exerted by the prevailing winds and the Coriolis force. The oceanic circulation pattern roughly corresponds to the Earth's atmospheric circulation pattern. The air circulation over the oceans in the middle latitudes is mainly anticlonic. The ocean circulation pattern also corresponds with the same at higher latitudes, where the wind flows is mostly cyclonic. The oceanic circulation follows this pattern. In regions of pronounced monsoonal flow, the monsoon winds influence the currents of movements. Due to the Coriolis force, the warm currents from low latitudes tend to move to the right in the northern hemisphere and to their left in the southern hemisphere. The oceanic circulation transports heat from one latitude belt to another in a manner similar to the heat transported by the general circulation of the atmosphere. The cold waters of the Arctic and Antarctic circles move towards warm water in tropical and equatorial regions, while the warm waters of the low latitudes move polewards. The major currents in the different oceans are shown in Figure 14.3. Prepare a list of currents which are found in the Pacific, Atlantic, and Indian Oceans. How is the movement of currents influenced by prevailing winds? Give some examples from Figure 14.3. Effects of ocean currents. Ocean currents have a number of direct and indirect influences on human activities. West coasts of the continents in tropical and subtropical latitudes are bordered by cool waters. Their average temperatures are relatively low with a narrow diurnal and annual ranges. There is fog, but generally the areas are arid. West coasts of the continents in the middle and higher latitudes are bordered by the warm waters which cause a distinct marine climate. They are characterized by cool summers and relatively mild winters with a narrow annual range of temperatures. Warm currents flow parallel to the east coast of the continents in tropical and subtropical latitudes. This results in warm and rainy climates. These areas lie in the western margins of the subtropical anticyclones. The mixing of warm and cold currents help to replenish the oxygen and favor the growth of planktons, the primary food for fish population. The best fishing grounds of the world exist mainly in these mixing zones. Exercises. Number 1. Upward and downward movement of ocean water is known as the A. Tide, B. Current, C. Wave, or D. None of the above. Number 2. Spring tides are caused A. As a result of the moon and the sun pulling the earth gravitationally in the same direction. B. As a result of the moon and the sun pulling the earth gravitationally in the opposite direction. C. Indentation in the coastline. Or D. None of the above. Number 3. The distance between the Earth and the Moon is minimum when the Moon is in A. Aphelion, B. Perigee, C. Perihelion, or D. Apogee. Number 4. The Earth reaches its perihelion in A. October, B. September, C. July, or D. January. Answer the following questions in about 30 words. Number 1. What are waves? Number 2. Where do waves in the ocean get their energy from? Number 3. What are tides? Number 4. How are tides caused? And number 5. How are tides related to navigation? Answer the following questions in about 150 words. Number 1. How do currents affect the temperature? How does it affect the temperature of coastal areas in the Northwest Europe? Number 2. What are the causes of currents? Project work. Number 1. Visit a lake or a pond and observe the movement of waves. Throw a stone and notice how waves are generated. Number 2. Take a globe and a map showing the currents of the oceans. Discuss why certain currents are warm or cold and why they deflect in certain places and examine the reasons.
Unit 6, Life on the Earth. This unit deals with biosphere, importance of plants and other organisms, ecosystems, biogeochemical cycle, and ecological balance, biodiversity, and conservation. Chapter 15, Life on the Earth. By now you might have realized that all units of this book have acquainted you with the three major realms of the environment, that is, the lithosphere, the atmosphere, and the hydrosphere. You know that living organisms of the Earth, constituting the biosphere, interact with other environmental realms. The biosphere includes all the living components of the Earth. It consists of all plants and animals, including microorganisms that live on the planet Earth, and their interactions with the surrounding environment. Most of the organisms exist on the lithosphere and/or the hydrosphere, as well as in the atmosphere. There are also many organisms that move freely from one realm to the other. Life on the Earth is found almost everywhere. Living organisms are found from the poles to the equator, from the bottom of the sea to several kilometers in the air, from freezing waters to dry valleys, from under the sea to underground water lying below the Earth's surface. The biosphere and its components are very significant elements of the environment. These elements interact with other components of the natural landscape such as land, water, and soil. They are also influenced by the atmospheric elements such as temperature, rainfall, moisture, and sunlight. The interactions of biosphere with land, air, and water are important to the growth, development, and evolution of the organism. Ecology. You have been reading about ecological and environmental problems in newspapers and magazines. Have you ever thought of what ecology is? The environment, as you know, is made up of abiotic and biotic components. It would be interesting to understand how the diversity of life forms is maintained to bring a kind of balance. This balance is maintained in a particular proportion so that a healthy interaction between the biotic and abiotic components goes on. The term ecology is derived from the Greek word ekos, meaning house, combined with the word logy, meaning the science of, or the study of. Literally, ecology is the study of the earth as a household of plants, human beings, animals, and microorganisms. They all live together as interdependent components. A German zoologist, Ernest Haeckel, who used the term as ecology in 1869, became the first person to use the term ecology. The study of interactions between life forms, biotic, and the physical environment, abiotic, is the science of ecology. Hence, ecology can be defined as a scientific study of the interactions of organisms with their physical environment and with each other. The interactions of a particular group of organisms with abiotic factors within a particular habitat, resulting in clearly defined energy flows and material cycles on land, water, and air, are called ecological systems. A habitat in the ecological sense is the totality of the physical and chemical factors that constitute the general environment. A system consisting of biotic and abiotic components is known as ecosystem. All these components in ecosystem are interrelated and interact with each other. Different types of ecosystems exist with varying ranges of environmental conditions where various plants and animal species have got adapted through evolution. This phenomenon is known as ecological adaptation. Types of ecosystems. Ecosystems are of two major types, terrestrial and aquatic. Terrestrial ecosystem can further be classified into biomes. A biome is a plant and animal community that covers a large geographical area. The boundaries of different biomes on land are determined mainly by climate. Therefore, a biome can be defined as the total assemblage of plant and animal species interacting within specific conditions. These include rainfall, temperature, humidity, and soil conditions. Some of the major biomes of the world are forest, grassland, desert, and tundra biomes. Aquatic ecosystems can be classed as marine and freshwater ecosystems. Marine ecosystem includes the oceans, estuaries, and coral reefs. Freshwater ecosystem includes lakes, ponds, streams, marshes, and bogs. Structure and functions of ecosystems. The structure of an ecosystem involves a description of the available plant and animal species. From a structural point of view, all ecosystems consist of abiotic and biotic factors. Abiotic factors include rainfall, temperature, sunlight, atmospheric humidity, soil conditions, inorganic substances, carbon dioxide, water, nitrogen, calcium, phosphorus, potassium, etc. Biotic factors include the producers, the consumers, primary, secondary, tertiary, and the decomposers. The producers include all the green plants, which manufacture their own food through photosynthesis. The primary consumers include herbivorous animals like deer, goats, mites, and all plant-eating animals. The carnivores include all the flesh-eating animals like snakes, tigers, and lions. Certain carnivores that feed on also carnivores are known as top carnivores like hawks and mongooses. Decomposers are those that feed on dead organisms, for example scavengers like vultures and crows, and for the breaking down of the dead matter by other decomposing agents like bacteria and various microorganisms. The producers are consumed by the primary consumers, whereas the primary consumers are, in turn, being eaten by the secondary consumers. Further, the secondary consumers are consumed by the tertiary consumers. The decomposers feed on the dead at each and every level. They change them into various substances such as nutrients, organic and inorganic salts essential for soil fertility. Organisms of an ecosystem are linked together through a food chain. For example, a plant eating a beetle feeding on a paddy stalk is eaten by a frog, which in turn eaten by a snake, which is then consumed by a hawk. This sequence of eating and being eaten and the resultant transfer of energy from one level to another is known as the food chain. Transfer of energy that occurs during the process of a food chain from one level to another is known as flow of energy. However, food chains are not isolated from one another. For example, a mouse feeding on grain may be eaten by different secondary consumers, carnivores, and these carnivores may be eaten by other tertiary consumers, top carnivores. In such situations, each of the carnivores may consume more than one type of prey. As a result, the food chains get interlocked with one another. This interconnecting network of species is known as food web. Generally, two types of food chains are recognized: grazing food chain and detritus food chain. In a grazing food chain, the first level starts with plants as producers and ends with carnivores as consumers at the last level, with herbivores being at the intermediate level. There is a loss of energy at each level, which may be through respiration, excretion, or decomposition. The levels involved in a food chain range between 3 to 5, and energy is lost at each level. A detritus food chain is based on autotrophs energy capture initiated by grazing animals and involves the decomposition or breaking down of organic wastes and dead matter derived from the grazing food chain. Types of biomes. In the earlier paragraphs, you have learned the meaning of the term biome. Let us now try to identify the major biomes of the world. There are 5 major biomes: forest, desert, grassland, aquatic, and altitudinal biomes. Some features of these biomes are given in Table 15.1. Biogeochemical cycles. The sun is the basic source of energy on which all life depends. This energy initiates life processes in the biosphere through photosynthesis, the main source of food and energy for green plants. During photosynthesis, carbon dioxide is converted into organic compounds and oxygen. Out of the total solar insolation that reaches the Earth's surface, only a very small fraction, 0.1%, is fixed in photosynthesis. More than half is used for plant respiration, and the remaining part is temporarily stored or is shifted to other portions of the plant. Life on Earth consists of a great variety of living organisms. These living organisms exist and survive in a diversity of associations. Such survival involves the presence of systemic flows, such as flows of energy, water, and nutrients. These flows show variations in different parts of the world, in different seasons of the year, and under varying local circumstances. Studies have shown that for the last 1 billion years, the atmosphere and hydrosphere have been composed of approximately the same balance of chemical components. This balance of the chemical elements is maintained by a cyclic passage through the tissues of plants and animals. The cycle starts by absorbing the chemical elements by the organism and is returned to the air, water, and soil through decomposition. These cycles are largely energized by solar insolation. These cyclic movements of chemical elements of the biosphere between the organism and the environment are referred to as biogeochemical cycles. Bio refers to living organisms and geo to rocks, soil, air, and water of the earth. There are 2 types of biogeochemical cycles: the gaseous and the sedimentary cycle. In the gaseous cycle, the main reservoir of nutrients is the atmosphere and the ocean. In the sedimentary cycle, the main reservoir is the soil and the sedimentary and other rocks of the Earth's crust. Table 15.1 World Biomes. Biomes: forest, subtypes: A tropical, 1 equatorial, 2 deciduous, B temperate, C boreal. Regions: A1 10 degrees north to south, A2 10 degrees to 25 degrees north to south, B eastern North America, New England, Asia, western and central Europe, C broad belt of Eurasia and North America, parts of Siberia, Alaska, Canada, and Scandinavia. Climatic characteristics: A1 temperature 20 to 25 degrees Celsius, evenly distributed. A2 temperature 25 to 30 degrees Celsius, rainfall average annual 1000 millimeters seasonal. B temperature 20 to 30 degrees Celsius, rainfall evenly distributed, 750 to 1,500 millimeters, well-defined seasons, and distinct winter. C. Short, moist, moderately warm summers and long, cold, dry winter. Very low temperatures, precipitation mostly snowfall, 400 to 1,000 millimeters. Soil, A1 acidic, poor in nutrients, A2 rich in nutrients, B fertile, enriched with decaying litter, C acidic and poor in nutrients, thin soil cover. Flora and fauna. A1 multi-layered canopy, tall and large trees, A2 less dense trees of medium height, many varieties coexist. Insects, bats, birds, and mammals are common species in both. Moderately dense, broad-leaved trees with less diversity of plant species. Oak, beech, maple, etc. are some common species. Squirrels, rabbits, skunks, birds, black bears, mountain lions, etc. C. Evergreen conifers like pine, fir, and spruce, etc. Woodpeckers, hawks, bears, wolves, deers, hares, and bats are common animals. Biomes, desert. Subtypes: A. Hot and dry desert, B. Semi-arid desert, C. Coastal desert, D. Cold desert. Regions: A. Sahara, Kalahari, Marustali, Rub el Khali. B. Marginal areas of hot deserts, C. Atacama, D. Tundra climatic regions. Climatic characteristics: A. Temperature 20 to 45 degrees Celsius, B. 21 to 38 degrees Celsius, C. 15 to 35 degrees Celsius, D. 2 to 25 degrees Celsius. A to D. Rainfall is less than 50 millimeters. Soil: rich in nutrients with little or no organic matter. Flora and fauna: scanty vegetation, few large mammals, insects, reptiles, and birds. D. Rabbits, rats, antelopes, and ground squirrels. Biomes, grassland. Subtypes: A. Tropical savanna, B. Temperate steppe. Regions: A. Large areas of Africa, Australia, South America, and India, B. Parts of Eurasia and North America. Climatic characteristics: A. Warm, hot climates, rainfall 500 to 1,250 millimeters. B. Hot summers and cold winter, rainfall 500 to 900 millimeters. Soil: A. Porous with thin layer of humus, B. Thin flocculated soil rich in bases. Flora and fauna: A. Grasses, trees and large shrubs absent. Giraffes, zebras, buffaloes, leopards, hyenas, elephants, mice, moles, snakes, and worms, etc. are common animals. B. Grasses, occasional trees such as cottonwoods, oaks, and willows. Gazelles, zebras, rhinoceros, wild horses, lions, varieties of birds, worms, snakes, etc. are common animals. Biomes, aquatic. Subtypes: A. Freshwater, B. Marine. Regions: A. Lakes, streams, rivers, and wetlands, B. Oceans, coral reefs, lagoons, and estuaries. Climatic characteristics: A to B. Temperatures vary widely with cooler air temperatures and high humidity. Soil: A. Water, swamps, and marshes, B. Water, tidal swamps, and marshes. Flora and fauna: algal and other aquatic and marine plant communities with varieties of water-dwelling animals. Biomes, altitudinal. Subtypes: none. Regions: slopes of high mountain ranges like the Himalayas, the Andes, and the Rockies. Climatic characteristics: temperature and precipitation vary depending upon latitudinal zone. Soil: regolith over slopes. Flora and fauna: deciduous to tundra vegetation, varying according to altitude. The water cycle: all living organisms, the atmosphere, and the lithosphere maintain between them a circulation of water in solid, liquid, or gaseous form, referred to as the water or hydrologic cycle. The carbon cycle: carbon is one of the basic elements of all living organisms. It forms the basic constituent of all the organic compounds. The biosphere contains over 500,000 carbon compounds in them. The carbon cycle is mainly the conversion of carbon dioxide. This conversion is initiated by the fixation of carbon dioxide from the atmosphere through photosynthesis. Such conversion results in the production of carbohydrate, glucose, that may be converted to other organic compounds such as sucrose, starch, cellulose, etc. Here, some of the carbohydrates are utilized directly by the plant itself. During this process, more carbon dioxide is generated and is released through its leaves or roots during the day. The remaining carbohydrates not being utilized by the plant become part of the plant tissue. Plant tissues are either being eaten by the herbivorous animals or get decomposed by the microorganisms. The herbivores convert some of the consumed carbohydrates into carbon dioxide for release into the air through respiration. The microorganisms decompose the remaining carbohydrates after the animal dies. The carbohydrates that are decomposed by the microorganisms then get oxidized into carbon dioxide and are returned to the atmosphere. The oxygen cycle. Oxygen is the main byproduct of photosynthesis. It is involved in the oxidation of carbohydrates with the release of energy, carbon dioxide, and water. The cycling of oxygen is a highly complex process. Oxygen occurs in a number of chemical forms and combinations. It combines with nitrogen to form nitrates and with many other minerals and elements to form various oxides, such as the iron oxide, aluminium oxide, and others. Much of oxygen is produced from the decomposition of water molecules by sunlight during photosynthesis and is released in the atmosphere through transpiration and respiration processes of plants. The nitrogen cycle. Nitrogen is a major constituent of the atmosphere, comprising about 78% of the atmospheric gases. It is also an essential constituent of different organic compounds such as the amino acids, nucleic acids, proteins, vitamins, and pigments. Only a few types of organisms, like certain species of soil bacteria and blue-green algae, are capable of utilizing it directly in its gaseous form. Generally, nitrogen is usable only after it is fixed. 90% of fixed nitrogen is biological. The principal source of free nitrogen is the action of soil microorganisms and associated plant roots on atmospheric nitrogen found in pore spaces of the soil. Nitrogen can also be fixed in the atmosphere by lightning and cosmic radiation. In the oceans, some marine animals can fix it. After atmospheric nitrogen has been fixed into an available form, green plants can assimilate it. Herbivorous animals feeding on plants in turn consume some of it. Dead plants and animals' excretion of nitrogenous wastes are converted into nitrites by the action of bacteria present in the soil. Some bacteria can even convert nitrites into nitrates that can be used again by green plants. There are still other types of bacteria capable of converting nitrates into free nitrogen, a process known as denitrification. Other mineral cycles. Other than carbon, oxygen, nitrogen, and hydrogen being the principal geochemical components of the biosphere, many other minerals also occur as critical nutrients for plant and animal life. These mineral elements required by living organisms are obtained initially from inorganic sources such as phosphorus, sulfur, calcium, and potassium. They usually occur as salts dissolved in soil, water, or lakes, streams, and seas. Mineral salts come directly from the Earth's crust by weathering, where the soluble salts enter the water cycle, eventually reaching the sea. Other salts are returned to the Earth's surface through sedimentation, and after weathering, they again enter the cycle. All living organisms fulfill their mineral requirements from mineral solutions in their environments. Other animals receive their mineral needs from the plants and animals they consume. After the death of living organisms, the minerals are returned to the soil and water through decomposition and flow. Ecological balance. Ecological balance is a state of dynamic equilibrium within a community of organisms in a habitat or ecosystem. It can happen when the diversity of the living organisms remains relatively stable. Gradual changes do take place, but that happens only through natural succession. It can also be explained as a stable balance in the number of each species in an ecosystem. This occurs through competition and cooperation between different organisms where population remains stable. This balance is brought about by the fact that certain species compete with one another determined by the environment in which they grow. This balance is also attained by the fact that some species depend on others for their food and sustenance. Such accounts are encountered in vast grasslands where the herbivorous animals, deer, zebra, buffaloes, etc., are found in plenty. On the other hand, the carnivorous animals, tigers, lions, etc., that are not usually in large numbers, hunt and feed on the herbivores, thereby controlling their population. In the plants, any disturbance in the native forests, such as clearing the forest for shifting cultivation, usually brings about a change in the species distribution. This change is due to the competition where the secondary forest species such as grasses, bamboos, or pines overtakes the native species, changing the original forest structure. This is called succession. Ecological balance may be disturbed due to the introduction of new species, natural hazards, or human causes. Human interference has affected the balance of plant communities, leading to disturbances in the ecosystems. Such disturbances bring about numerous secondary successions. Human pressure on the Earth's resources has put a heavy toll on the ecosystem. This has destroyed its originality and has caused adverse effects to the general environment. Ecological imbalances have brought many natural calamities like floods, landslides, diseases, erratic climatic occurrences, etc. There is a very close relationship between the plant and animal communities within particular habitats. Diversity of life in a particular area can be employed as an indicator of the habitat factor. Proper knowledge and understanding of such factors provide a strong base for protecting and conserving the ecosystems.
Exercises. Number 1. Multiple choice questions. Bit 1. Which one of the following is included in biosphere? A. Only plants. B. All living and non-living organisms. C. Only animals. D. All living organisms. Bit 2. Tropical grasslands are also known as A. The prairies. B. The savannas. C. The steppes. D. None of the above. Bit 3. Oxygen combines with iron found in the rocks to form A. Iron carbonate. B. Iron nitrites. C. Iron oxides. D. Iron sulfate. Bit 4. During photosynthesis, carbon dioxide combines with water in the presence of sunlight to form A. Proteins. B. Amino acids. C. Carbohydrates. D. Vitamins. Question 2. Answer the following questions in about 30 words. What do you understand by the term ecology? Bit 2. What is an ecological system? Identify the major types of ecosystems in the world. Bit 3. What is a food chain? Give one example of a grazing food chain identifying the various levels. Bit 4. What do you understand by the term food wave? Give examples. Bit 5. What is a biome? Answer the following questions in about 150 words. Bit 1. What are the biogeochemical cycles? Explain how nitrogen is fixed in the atmosphere. Bit 2. What is an ecological balance? discuss the important measures needed to prevent ecological imbalances. Project work show the distribution of different biomes on the outline map of the world, with a note highlighting the important characteristics of each biome. Bit 2. Make a note of trees, shrubs, and perennial plants in your school campus and devote half a day to observe the types of birds which come to the garden. Can you describe the diversity of birds?
Chapter 16, Biodiversity and Conservation. You have already learned about the geomorphic processes, particularly weathering and depth of weathering mantle in different climatic zones. You should know that this weathering mantle is the basis for the diversity of vegetation and hence the biodiversity. The basic cause for such weathering variations and resultant biodiversity is the input of solar energy and water. No wonder that the areas that are rich in these inputs are the areas of wide spectrum of biodiversity. Biodiversity as we have today is the result of 2.5 to 3.5 billion years of evolution. Before the advent of humans, our Earth supported more biodiversity than in any other period. Since the emergence of humans, however, biodiversity has begun a rapid decline, with one species after another bearing the brunt of extinction due to overuse. The number of species globally vary from 2 million to 100 million, with 10 million being the best estimate. New species are regularly discovered, most of which are yet to be classified. An estimate states that about 40% of freshwater fishes from South America are not classified yet. Tropical forests are very rich in biodiversity. Biodiversity is a system in constant evolution from a viewpoint of species as well as from viewpoint of an individual organism. The average half-life of a species is estimated at between 1 and 4 million years, and 99% of the species that have ever lived on the earth are today extinct. Biodiversity is not found evenly on the earth. It is consistently richer in the tropics. As one approaches the polar regions, one finds larger and larger populations of fewer and fewer species. Biodiversity itself is a combination of two words, bio, life, and diversity, variety. In simple terms, biodiversity is the number and variety of organisms found within a specified geographic region. It refers to the varieties of plants, animals, and microorganisms, the genes they contain, and the ecosystems they form. It relates to the variability among living organisms on the earth, including the variability within and between the species, and that within and between the ecosystems. Biodiversity is our living wealth. It is a result of hundreds of million years of evolutionary history. Biodiversity can be discussed at three levels. 1. Genetic diversity. 2. Species diversity. 3. Ecosystem diversity. Genetic diversity. Genes are the basic building blocks of various life forms. Genetic biodiversity refers to the variation of genes within species. Groups of individual organisms having certain similarities in their physical characteristics are called species. Human beings genetically belong to the Homo sapiens group and also differ in their characteristics, such as height, color, physical appearance, etc., considerably. This is due to genetic diversity. This genetic diversity is essential for a healthy breeding of population of species. Species diversity. This refers to the variety of species. It relates to the number of species in a defined area. The diversity of species can be measured through its richness, abundance, and types. Some areas are more rich in species than others. Areas rich in species diversity are called hotspots of diversity. Ecosystem diversity. You have studied about the ecosystem in the earlier chapter. The broad differences between ecosystem types and the diversity of habitats and ecological processes occurring within each ecosystem type constitute the ecosystem diversity. The boundaries of communities, associations of species, and ecosystems are not very rigidly defined. Thus, the demarcation of ecosystem boundaries is difficult and complex. Importance of biodiversity. Biodiversity has contributed in many ways to the development of human culture, and in turn, human communities have played a major role in shaping the diversity of nature at the genetic, species, and ecological levels. Biodiversity plays the following roles: ecological, economic, and scientific. Ecological role of biodiversity. Species of many kinds perform some function or the other in an ecosystem. Nothing in an ecosystem evolves and sustains without any reason. That means every organism, besides extracting its needs, also contributes something of useful to other organisms. Can you think of the way we humans contribute to the sustenance of ecosystems? Species capture and store energy, produce and decompose organic materials, help to cycle water and nutrients throughout the ecosystem, fix atmospheric gases, and help regulate the climate. These functions are important for the ecosystem function and human survival. The more diverse an ecosystem, better are the chances for the species to survive through adversities and attacks, and consequently is more productive. Hence, the loss of species would decrease the ability of the system to maintain itself. Just like a species with a high genetic diversity, an ecosystem with high biodiversity may have a greater chance of adapting to environmental change. In other words, the more the variety of species in an ecosystem, the more stable the ecosystem is likely to be. Economic role of biodiversity. For all humans, biodiversity is an important resource in their day-to-day life. One important part of biodiversity is crop diversity, which is also called agrobiodiversity. Biodiversity is seen as a reservoir of sources to be drawn upon for the manufacture of food, pharmaceutical, and cosmetic products. This concept of biological resources is responsible for the deterioration of biodiversity. At the same time, it is also the origin of new conflicts dealing with rules of division and appropriation of natural resources. Some of the important economic commodities that biodiversity supplies to humankind are food crops, livestock, forests, fish, medicinal resources, etc. Scientific role of biodiversity. Biodiversity is important because each species can give us some clue as to how life evolved and will continue to evolve. Biodiversity also helps in understanding how life functions and the role of each species in sustaining ecosystems, of which we are also a species. This fact must be drawn upon every one of us so that we live and let other species also live their lives. It is our ethical responsibility to consider that each and every species along with us have an intrinsic right to exist. Hence, it is morally wrong to voluntarily cause the extinction of any species. The level of biodiversity is a good indicator of the state of our relationships with other living species. In fact, the concept of biodiversity is an integral part of many human cultures. Loss of biodiversity. Since the last few decades, growth in human population has increased the rate of consumption of natural resources. It has accelerated the loss of species and habitation in different parts of the world. Tropical regions, which occupy only about 1/4 of the total area of the world, contain about 3/4 of the world human population. Overexploitation of resources and deforestation have become rampant to fulfill the needs of large population. As these tropical rainforests contain 50% of the species on the earth, destruction of natural habitats have proved disastrous for the entire biosphere. Natural calamities such as earthquakes, floods, volcanic eruptions, forest fires, droughts, etc., cause damage to the flora and fauna of the earth, bringing change to the biodiversity of respective affected regions. Pesticides and other pollutants such as hydrocarbons and toxic heavy metals destroy the weak and sensitive species. Species which are not the natural inhabitants of the local habitat but are introduced into the system are called exotic species. There are many examples when a natural biotic community of the ecosystem suffered extensive damage because of the introduction of exotic species. During the last few decades, some animals like tigers, elephants, rhinoceros, crocodiles, minks, and birds were hunted mercilessly by poachers for their horn, tusks, hides, etc. It has resulted in the rendering of certain types of organisms as endangered category. The International Union of Conservation of Nature and Natural Resources, IUCN, has classified the threatened species of plants and animals into 3 categories for the purpose of their conservation. Endangered species. It includes those species which are in danger of extinction. The IUCN publishes information about endangered species worldwide as the Red List of Threatened Species. Vulnerable species. This includes the species which are likely to be in danger of extinction in near future if the factors threatening to their extinction continue. Survival of these species is not assured as their population has reduced greatly. Rare species. Population of these species is very small in the world. They are confined to limited areas or thinly scattered over a wider area. Conservation of biodiversity. Biodiversity is important for human existence. All forms of life are so closely interlinked that disturbance in one gives rise to imbalance in the others. If species of plants and animals become endangered, they cause degradation in the environment, which may threaten human beings' own existence. There is an urgent need to educate people to adopt environment-friendly practices and reorient their activities in such a way that our development is harmonious with other life forms and is sustainable. There is an increasing consciousness of the fact that such conservation with sustainable use is possible only with the involvement and cooperation of local communities and individuals. For this, the development of institutional structures at local levels is necessary. The critical problem is not merely the conservation of species nor the habitat, but the continuation of process of conservation. The Government of India, along with 155 other nations, have signed the Convention of Biodiversity at the Earth Summit held at Rio de Janeiro, Brazil in June 1992. The World Conservation Strategy has suggested the following steps for biodiversity conservation. 1. Efforts should be made to preserve the species that are endangered. 2. Prevention of extinction requires proper planning and management. 3. Varieties of food crops, forage plants, timber trees, livestock, animals, and their wild relatives should be preserved. 4. Each country should identify habitats of wild relatives and ensure their protection. 5. Habitats where species feed, breed, rest, and nurse their young should be safeguarded and protected. 6. International trade in wild plants and animals be regulated. To protect, preserve, and propagate the variety of species within natural boundaries, the Government of India passed the Wildlife Protection Act 1972, under which national parks and sanctuaries were established and biosphere reserves declared. Details of these biosphere reserves are given in the book India, Physical Environment. There are some countries which are situated in the tropical region. They possess a large number of the world's species diversity. They are called megadiversity centers. There are 12 such countries, namely Mexico, Colombia, Ecuador, Peru, Brazil, Democratic Republic of Congo, Madagascar, China, India, Malaysia, Indonesia, and Australia, in which these centers are located. In order to concentrate resources on those areas that are most vulnerable, the International Union for the Conservation of Nature and Natural Resources, IUCN, has identified certain areas as biodiversity hotspots. Hotspots are defined according to their vegetation. Plants are important because these determine the primary productivity of an ecosystem. Most but not all of the hotspots rely on species-rich ecosystems for food, firewood, cropland, and income from timber. In Madagascar, for example, about 85% of the plants and animals are found nowhere else in the world. Other hotspots in wealthy countries are facing different types of pressures. The islands of Hawaii have many unique plants and animals that are threatened by introduced species and land development.
Exercises. Number 1. Multiple choice questions. Bit 1. Conservation of biodiversity is important for A. Animals, B. Animals and plants, C. Plants, D. All organisms. Bit 2. Threatened species are those which A. Threaten others, B. Lion and tiger, C. Are abundant in number, D. Are suffering from the danger of extinction. Bit 3. National parks and sanctuaries are established on the purpose of A. Recreation, B. Hunting, C. Pets, D. Conservation. Bit 4. Biodiversity is richer in A. Tropical regions, B. Polar regions, C. Temperate regions, D. Oceans. Bit 5. In which one of the following countries the Earth Summit was held? A. The UK, B. Mexico, C. Brazil, D. China. Question number 2. Answer the following questions in about 30 words. A. What is biodiversity? B. What is the different levels of biodiversity? 3. What do you understand by hotspots? Bit 4. Discuss briefly the importance of animals to humankind. Bit 5. What do you understand by exotic species? Question 3. Answer the following questions in about 150 words. Bit 1. What are the roles played by biodiversity in the shaping of nature? Bit 2. What are the major factors that are responsible for the loss of biodiversity? What steps are needed to prevent them? Project work. Collect the names of national parks, sanctuaries, and biosphere reserves of the state where your school is located and show their location on the map of the India.